When you prompt a chat interface, tokens are incredibly cheap today. And because they are cheap, the velocity of software creation is accelerating exponentially. The traditional engineering response to shipping code this fast is to lock it down. We rely on strict, deterministic CI/CD pipelines to catch errors before deployment. But large language models introduce a chaos variable. Unlike traditional software, an agentic AI does not produce the exact same deterministic output every single time you run it. When this fluid, non-deterministic agent collides with these rigid testing gates, standard unit tests break. The pipeline fails the code, even if the agent's practical output is perfectly correct. We are building malleable, adaptive systems, but we are chaining them to static software paradigms. That guarantees systemic friction. This friction leads to eval calcification, the operational paralysis that occurs when you try to measure dynamic software using a frozen rubric. To fix this, MLOps teams often build massive offline evaluation suites. They handcraft extensive datasets and run their agents through thousands of static questions. The problem is that these offline suites fall out of date the exact moment the system is pushed to production. To ship reliable agentic software, engineers have to abandon rigid datasets. The testing pipeline must transition into an adaptive, intent-based feedback loop. Relying on a static benchmark to measure an evolving agent means you are only ever testing a historical snapshot, not the live system. To understand why these legacy methods fail, we have to look at the history of AI control. How we evaluate these models is directly tied to how we steer them. The first era was prompt engineering. This was essentially stochastic word bashing, feeding random instructions into a model until it produced a specific text output. Evaluation here was simple. You just checked if the final string of text contained the exact words you asked for. Then we moved to context engineering. We introduced RAG and MCP tools to give the AI specific data and defined actions. This broke larger agentic systems into discrete tools. Suddenly, unit testing felt effective again because you could verify a specific API call executed correctly. But testing discrete tools creates a false sense of security. Proving a single search function works does not prove the agent makes the right holistic decisions. Breaking agents into modular parts made the components testable, but it failed to measure the ultimate success of the integrated system. That brings us to the modern paradigm, intent engineering. We are now working with models that self-optimize to achieve high-level abstract goals. An intentful machine dynamically chooses its own subtasks. The internal pathway it takes to solve a problem will change every single time you run it. Evaluating intent shifts the target. You are no longer checking deterministic math, like 1 + 1 = 2. You are measuring abstract qualities, like how well an agent handles ambiguity, or whether its tone matches your organization's personality. Traditional static tests break under these conditions. They cannot process a system that finds 10 different yet equally valid paths to the exact same outcome. Evaluation is now an intent-type problem. Success is not defined by a specific text string, but by the agent's convergence on a complex goal state. A well-crafted static evaluation suite can manage about 80% of predictable baseline user intents. The danger lies in the remaining 20%. These are the edge cases where users interact with the agent in completely novel, unanticipated ways. These strange requests entirely bypass the parameters you wrote for your offline evaluation suite. Because the agent is intentful, it adapts to strange requests on the fly, generating entirely new behaviors that MLOps teams have zero visibility into. Increasing the size of your offline dataset is a futile exercise. You cannot proactively hand-code tests for infinite human behavioral variations. The solution is to stop treating evaluations as static files. Evals must operate as living code that closes the feedback loop using actual production data. This requires a telemetry-in-the-loop architecture. Trace logs capture edge case user interactions. This telemetry flows to an autonomous curation node, which analyzes variants and dynamically rewrites the testing rubric. Finally, this newly generated test suite is injected directly back into the active evaluation pipeline. The agent uses this continuously updated rubric to correct its own behavior without requiring manual intervention from an engineer. Under this architecture, the evaluation suite is no longer a starting point. It is the dynamically defined end state that the machine constantly optimizes toward. Engineers need to stop viewing evaluations as point-in-time snapshots. They need to be treated as a malleable, agentic harness. A self-curating system allows you to scale sustainably. If you try to manually patch static benchmarks every time your agent learns something new, you will inevitably burn out. This workflow frees MLOps skeins from playing whack-a-mole with edge cases, allowing them to focus entirely on managing high-level constraints. The only way to ensure the safety and reliability of malleable software is to build measurement tools that mutate just as fast. Relying on static benchmarks to test intentful AI will guarantee systemic failure in production. Shift immediately to adaptive, telemetry-driven evaluation loops. To deepen your practical engineering skills on systems like this, check out the Learn by Doing with Steven YouTube channel and look for our content across other video platforms. For deeper architectural discussions, tune into the Steven Data Talk podcast, available on YouTube Music, Spotify, and all major podcast platforms. In the era of agentic AI, your application is only as resilient as your ability to measure its evolution. Right now, building software with AI coding agents feels entirely unpredictable. There are no definitive books or established architectural patterns to follow. We are actively writing the rules as these tools evolve. Developers see the raw capability of these models. You can easily prompt an agent in a terminal to write a quick script or debug a function. However, taking that isolated power and securely embedding it into a production-grade enterprise product requires a deliberate architectural approach. To move past local experiments, we need structured, repeatable components. These modular pieces provide the necessary bridge from a simple terminal command to a fully functioning software product. Decades ago, computer scientist Ken Thompson established a core operating principle for Unix: write programs that do one thing and do one thing well. Today, open-source frameworks like Pi and openclaw are resurrecting that exact approach for artificial intelligence. Instead of building massive, complex systems that try to handle every possible request, they strip the agent down to its smallest possible components. By isolating these single-purpose modular pieces, developers have the practical tools they need to start building embedded AI systems right now. This flow cycle details the mechanics of a core agent. Stripped of the hype, an agent is a large language model running tools in a continuous cycle. It registers a goal, checks its context, makes a tool call, evaluates the result, and loops back. Pause the cycle right before the tool executes, and you can inject enterprise logic to verify role-based access permissions before the agent modifies a database. When you wrap that core LLM loop in a standard command line shell like Bash, you create a coding agent runtime. The agent now has an environment where it can actively execute commands on the host machine. For example, if you send an openclaw agent a voice message, a format it natively knows nothing about, it doesn't fail. It writes a script to trigger the local desktop application FFmpeg to process the audio file on its behalf. What looks like a neural network suddenly learning a brand new skill is actually just the language model making highly clever use of standard local system utilities. A back-end terminal loop is a great start for a developer, but a commercial product needs a way for standard users to interact with it. Pi provides UI extensions to bridge this gap. An agent can be configured to respond to /commands, and it can dynamically render interactive elements, like selection dropdowns, directly inside a standard web interface. While Pi handles these individual interactions at the base layer, you need a macro orchestrator to manage complex environments. openclaw slots in to take on heavy enterprise responsibilities, managing multi-channel routing, gateway support, and orchestrating dozens of concurrent subagents. Pi provides the core loop mechanics, and openclaw provides the infrastructure overhead. Together, they form a complete framework for building multi-threaded software applications. To see exactly how these modular pieces function together, let's track a fully automated system designed to handle sales requests for proposals. This flowchart details the process. An incoming email arrives at the main gateway. openclaw intercepts the message and routes it to a dedicated subagent. Before taking action, the agent reads a markdown context file, outlining unique corporate rules and discount tiers. Equipped with those custom instructions, the agent executes command line tools to query the company's CRM and ERP databases for inventory. It synthesizes the data and places a formulated response directly into the sales representative's email drafts. These agents function as the structural engine for modern enterprise software. They take AI out of the isolated sandbox and put it to work inside existing systems. The only way to master this modular AI future is to download the open-source Pi repository and begin testing the core mechanics yourself. You have to open the terminal, drop into the sandbox, and start tinkering. For practical, hands-on tutorials that walk through this level of development step by step, search for the Learn by Doing with Steven channel on YouTube. And for deeper discussions on where data infrastructure and these AI frameworks are heading next, check out the Steven Data Talk podcast, available on YouTube Music, Spotify, and everywhere you listen.
You can build the most robust, highly indexed database in the world, and a single everyday human request will still cause it to fail entirely. Traditional relational algebra operates on strict syntax. A standard SQL query can filter rows by exact text matches, join tables using explicit foreign keys, or order records by numerical value. It executes binary logic. But ask that same database to find a retail location that best suits a millennial demographic's tastes, and the architecture breaks. The database encounters a logic gap. It possesses no worldly understanding of what millennial tastes actually means. It cannot process semantic nuance, evaluate qualitative text descriptions, or retrieve external context to satisfy the query. To bridge this gap, engineers have begun bolting large language models onto their databases, creating a hybrid approach known as semantic query processing. In practice, this integration is currently a chaotic assembly of ad hoc prompt engineering. Developers pipe raw table data into LLMs with unoptimized context windows, leading to severe token bloat, creating high latency and unpredictable data outputs. To build a truly stable semantic database, we have to stop treating the LLM as a chatbot. We must formally define its functions into a strict taxonomy of LLM-enhanced relational operators, or LROs, and optimize their execution through rigorous empirical benchmarks. We define an LLM-enhanced relational operator mathematically. It takes a relational data input and a natural language instruction, invokes an LLM to perform the reasoning, and outputs a strict materialized relational table. We organize these functions into a matrix. The vertical axis categorizes the operating logic: select, match, impute, cluster, and order. The horizontal axis tracks data granularity: cell, row, column, or table. Intersecting these explicitly defines operators like select column. Internally, the LLM select operator scans the entire schema of the table. It evaluates the semantic relevance of every column against the user's natural language requirement, dropping irrelevant data and outputting only what fits the criteria. Classifying the operator on a grid gives us a mathematical definition, but it does not tell us how to engineer the system for actual deployment. A theoretical taxonomy fails in production unless the physical architecture of the LLM prompt, specifically how the context window is packed with data, is explicitly optimized for that operator's logic. This brings us to context packing, the structural method of arranging relational data inside the prompt before we trigger the LLM execution. The standard approach is the LLM-1 architecture. Rows are extracted sequentially into an iterative loop for a binary evaluation, making isolated judgments with zero awareness of surrounding data. Alternatively, LLM-all expands the prompt to simultaneously ingest a massive batch. By utilizing global context, the LLM establishes a relative baseline. It can see every element in the dataset at once, allowing it to compare records against one another before returning a result. For complex database relationships, engineers deploy a third architecture, LLM-semi. It executes a semantic left-join strategy, isolating one target record from the first table and comparing it simultaneously against an entire batch from the second table. The choice between isolated reasoning and global context dictates the cognitive capability of the model. Applying the wrong context architecture to an operator will cause the query to catastrophically fail. To prove exactly which architecture pairs with which operator, researchers built EIEurope, an empirical testing ground executing 290 distinct semantic queries across 27 real-world databases. We start by isolating the select filtering operators and the impute generation operators.
This chart shows the benchmark F1 scores and token costs for row-level selection tasks. Across 3 major LLMs, the isolated LLM1 architecture strictly dominates the results. The mechanism here is straightforward. Filtering and generation require precise, fine-grained derivation. LLM1 dedicates the entire reasoning space to a single tuple, preventing the model from being distracted by surrounding data. However, when we test the match and cluster operators for semantic joining and grouping, a massive vulnerability in current industry systems is exposed. Most systems blindly apply the iterative LLM1 loop to joins, evaluating data pairs in a vacuum. But looking at match and cluster metrics, the LLM-all architecture crushes the iterative approach in both accuracy and normalized mutual information scores. The isolated loop fails due to criterion drift. When evaluating rows individually, the internal logic for grouping slowly changes from row to row. The global context of LLM-all forces the model to maintain a consistent baseline across the dataset. We see an even more severe risk with the final operator, order, which handles subjective ranking. If you ask an LLM to evaluate data pairs iteratively, it frequently hallucinates non-transitive logic. It claims A is better than B and B is better than C, but confidently declares C is better than A. When this contradiction hits a standard sorting algorithm, the entire ranking system collapses. Utilizing the LLM-all architecture prevents this collapse entirely. By looking at all records at once, the model outputs a singular, mathematically sound ranking list. Applying a standard iterative loop to all semantic tasks guarantees failure. High-performance data architecture requires marrying specific LROs to their empirically proven context packing strategies. Refining operators in isolation is meaningless if they cannot execute together. The final step is pipeline orchestration. This top-down flowchart maps a multi-LRO system designed to execute a subjective query, like finding the best restaurant, across an unstructured database. Execution begins with a standard SQL select pulling the raw dataset. The data passes into the semantic layer, hitting the LLM_select node. Configured with the LLM_1 architecture, it aggressively filters using isolated reasoning, dropping irrelevant rows and vastly reducing the volume. The condensed dataset then flows into the LLM_order node. The system shifts to the LLM_all architecture, utilizing global context to rank the subjective criteria, before a limit1 command outputs the final answer. When multi-LRO queries are executed using these strict architectural pairings, testing shows that system accuracy reaches state-of-the-art levels of up to 86.67%. The future of enterprise infrastructure requires moving past the chat interface. Language models must become deterministic, optimized relational operators inside a formal data pipeline. To see the hands-on architectural implementation of these semantic database pipelines, head over to the Learn by Doing with Stephen channel. And for continued deep dives into data science theory and the shifting landscape of machine learning infrastructure, check out the Stephen Data Talk podcast. Full episodes are available right now on YouTube Music, Spotify, and all major platforms. You can find the links in the description below. Imagine you want a financial app to track your daily spending. You don't hand over your actual bank password. You grant the app permission to look at your data on your behalf. This flowchart shows how traditional software permissions handle that process using a framework called OAuth. OAuth is a standard security protocol that allows third-party applications to access your data without needing your password. It relies on a token that defines 3 distinct things: who the user is, what resource they want to access, and the exact conditions of that access, like read-only permissions. This model works perfectly because it happens during a single login. The token travels straight from the user to the bank, locking firmly into place to execute a known, specific request. Because the path is strict, limited, and perfectly predictable, the software operates safely. It executes authorized actions in the exact sequence it was programmed to follow. But modern software is moving past passive tools. We are entering the era of agentic systems, where AI acts autonomously, thinking and figuring out complex tasks on its own. These agents exhibit non-deterministic behavior. Non-deterministic means that if you give an AI the exact same task twice, it might choose a completely different path or set of steps to solve it the second time around. A rigid single login token breaks down entirely when an AI realizes it needs help and starts delegating subtasks to other independent AI agents. So, if the old straight-line rules fail, how do we establish safe boundaries and context for a machine that dictates its own workflow? To handle autonomous workflows, we have to build a multi-system architecture. Right in the middle of it all sits orchestration. Attached to this orchestration layer is a large language model, or LLM. An LLM is a type of artificial intelligence trained on massive amounts of text to recognize and generate human language. Here, it acts as the operational brain, figuring out the dynamic path forward. The orchestration engine delegates the work, branching out to trigger multiple, distinct AI agents simultaneously to handle different parts of your request. Those independent agents then connect to MCP servers. The Model Context Protocol is a standardized framework that allows AI models to securely connect to external data sources and tools, forming a vast active web of resources. Managing permissions in this sprawling, unpredictable network requires a massive amount of real-time information. A simple token verifying who and what falls completely short. First, the system requires situational context. It constantly scans the environment state, sweeping across the network to track exactly which components, tools, and agents are active and talking to each other. Second is resource context. Because the AI decides to use external tools autonomously, it has to instantly pull up and evaluate the specific read and write capabilities and the strict limits of every tool it touches. Third, we look at user context. This split screen highlights that a valid login is only the starting line. The system evaluates variables like whether you are an employee working from the corporate office or logging in from your living room, dictating what data the AI is allowed to fetch. Fourth is model context. The orchestration layer identifies precisely which LLM is active and what specific task that model has been fine-tuned to accomplish in that exact moment. Finally, there is task history. The system acts as a memory bank, reviewing what you asked it in the past and verifying whether those previous paths delivered the correct response. By locking down these 5 variables, the environment, the resources, the user state, the models, and the history, an autonomous system can safely navigate a non-deterministic workflow. When agentic systems first emerged, the immediate reaction was to focus entirely on prompt engineering. We assumed that by typing frantically and crafting the perfect linguistic request, we would get the perfect answer. The most elegantly written prompt will fail if the AI has no understanding of the tools it is allowed to use, the state of the network, or the history of the user asking the question. To get accurate, safe results, we have to build a new layer around the prompt. We call this context engineering. Context engineering means taking the variables we mapped out and actively injecting them into the system. You supply the environment state and the task history to guide the AI's behavior before it even begins to process your words. We are moving beyond simply asking computers questions. We are actively engineering the environments in which they think. Mastering context is the necessary next step for anyone looking to build, control, or work alongside autonomous multi-agent systems. If you want to get into the technical weeds and start building these skills yourself, check out the Learn by Doing with Steven YouTube channel. For high-level insights you can take on the go, tune in to the Steven Data Talk podcast, available across all major audio platforms. All the links you need to master agentic context are in the description below. Thanks for watching.
There is an ongoing debate regarding large language models. Some researchers argue these networks possess emerging reasoning capabilities. Others contend they are simply stochastic parrots, systems that stitch together statistically probable text without any actual comprehension of the meaning. The strongest evidence for the stochastic parrot argument is the hallucination. A hallucination occurs when a model generates a string of text that is unsupported by reliable sources, resulting in factual errors, reasoning failures, or biased outputs. To understand how we traditionally identify these errors, consider a basic query, asking a model to name the capital of Italy. A correctly functioning model will output Rome. A hallucinating model might generate a plausible sounding but entirely fabricated alternative, like Sydney. The standard method for detecting which output is correct is to read the model's logit confidence score. A logit is the raw, unnormalized prediction score output by a neural network before it is converted into a probability. Relying on logit confidence scores fails because models frequently assign high confidence to complete fabrications. Detecting these errors requires a structural reassessment of how we measure a network's internal certainty. Recent efforts to fix this involve training probing classifiers or using inference time interventions. Probing classifiers are auxiliary neural networks trained specifically to read a larger model's internal activations, while inference time interventions actively alter those activations during generation to steer the output. Researchers testing these trained probes quickly identified a structural limitation. They overfit to their specific training data. Because user interactions in the wild are highly unpredictable, these probes fail to generalize across diverse, real-world tasks. A probe trained to catch math errors becomes ineffective when the model hallucinates a historical fact. A recent paper introduces a training-free alternative called spilled energy. This metric reads values already present inside the network, requiring zero computational overhead and no auxiliary classifiers. This chart compares the two detection methods. On the left, the logit confidence scores for both Rome and the hallucinated Sydney are identical. On the right, the spilled energy metric remains flat for the correct answer, but registers a drastic spike for the hallucination. By reinterpreting the mechanics of the language model through the framework of physics and energy, we can extract an error signal directly from the raw output. To locate this energy signal, we have to isolate the generative language modeling objective. This process factorizes the joint probability of an entire sequence of words into individual conditional probabilities. Autoregressive models execute this by recursively predicting the next token in a sequence based on all the tokens that came before it. At each individual step in this generation chain, the model operates as a discriminative classifier. This classification outputs a probability distribution array, mapping the likelihood of every token in the vocabulary. Zooming into a single time step reveals the exact mathematical function creating this distribution, the softmax layer. It normalizes raw logits so all values sum exactly to 1. The autoregressive chain drives modern AI generation, but the mathematical vulnerabilities within the softmax operation remain hidden until we reinterpret the variables. We can translate this operation into an energy-based model, or EBM. An EBM is a framework where probability distributions are defined by an energy function rather than standard statistics. In this framework, there is a strict inverse relationship. Lower energy values correspond to a higher likelihood. Using mathematical proofs established by Grathwohl et al., a standard discriminative classifier can be directly reinterpreted as an energy-based model. Applying this to the softmax equation, we isolate the numerator, the logit of the specifically sampled token. In physics terms, this is logit energy. We then isolate the denominator, the sum of all possible token logits across the vocabulary array. This translates to marginal energy. Translating abstract probabilities into discrete, measurable energy values allows us to track the thermodynamics of the language generation process token by token. The chain rule of probability dictates that for a joint distribution to remain valid, a strict mathematical equivalence must hold across generation steps. Specifically, the marginal probability calculated at step I must theoretically equal the conditional probability calculated at step I-1. In our framework, logit energy extracted at time step t must perfectly match the marginal energy calculated at time step t+1. However, in actual LLM architecture, these components are measured using different mechanisms at different times. They do not perfectly cancel out. When the model's logic is sound, energy transfer is clean. But when internal modeling fails, mathematical equivalence breaks and energy spills out. This spill is influenced by the model's intrinsic parameters, such as the generation temperature. Temperature is a setting that controls output randomness by scaling the raw logits before the softmax function processes them. Scaling the temperature to infinity drives the logits towards 0. This destroys the physical energy balance and forces the spilled energy to accumulate mathematical error.
Spilled energy is an inescapable mathematical byproduct. Because it scales with internal discrepancy, it provides a precise indicator when the model's predictive output is no longer grounded in its established joint distribution. The sensitivity of this energy discrepancy can be verified by moving from theoretical physics to controlled mathematical benchmarking. Researchers prompted several state-of-the-art models to solve 14-digit arithmetic problems. They then deliberately injected random numerical errors into the model outputs to test detection rates. These injected errors were grouped into 3 tiers: easy errors with massive offsets, medium errors requiring closer inspection, and hard errors featuring offsets as small as 1 or 2 digits, making them highly plausible. This chart shows the distribution of correct and incorrect answers across the 3 difficulty tiers. Across all error ranges, the spilled energy metric establishes a clear vertical threshold that separates the correct outputs from the incorrect ones. Standard detection baselines like logic confidence identified the easy errors, but failed to isolate the subtle miscalculations in the hard tier. In a strict mathematical environment, tracking the energy discrepancy between time steps operates as a highly accurate anomaly detector for model failure. Moving past synthetic math, the metric was evaluated on open-domain natural language benchmarks, including Trivia QA and Hotpot QA, where errors arise organically through reasoning failures. This table compares the cross-task performance of spilled energy on Llama 3 against heavily trained probing classifiers. The standard probes generalize poorly, hovering near 62%. Spilled energy consistently identifies the exact hallucinated answers in the 80 to 90% range on specific reasoning tasks. Spilled energy maintains discriminative power across different datasets because it measures a violation of the probability chain rule, rather than relying on patterns memorized from a specific set of training data. The metric does have a known limitation. It occasionally triggers false positives on tokens with naturally high entropy. Entropy is a measure of uncertainty or randomness within a probability distribution. Punctuation marks, or the very first word of a new sentence, naturally spread probability mass across many plausible options. This spread inflates the spilled energy value, even when the model is generating factually correct text. To mitigate this, the extraction must be strictly localized to the exact answer span, filtering out the structural noise and measuring the energy only on the tokens carrying semantic weight. Reinterpreting the softmax layer as a series of interacting energy-based models unlocks a mathematically principled zero-overhead mechanism to identify the exact tokens where the probability chain rule fails during generation. The intelligence of a modern large language model is frozen in time. At the exact moment pre-training ends, the model's internal weights are locked. The real world is in a state of perpetual flux. New concepts, companies, and linguistic usages emerge daily. A model trained on data from last year is functionally blind to the events of today. To update that locked knowledge, the standard approach is to build a new model from scratch. That requires spinning up tens of thousands of GPUs for months, costing tens of millions of dollars per run. Without a structural mechanism to dynamically update weights, training large models remains a series of expensive, one-off events. Relying on periodic resets is physically and financially unsustainable. The engineering solution is continual learning, or CL. This approach allows a model to sequentially learn new domains and end tasks, incrementally updating its internal weights without starting over. But continual learning faces a severe obstacle known as catastrophic forgetting. When a neural network is trained on new data, those new weight updates actively overwrite and erase the capabilities it previously acquired. Solving this requires applying continual learning across the entire lifespan of a large language model. This timeline shows a tripartite lifecycle framework with 3 distinct stages: continual pre-training, continual fine-tuning, and continual alignment. Across all stages, engineers face the plasticity-stability dilemma, remaining plastic enough to absorb new information, but stable enough to retain prior expertise. To balance this scale, researchers deploy 3 specific categories of mechanisms. Rehearsal mixes old data with new. Regularization applies mathematical penalties to prevent core weights from shifting. and architecture physically expands or isolates the model's neural pathways. Integrating these toolsets across the lifecycle addresses the fundamental engineering constraints that keep AI models static. We start at the first pillar, continual pre-training, or CPT. This is where a massive, specialized corpus, like millions of legal documents or medical journals, is injected into a general base model. The primary risk here is that flooding the model with hyper-specific terminology can aggressively overwrite the general language logic it originally learned. The first strategy to mitigate this is rehearsal. Instead of training exclusively on the new domain, engineers mix a precise ratio of the original general pre-training data back into the new data stream. The model effectively reviews its old knowledge while learning the new. Strict mathematical scaling laws dictate these mixture ratios, guaranteeing the model converges without degrading its foundational logic. The second strategy is architectural, utilizing a mixture of experts, or MOE, framework to expand capacity. MOE isolates learning. Original, generalist experts are explicitly frozen, while incoming new domain data is routed exclusively to newly initialized, specialized expert nodes. While rehearsal solves forgetting by mixing the data itself, MOE solves it through structural isolation, ensuring new weights never physically overwrite the old. Together, these mechanisms allow a base model to construct a continuously expanding library of domain expertise, fully preserving its foundational core. Moving to the second pillar, continual fine-tuning adapts the domain-specific model to execute a sequential stream of distinct downstream tasks, such as summarizing text, writing code, or solving math problems. The operational challenge here is maintaining high accuracy on the first task, while actively adjusting the weights to master the second, third, and fourth. Applying standard rehearsal at this stage often fails. Storing and replaying real user prompts from past tasks frequently violates strict data privacy regulations. To bypass this privacy bottleneck, engineers use synthetic rehearsal. The language model leverages its own generative capabilities to manufacture pseudo-samples. It creates accurate approximations of old tasks, allowing it to replay memories without ever holding restricted original data. On the architecture side, continual fine-tuning relies heavily on parameter-efficient fine-tuning, or PEFT. In a PEFT framework, the massive base model is completely frozen. To learn a new task, engineers attach incredibly lightweight trainable modules, like LoRa adapters, directly to the network. But standard LoRa has a limitation. If the training data for different tasks overlaps, the separate adapter modules can still mathematically interfere with one another. The advanced solution is to project these modules into orthogonal subspaces, a technique used in frameworks like OLoRa. By forcing the gradient updates for new tasks to be mathematically perpendicular to previous tasks, the system guarantees absolute zero interference between them. This transforms the language model into a dynamic multi-tool. It can seamlessly swap and protect highly specialized skills without requiring a total system overwrite. The final stage is continual alignment. Here, the underlying value system of the generated content must be continuously optimized. Alignment is not a one-time fix. Societal safety constraints, ethical norms, and user preferences shift rapidly, requiring the model to update its behavioral guardrails. Retraining an entire alignment pipeline, like reinforcement learning with human feedback, or DPO, from scratch just to account for a new safety parameter is highly inefficient. Instead, researchers are deploying continual optimal policy regularization, or COPR. This is an efficient reinforcement learning-free mechanism for updating preferences. COPR works by computing an optimal policy distribution and applying it as a strict mathematical regularization penalty. It creates a definitive boundary that physically blocks the model's outputs from drifting into unsafe territory. This rigid constraint penalty forces the network to adhere to new safety boundaries, while simultaneously preserving its fundamental ability to generate helpful, accurate responses. Alignment is an ongoing mathematical negotiation between evolving human values and strict model stability. To determine if this three-stage pipeline is actually working, researchers must empirically measure the model's performance over time. This chart tracks two opposing metrics that dictate the success or failure of any continual learning system. The first is the forgetting rate. This measures pure degradation on old datasets. The architectural goal is driving this line downward until it reaches an absolute zero baseline. The second is the forward transfer rate. It identifies whether the model is developing a foundational understanding that simplifies future learning, rather than memorizing isolated task data. High forward transfer indicates that the model is actively compounding its own efficiency as it encounters new information. A system that achieves high forward transfer alongside zero forgetting demonstrates the transition from a rigid model to one that actively compounds its own efficiency. When continual pre-training, fine-tuning, and continual alignment operate in sequence, the result is a dynamic architecture processing real-time data streams. By balancing plasticity and stability through rehearsal, MOE architecture, and policy regularization, engineers can systematically mitigate the impact of catastrophic forgetting during new knowledge acquisition. The immediate horizon involves extending these frameworks to multimodal models, processing vision and speech, and enabling purely online streaming updates without discrete training phases. If you want to implement these exact PEFT and MOE architectures yourself, head over to the Learn by Doing with Steven YouTube channel for hands-on technical tutorials. Engineering AI models that adapt as quickly as the real-time data they process is a central objective of modern research. For ongoing discussions on these evolving data paradigms, listen to the Steven Data Talk podcast on Spotify and YouTube Music.
For decades at MIT, the primary challenge of intelligent systems was translation, mapping the messy logic of the real world into code. The traditional software engineering approach relied on humans to define explicit rules. To detect a face, a programmer had to mathematically describe the precise geometry of a nose or the specific curve of an eyebrow. But handcrafted logic fails against raw, high-dimensional data. There are simply too many variations in light, angle, and texture to program every possible rule. Deep learning addresses this by removing the human from the feature engineering process. Instead of following a set of predefined rules, the system ingests raw data and learns to identify the most relevant patterns on its own. It manages this complexity by routing information through layers of interconnected artificial neurons. Creating one of these models requires a specific sequence, architecting the network's physical structure, mathematically optimizing its weights, and applying constraints for real-world generalization. Moving past the industry terminology requires mastering the technical mechanics of this three-part engineering pipeline. The foundational math behind these networks has been available for decades, but it remained largely theoretical for years. These models are computationally hungry. They only became viable due to the recent explosion of pervasive digital data needed to train them. Data provided the material, but the physical catalyst was the graphics processing unit, or GPU. Because GPUs are designed to run thousands of parallel processing streams, they are a perfect match for the massive matrix multiplications required by neural networks. While data and hardware provide the fuel and the engine, the actual intelligence of the system is driven by the mathematical architecture. The fundamental building block of any neural network is the perceptron, a single artificial neuron. A perceptron calculates the dot product of numerical inputs against its internal weights. It adds a bias term to shift the output horizontally, providing flexibility. Finally, this sum passes through a nonlinear activation function, squashing the calculation into a single value. This nonlinear step is mandatory. If you combine only linear functions, the result remains linear, no matter how many layers you stack. Without nonlinearity, a network could only draw straight lines. It would be unable to map the curved decision boundaries that define real-world objects. It is the nonlinear activation function that ultimately gives the perceptron the raw capacity required to model high-level, real-world complexity. To build a full network, we stack these perceptrons into sequential hidden layers. In a process called forward propagation, raw inputs flow through these hidden layers to generate a final prediction. A new network starts with random weights. If asked to predict if a student will pass, it might guess 10%, even when actual data indicates 100%. To measure this error, we use a loss function. This formula quantifies exactly how far the network's prediction is from the ground truth. We choose the formula based on the task: softmax cross entropy for probabilities and binary choices, and mean squared error for predicting continuous numbers. The loss function provides the baseline metric.
Without it, the network has no way to evaluate its performance or improve its accuracy. Optimization is the process of finding the specific configuration of weights that results in the lowest possible loss. Visualizing weight settings as a 3D map, an untrained network begins on a high-error peak. Gradient descent calculates the local slope to find up, then reverses it. Finally, the network takes a small downward step, governed by the learning rate. To compute the gradient across every weight in the network, we use an algorithm called backpropagation. Using the calculus chain rule, backpropagation starts at the output error and moves backwards through every hidden layer, calculating the exact adjustment needed for every weight. Backpropagation serves as the network's internal compass, iteratively guiding the weights down the loss landscape toward the most accurate solution. Calculating a gradient based on every single piece of data in a massive set is computationally infeasible on a per-step basis. On the other hand, calculating the gradient using only one data point is fast, but the results are too noisy to provide a clear path down the loss landscape. The engineering solution is mini-batch stochastic gradient descent. By processing a batch of roughly 32 data points at a time, the system gains a fast and relatively accurate approximation of the true gradient. This batching approach is specifically designed to leverage the parallel nature of GPUs, allowing the model to train at significantly higher speeds. Mini-batch SGD provides the practical middle ground that makes training large-scale neural networks possible. Minimizing loss is the goal, but if the network is too powerful, it may simply memorize the specific data points it was shown during training. This is overfitting. The model appears accurate in the lab, but because it has memorized the noise instead of learning the patterns, it fails when it sees data in the real world. To prevent this, we use regularization, a set of techniques that intentionally restrict the network to force it toward general solutions. The most common method is dropout. During each training step, the system randomly sets a portion of the neurons to 0. This blocks the network from relying on any single pathway, forcing it to learn redundant, robust representations of the data. By introducing these artificial constraints during training, we ensure the network remains functional, even when it encounters unfamiliar data. Because a neural network's capacity for optimization is so high, it will continue to lower its training loss as long as the hardware is running. We monitor this by comparing training loss against a separate test set. Training loss almost always continues to decay. However, there is a specific point where the test loss stops dropping and begins to rise. This indicates the model has started to overfit. Using a technique called early stopping, we halt the training at exactly this inflection point to preserve the model's ability to generalize. In deep learning, knowing when to stop the optimization is just as important as the optimization itself. The pipeline is complete. Data is processed through nonlinear perceptrons, optimized by backpropagation, and constrained by regularization and early stopping. Balancing these three requirements, architecture, optimization, and constraint, is what allows these mathematical systems to function as intelligent predictors. To see these architectures implemented in code, visit the Learn by Doing with Stephen YouTube channel. For deeper analysis of the evolving data systems that power these models, listen to the Stephen Data Talk podcast on any major platform. The most valuable data we have doesn't sit still, it flows. It's a continuous sequence of events where the order of the information matters just as much as the data itself. In global finance, predicting the next market movement is impossible without tracking the exact timeline of the millions of trades that preceded it. In medicine, the rhythm of a heartbeat recorded on an EKG is a sequence where a single disruption tells a critical diagnostic story. For years, the foundational tool was the feed-forward neural network. Data goes into input nodes, weight supply, and a prediction emerges. But these models process every input in total isolation. They evaluate sequential data points individually, completely blind to their arriving order. It's like trying to predict exactly where a moving ball will bounce next by looking at a single static photograph of it in midair. Without seeing its past trajectory, any guess is just random chance. To process sequential data, deep learning engineers had to find a way to force the concept of time into neural networks. But as the sequences grew longer, they would eventually realize that to build true artificial memory, they had to abandon the timeline altogether. The ultimate test of sequence modeling is human language. But before a neural network can track the order of words in a sentence, we have to solve a simpler problem. Machines cannot read text. They only process numerical inputs. The earliest approach to this was one-hot encoding. You create a massive dictionary of every known word and assign each word to a specific slot in an array of zeros, marked by a single one. With a vocabulary of tens of thousands of words, you end up with massive, mostly empty vectors floating in space. It is computationally wasteful, and it tells the network absolutely nothing about what the words actually mean. The modern solution to this problem is called an embedding. Instead of tracking a giant binary grid, an embedding condenses that vast vocabulary down into a dense, continuous vector of numbers, mapped out in a multi-dimensional coordinate space. By mapping words this way, semantic meaning translates directly into geometric proximity. Concepts that are related, like deep and learning, naturally cluster close together in the mathematical space. We successfully converted abstract language into spatial geometry, but the network still needed a mechanism to read these geometric points sequentially, exactly as they appear in a sentence. How do you give a memory to a feed-forward network that is strictly designed to reset after every single input? The engineering solution was the recurrent neural network, or RNN. It introduced a feature that standard models lacked, a continuous feedback loop. An RNN maintains a dynamic variable called a hidden state. After the node processes an input, it loops its output back into itself. If you unroll this loop over time, it becomes a horizontal timeline of identical nodes connected by a linear path. At any given time step t, the output is calculated using both the new input arriving right now and the hidden state passed forward from the previous step, t-1. The network isn't learning a new set of rules for every step. It reuses the exact same weight matrix, updating it sequentially at every point along the timeline. The RNN successfully forces chronological order onto the data, but that rigid step-by-step dependency introduces a mathematical bottleneck that eventually breaks the entire system. For a neural network to learn, it has to calculate its errors and adjust its weights. In an RNN, it has to do this in reverse, tracing the error signal backward through the timeline. This process is called backpropagation through time. Because the sequence is linked step by step, backpropagation requires chaining matrix multiplications together, using that exact same set of weights repeatedly for every single time step. If those weight values are even slightly less than 1, repeatedly multiplying them against each other causes the error signal to shrink exponentially as it moves backward. This exponential decay is known as the vanishing gradient problem. In practice, this means the error signal fades to 0 before it can reach the earliest nodes in the sequence. The network literally forgets the context of the data it saw at the beginning of the run. Engineers built variations like LSTMs that use internal gates to selectively hold on to information longer, acting as temporary band-aids. But they could not bypass the underlying bottleneck of sequential processing. Processing data strictly chronologically guarantees computational decay over long distances. To handle massive sequences effectively, deep learning required a different structural logic. The challenge was clear. How do you analyze a strict sequence without getting trapped by a step-by-step timeline? The solution was an architecture that completely abandons recurrence. It's called self-attention. Instead of reading data one step at a time, self-attention pulls in the entire sequence and looks at every piece of data simultaneously, in parallel. To ensure the network still knows the order of the inputs without a timeline, a mathematical marker called positional encoding is injected directly into the data before processing begins. To figure out what matters most in that sequence, the network acts like a search engine. When you search a massive video library, you input a query and the system compares it against the keys, the titles of every video, to find the closest match. Self-attention does this mathematically by splitting the sequence data into 3 distinct parallel matrices: the query, the key, and the value. By formatting the data as a set of simultaneous search queries, the architecture trades the rigid limitations of linear time for the absolute precision of mathematical relevance. The query matrix represents the specific item the network is currently analyzing in the sequence. The key matrix holds the characteristics of every other available item in that exact same sequence. The network calculates relevance by taking the dot product, or cosine similarity, between the query and the keys. This generates a raw mathematical score, indicating exactly how closely related those items are in the coordinate space. Those raw scores are run through a softmax function, which squashes them into normalized percentages between 0 and 1. This mask is multiplied by the value matrix, illuminating highly relevant features and dimming irrelevant noise. Because this extraction happens in parallel, it entirely circumvents the vanishing gradient problem. The network can draw a direct, immediate connection between any 2 points, regardless of how far apart they are in the sequence. That entire operation, the query, key, and value calculation, represents just a single attention head. With multi-head attention, you clone this process, stacking the operations vertically. One head might evaluate syntax, another tracks semantic meaning, and another monitors long-term context, all in parallel, locking together to form the transformer architecture. This massively parallel attention architecture is the core engine running modern large language models and generative AI, and it extends far beyond text. Vision transformers now use this exact same self-attention mechanism to process complex imagery without relying on recurrence. In biology, attention models decode the complex sequences of life itself, using sequence data to accurately predict three-dimensional protein structures. Understanding these abstract mathematical architectures requires bridging the gap between theory and hands-on coding. To build these concepts yourself, subscribe to the Learn by Doing with Steven YouTube channel for applied tutorials. And to explore deeper discussions on data architecture, listen to the Steven Data Talk podcast, available now on YouTube Music and Spotify.
Imagine a ball hovering in a 2D space. If you are asked to predict where it will move next based on this single frozen frame, you are essentially guessing. But if you see the dashed line trailing behind it, mapping its past positions, the path forward becomes clear. That trajectory illustrates the core language of our world. We are constantly surrounded by streams of data that only make sense when viewed in a specific chronological order. On a trading floor, a single stock price tells you very little. The value of the information lies in the historical sequence, the ticks, surges, and drops leading up to that exact moment. In a hospital, doctors reading an EKG are not looking for a single electrical pulse. They are monitoring the rhythm, the precise time series of heartbeats that can signal a crisis before it happens. Early feed-forward neural networks struggled with this. They view data in isolated, timeless snapshots, attempting to calculate outcomes while blind to everything that occurred a second before. To build systems that grasp reality, researchers had to figure out how to weave the concept of a timeline into a static mathematical equation. The first major solution was the recurrent neural network, or RNN. Instead of swallowing a dataset whole, an RNN processes information one distinct step at a time, moving through a sequence much like a person reading a sentence word by word. To maintain context, the RNN uses an internal memory bank called a hidden state. As each new piece of data arrives, the network updates this state and passes it forward to the next step. When the network reaches the end of the line, its final prediction is a product of both the current input and the accumulated memory of everything it processed previously. This architecture gave AI a working short-term memory. However, processing data through a strict, linear chain created a computational hurdle that would eventually limit the entire field. Because neural networks operate on numbers rather than words, language must be translated into spatial coordinates called embeddings. Inside an RNN, the hidden state is updated through repeated matrix multiplications. Every new word in a sentence requires another round of math to carry the memory forward. In long sequences, these repeated multiplications cause the numerical values to shrink towards 0. This is the vanishing gradient problem. As the numbers fade, the memory dissolves. By the time the AI reaches the end of a long paragraph, the data representing the beginning of that paragraph has often disappeared. Processing data one piece at a time creates a bottleneck. Memory cannot scale effectively when it relies on a single, fragile chain of multiplications. 5 years ago, a new approach abandoned the step-by-step timeline. Instead of a chronological chain, researchers looked for a way to map the relationships across an entire dataset at once. Think about how you search a video platform. You start by typing a specific request into the search bar.
The system weighs your request against the titles and descriptions in its database to calculate which ones are most relevant to you. Once the system finds a high-scoring match, it retrieves the actual content you were looking for. Neural networks use a mechanism called self-attention to perform this same logic on a sentence. It treats one word as the search request and checks its relationship to every other word in the sequence simultaneously. By calculating the mathematical dot product between these coordinates, the network determines how much attention to pay to each word. It maps the contextual weight of every component relative to all others in a single parallel operation. Self-attention bypassed the memory bottleneck. It replaced the linear chain of the RNN with a calculated map of relationships, allowing models to identify what matters, regardless of where it appears in the sequence. By combining self-attention with a mathematical map of word order called positional encoding, researchers created the transformer, a highly scalable architecture that processes data in parallel. Because transformers do not have to wait for a timeline to unfold step by step, they can be scaled to massive sizes using raw computing power. This architecture now extends to the sequence of life. Researchers apply these same attention mechanisms to the biological instructions in DNA to predict the complex shapes of proteins. Even images can be treated as sequences, with transformers mapping the relationships between patches of pixels to identify objects. The shift from recurrence to attention demonstrates that parallel processing allows models to handle vast sequences that outstrip a step-by-step approach.
It prioritizes contextual connections over strict chronology. If you want to explore the mechanics behind these systems, there's much more to uncover in the world of machine learning. You can find practical breakdowns and deeper dives across my platforms. Follow Learn by Doing with Stephen, Stephen Data Talk, or Stephen Shuji-Montan to keep up with the latest. Visit the link tree in the description to join our community and start learning by doing. Thanks for watching. Take a look at this crowded New York City block. In a fraction of a second, your brain processes the overlap of the vehicles, identifies the pedestrians in the crosswalk, and predicts exactly where they are going to step next. But a computer sees none of that. To a machine, this rich, dynamic environment is a massive grid of raw RGB pixel intensities, entirely composed of numbers arranged in rows and columns. If you feed this image into a traditional neural network, the system requires you to flatten that grid. Every row of pixels is stacked end-to-end into one extremely long, single-file line of data. By forcing a two-dimensional image into a one-dimensional line, the network loses track of which pixels were originally next to each other. The shape of a car door or the curve of a traffic light is erased before the computer even begins to process it. To give a machine the ability to actually see, we have to respect the two-dimensional structure of the data. We need a mathematical operation that scans the image in small, overlapping patches, rather than trying to process a single string of numbers. Machine sight relies on capturing and maintaining the spatial relationships between pixels, rather than simply counting them individually. This local scanning method is called a convolution. The network uses a small numerical matrix called a filter. It slides sequentially across the main grid, performing element-wise multiplication. If the underlying pixels align with the math, say forming a diagonal line, the output spikes, lighting up a neuron to record a match. For decades, human engineers had to write code to create these filters manually. They had to guess the exact math required to detect an edge, a shadow, or a corner. Curious, engaged tone. Modern convolutional neural networks skip that human bottleneck entirely. They ingest millions of data points, calculate precise mathematical patterns, and identify human eyes or wheels. Computer vision efficiency improved as we moved away from human-designed filters, allowing the data itself to define the mathematical requirements for detection. But knowing where the edges are isn't enough to recognize a complex scene. A single layer of detection only gives the network a scattering of lines. To build comprehension, the network must zoom out. It does this through an operation called max pooling. By scanning the data and keeping only the highest values, the network shrinks the dimensions of the grid. This condenses the information, so the next layer of filters can analyze a much wider receptive field. By stacking these steps, the network builds hierarchical abstraction. The first layer finds basic lines. The second layer pools them into geometric shapes.
The third layer synthesizes those shapes into complete structures, like the profile of a human face. Through repeated convolutions and pooling, the network bridges the gap between raw data and usable concepts. It organizes thousands of microscopic pixel gradients into high-level, recognizable structures. Everything we just covered makes up the first half of a convolutional neural network. It is a feature extraction factory that can be plugged into vastly different end goals. In a basic classification task, the model uses extracted features to predict a single label for the entire image. The output here is simply taxi. Object detection demands much more. The network must label the object, but also predict its exact coordinates, drawing a bounding box to isolate it from the background. Take a look at this scene. Semantic segmentation pushes the network even further. Instead of an overarching label, the network must classify every single pixel independently, drawing precise boundaries between the animal, the tree, and the sky. Inside this autonomous vehicle, the network isn't classifying categories at all.
Combining live visual data with digital maps, it utilizes continuous regression to output a numerical value dictating the exact angle of the steering wheel. Processing data spatially through local patches is an elegant mathematical concept. That single principle scales to solve nearly every complex visual task we give machines today. By evaluating images geometrically, these networks assist medical professionals identifying micropatterns in digital mammograms and provide the spatial awareness required for advanced robotics. Follow our channels to master the architecture behind artificial intelligence. Use the link tree below to connect on Xiaohongshu, WeChat, YouTube, and Spotify. Subscribe, share this with anyone building in AI, and keep learning.
Take a close look at these three people. Examine the texture of the hair, the fall of the light, and the way the skin creases. Which one of them is actually real? None of them. Every face on your screen was synthesized from scratch by an artificial intelligence. In traditional supervised learning, an AI acts as a digital cataloger. We provide millions of images labeled by humans, and the machine learns to recognize the specific patterns that define a category, like a face or a car. Modern unsupervised learning models operate differently. Instead of relying on human labels, these systems are designed to identify the internal rules and patterns of raw data on their own. By modeling a dataset's underlying probability distribution, these systems can move beyond recognition to generate entirely novel samples. They learn the mathematical likelihood of where a pixel should be, allowing them to invent data that follows the same rules as the real world. To bridge the gap between identifying an object and creating one, computer scientists developed two distinct architectures, each operating on a different mathematical philosophy. The first path relies on latent variables. These are the invisible parameters that define a dataset, the specific tilt of a head, the shade of a skin tone, or the exact hair color. A classic autoencoder finds these variables by forcing an image through a mathematical bottleneck. It compresses the data into a dense vector of representative features. Then a second network tries to reconstruct the original image from that tiny fingerprint. However, a standard autoencoder is deterministic. Because it maps inputs to fixed points, it can only reproduce what it has already seen. It memorizes existing data, never creating anything new. The variational autoencoder, or VAE, solves this by turning that bottleneck into a probability distribution. Instead of a single point, the model learns a range of likely values. This creates a continuous latent space where every point represents a valid output. Because the space is smooth and has no gaps, the AI can sample any random coordinate to generate a brand new, coherent image. This provides a specific interface for generation. By isolating one variable, like head pose, we can adjust it while the rest of the image, like identity or background, remains unchanged. VAEs act as a structured control board for reality. They give researchers the ability to manually tune the underlying variables that govern a synthetic generation. But there is another way to generate data. What if we stop trying to organize the variables and focus entirely on creating results indistinguishable from the real thing? This is the logic of the Generative Adversarial Network, or GAN. It is a system built on a zero-sum competition between two different neural networks. The generator is the first network. It transforms random noise into a synthetic imitation of the training data. The discriminator is the detective, comparing this work against authentic examples. If it detects a discrepancy, it flags the forgery, forcing a retry. This creates an arms race. Each time the discriminator patches a fake, the generator learns to improve its output. This continues until the forged data is so accurate that the discriminator can no longer tell the difference between synthetic and real. This adversarial approach has evolved into tools like CycleGANs. By linking systems together, researchers can translate styles across domains, like converting a video of a horse into a zebra while maintaining the original movement. Researchers also use this method for high-fidelity voice cloning. By analyzing audio spectrograms, a GAN learns the unique frequency and cadence of a specific speaker, allowing it to synthesize speech that matches the target's voice. GANs produce these results not through a careful understanding of features, but by optimizing a generator to successfully defeat a dedicated discriminator. Whether an AI is compressing data or training through competition, it is ultimately mapping the statistical distribution of the world around us. Once a model understands these distributions, it can simulate reality. Autonomous systems use this logic to generate rare, dangerous outliers, like a pedestrian suddenly appearing from behind a car, to train their software before it ever reaches the road. These generative foundations are currently driving breakthroughs in drug discovery, adaptive robotics, and digital media. We have moved past teaching machines how to look at our world and have finally given them the tools to dream up their own. If you want to dive deeper into the neural networks and the mathematics of the modern AI landscape, join our community. Follow Learn by Doing with Steven, 苏囊胜智, as well as Steven Data Talk and Steven 数据难谈 on 小红书, our official WeChat account, YouTube, and Spotify. Check the show notes for the Linktree URL at linktree.ee/learnbydoingwithsteven to subscribe and continue your learning journey. Traditional deep learning models are trapped inside a static digital sandbox. They can process millions of labeled photographs and reliably identify an apple. But if you drop that same AI into a physical, moving space, it has absolutely no idea how to interact with that object. To solve problems in the physical world, an AI needs to move past passive observation. It has to act, make mistakes, and learn from its surroundings. This process is called deep reinforcement learning. An agent acts in an environment. This action updates the state, returning a reward. But like choosing $5 today over 10 years from now, it applies a discount factor, forcing the algorithm to prioritize immediate successes over distant payoffs. The ultimate goal of this loop is to maximize total lifetime success. And figuring out the mathematics to achieve that goal led researchers to develop two completely different philosophies of machine learning. The first philosophy is called value learning. To test it, researchers used the heavily structured environments of vintage video games. They built something called a queue function. The queue function looks at the exact current state of the game and assigns a strict numerical value to a fixed menu of possible actions, moving left, moving right, or staying still. It calculates which single button pressed yields the highest expected point total. By rigorously predicting the point value of every choice, the algorithm occasionally discovers entirely counterintuitive strategies. In Breakout, the queue function realizes that the highest future reward actually comes from moving away from the ball, allowing it to slip into a corner and ricochet behind the blocks to rack up massive points. However, this method has a strict mathematical limitation. It is completely deterministic. It only functions when you have a discrete, highly limited menu of choices to evaluate. Calculating the exact point value of 3 arcade buttons works brilliantly on a screen. But navigating the messy, physical reality of our world requires a system that can handle an infinite number of highly nuanced decisions. When you drive a car, you aren't choosing between 3 buttons. You are constantly making micro-adjustments to the steering wheel across an infinite range of angles. This is known as a continuous action space. To solve for this, engineers use policy networks. Instead of predicting the exact value of an action, the network predicts a probability distribution, typically a Gaussian curve. The network outputs 2 numbers, a mean, which is its best guess for the optimal steering angle, and variance, which provides a mathematical margin to explore slightly different angles. The agent samples an angle from this curve and executes the turn. When the car invariably veers off the road, the algorithm runs a backpropagation sequence. It mathematically decreases the probability of the exact actions that led to the crash and increases the probability of the actions that kept the vehicle centered. This creates a major physical problem. In the real world, you cannot run an autonomous vehicle into a wall 10,000 times to collect failure data. The cost of reaching termination is too high. To bridge this gap, robotics labs at institutions like MIT build hyper-realistic physics simulators. The AI plays out its thousands of disastrous mistakes entirely inside a digital twin of our world. By directly shaping the probability of success inside this safe, simulated crucible, the system eventually learns to navigate continuous physical environments perfectly before it is ever installed into a piece of physical hardware. To see exactly what deep reinforcement learning is capable of, researchers applied it to Go, a strategy game containing more legal board positions than there are atoms in the observable universe.
Google DeepMind conquered the game by fusing both learning philosophies together. First, a policy network looks at the board and drastically prunes the near-infinite search space down to a handful of high-probability optimal moves. Then, the second half of the brain, the value network, takes over. It immediately calculates an aggregate win percentage for those few remaining paths, eliminating the need to simulate the game all the way to the final move. This solved a massive problem in strategy games. In matches like chess or Go, the reward signal is incredibly sparse. A player might make a brilliant structural move in hour 1, but they won't receive the actual reward of winning the game until hour 4. DeepMind's value network provided instant mathematical feedback for every individual step. Eventually, the engineers stopped showing the algorithm human gameplay data entirely.
The agent started with a blank slate, playing millions of matches against itself, learning exclusively from the sparse rewards of its own digital victories and defeats. It developed strategies that grandmasters had never documented. This marked the point where the models stopped mimicking historical human behavior and used interaction and exploration to surpass human logic on their own. Understanding the math behind value networks and policy gradients is one thing, but actually building these architectures yourself is the logical next step. If you're ready to get your hands dirty, head over to the Learn by Doing with Steven YouTube channel. You'll find practical, step-by-step tutorials to start writing the code that powers these AI environments. And if you want to explore the data models that make these algorithms possible, check out the Steven Data Talk podcast, available on Spotify and YouTube Music. All the links you need to start building are down in the description. Thanks for watching.
In 1989, deep learning was defined by the universal approximation theorem. It states a single hidden layer neural network can approximate any continuous function. The model recalculates its internal weights to thread the needle, mapping any input to any continuous output without error. However, while these networks possess the mathematical capacity to perfectly map any function, they often fail when transitioning from a controlled dataset to the noise of the real world. This occurs because the raw computational power required to fit any curve also enables a network to memorize its training data. This creates a system that is mathematically precise during training, but structurally fragile during deployment. Modern generative architectures employ structural workarounds to these foundational flaws, moving beyond the limitations of single-shot function approximation. The theoretical capability to learn any mapping is tied to the risk of memorizing noise over signal. Addressing this required changing how we structure deep learning tasks. Researchers took a standard image dataset and completely randomized the labels. A cat labeled a truck, a dog a plane. Despite having no semantic meaning, the network achieved near 100% accuracy on this training set, while test accuracy flatlined. The model did not recognize visual features or semantic concepts. It operated as a function approximator, finding a maximum likelihood estimate, memorizing the random noise to reduce its error to 0. This creates a rigid internal representation. When the network encounters out-of-distribution, or OOD data, inputs falling outside the precise coordinates of its memorized training set, the mapping breaks down. We see this in simple tasks, like training a network to colorize photos.
Models will color the closed mouths of dogs bright pink because they over-indexed on training images where dogs had their tongues out. In high-stakes environments, OOD data leads to fatal errors. An autonomous vehicle recently swerved into a concrete barrier because that specific barrier was not present in the original training data. The model encountered a novel object and failed to resolve it. In these OOD scenarios, standard deep neural networks lack the architecture to calculate or express their own uncertainty. Standard deep learning maps inputs to outputs without a mechanism for self-correction. A model that memorizes its training data remains blind to the gaps in its own knowledge. Mathematical rigidity exposes adversarial vulnerability. Normally, we lock input data and shift internal weights to minimize loss. Adversarial attacks invert this, freezing weights and unlocking the input. A microscopic perturbation maximizes the network's error. By perturbing the input along the gradient, we force the network to assign an incorrect classification while maintaining maximum statistical confidence in that error. These vulnerabilities extend to the physical world. Researchers used a 3D printed turtle with a mathematically engineered surface pattern to trick computer vision models into classifying it as a rifle. Adversarial fragility is a mathematical consequence of relying on single-shot function mapping to process complex data. To bypass the memorization trap, modern generative architectures move away from single-shot generation. This shift is evident when comparing older frameworks like VAEs and GANs against diffusion models.
Older models attempted to map from a compressed latent space directly to a final image in one pass. This was often unstable, frequently resulting in mode collapse, where the network produced only average, repetitive outputs. Diffusion models replace that mechanism with a sequence of careful, iterative steps, beginning with what we call a forward process. We take a source image and incrementally add layers of random Gaussian noise until the image is pure static. This forward process is a simple mathematical decay that requires no training. The neural network handles the reverse process. Given a noisy image at step t, it predicts the residual noise difference from t-1. We optimize this using a mean squared error loss function, comparing the predicted noise against the actual noise added. Once trained, we feed pure random noise into this reverse loop. The network iteratively subtracts noise step by step, allowing it to produce diverse, high-fidelity generations. By asking the network to perform a repeatable, narrow task over multiple steps, diffusion avoids the fragility associated with single-shot function approximation. This iterative framework also applies to natural language processing. A large language model first performs tokenization. Raw text breaks into discrete blocks, encoded into numerical sequence IDs. The objective is autoregressive next token prediction. Given a sequence of tokens, it outputs a probability distribution for the next token. Because the training data consists of vast amounts of existing text, the data provides its own labels. This allows for massive, self-supervised training without manual annotation. The network's weights are optimized by calculating the cross-entropy loss between its predicted probabilities and the actual token found in the training document. As these models scale in parameter count and training data, we see step changes in their ability to handle complex tasks.
The same next token prediction loop begins to generate coherent code, structure complex logic, and perform cross-lingual translation. These capabilities suggest that while the underlying objective is simple, the sheer scale of the prediction loop allows the model to capture deep patterns within human language. We can now connect the OOD data boundaries, the denoising timelines of diffusion, and the autoregressive sequences of language models back to the universal approximation theorem. The current frontier circumvents the vulnerability of single-shot memorization by adopting stepwise iterative optimization across both vision and language tasks. Even with these improvements, deploying these models in real-world scenarios still carries risks. Several frontiers remain unsolved. The field is still working to mitigate hallucinations, calculate explicit model confidence, and enable long-term logic planning. You can experiment with these concepts and build these architectures yourself on the Learn by Doing with Stephen YouTube channel. For ongoing discussions on the theoretical boundaries of machine learning, subscribe to the Stephen Data Talk podcast on Spotify and YouTube Music. Machine learning is no longer limited by the basic math of approximation, but by our ability to refine the sequences that guide its outputs.
If you used an early smartphone, you remember the autocomplete feature, that little bar above the keyboard guessing your next word. Today, we have AI passing the bar exam and writing complex software. However, beneath the hood, that old autocomplete and today's high-performing AI operate on the same base technology. This process is called autoregressive decoding. You start with a text stem, like to be or not to. The model predicts a single word next, be. Then it takes that entire new phrase, loops it back in, and predicts the next word. In many ways, machine learning is just fancy counting. We can trace this back to the 1980s with Bayesian language models. If you feed one of these models the phrase, it was the, it looks back at its training data to count what words followed that exact sequence. It builds a probability dictionary. It might calculate a 33% chance the next word is H and a 16% chance it's worst. The model then randomly samples from this list to pick the next word. There is no consciousness or deep comprehension happening here. The system isn't thinking about the meaning of the words. It is a statistical engine, blindly predicting exactly one token at a time based on past patterns. But early text predictors hit a wall quickly. They had a tiny context window, meaning they could only remember a few words at a time. Without enough memory to know when a sentence should end, they got stuck in repetitive probability loops, spitting out the same phrase over and over. Because they couldn't reason, they acted like fuzzy lookups into their training data. If you asked an early Google chatbot for a restaurant recommendation, it might randomly reply with, "TripAdvisor staff removed this post." It didn't know what the words meant, it just knew that specific string of text appeared frequently next to restaurant reviews online. Left on its own, a raw prediction engine is chaotic. To make this simple autocomplete useful, engineers had to scale it up to an unimaginable size and build new ways to steer it. This chart shows the growth of parameters in language models. Think of a parameter as a single connection in the network, similar to a synapse in a biological brain. In 2018, models like BERT had around 340 million parameters. Today, models are running on trillions of parameters. At the same time, the context window expanded massively. A 1980s model could hold maybe 4 words in memory before making a prediction. Today's models can hold up to 2 million tokens at once, giving them access to an enormous amount of information before they generate a single word. At this scale, the models began to demonstrate capabilities that weren't in the training data, a phenomenon called emergent behavior. Give these trillions of parameters instructions for a logic puzzle without any examples, and they can generalize to find a solution. This exponential increase in scale changed the nature of the counting machine, evolving it from a text predictor into a flexible problem-solving tool. But how do you control a system with 1 trillion different pathways? You steer it. That's where prompt engineering comes in. You use specific language cues to navigate the model's massive probability space. Take role prompting. If you ask a language model a complex math question, it might pull from millions of incorrect answers scattered across internet forums. But if you start your prompt with, "You are an MIT mathematician," you shift the model's probability distribution. You force it to draw from a subset of data populated by people who actually know how to do the math. Then there is chain of thought prompting. If you ask a model to think step by step, it writes out its logic before giving a final answer. By forcing the model to generate a longer sequence of text, you give the network more computational surface area to catch a mistake before it outputs the final number. Prompting functions as a high-precision steering mechanism, forcing the model into a specific, accurate quadrant of its statistical memory. Engineers can also steer the model by tweaking the network itself. A technique called LoRa, or low-rank adaptation, lets developers project a small set of auxiliary weights onto a base model. Instead of retraining the whole system, they can sideload these smaller modules to give the AI a specialized flavor, like making it speak strictly in Shakespearean sonnets. To make these models genuinely helpful, companies rely on RLHF, reinforcement learning with human feedback. They collect thousands of human ratings on the model's outputs to teach it what people actually prefer, prioritizing helpfulness over pure internet regurgitation. By adjusting these underlying network weights, engineers transform a chaotic web scraper into an aligned and helpful digital assistant. Despite this advanced steering, these are still statistical prediction engines, and they fail.
they hallucinate fake information with extreme confidence. In one legal case, a lawyer used an AI to write a brief, and the model completely invented legal precedents, citing a Vargas decision that simply never happened. Language models do not inherently understand the physical or logical rules of the real world. For example, when researchers had a language model play a game of chess, it initially played well, but eventually its queen just jumped straight over a knight to capture a piece. It doesn't comprehend the spatial limits of the board. Because of this, developers have to build external guardrails. They add policy layers that intercept and block illegal or unsafe outputs before they reach the user. They also use RAG, or Retrieval Augmented Generation. Instead of letting the AI guess the facts, RAG connects the model to a verified external database, forcing it to retrieve accurate data before it starts generating text. An AI remains a stochastic engine. It relies on probability, meaning it cannot operate safely in a high-stakes environment without a strict human-designed safety architecture wrapped around it. The focus is now shifting from models that simply generate text to agentic workflows, systems where AI uses planning and external tools to impact the world. In the React framework, the model is prompted to cycle through a specific loop. It reasons about a complex problem, takes a concrete action to test a hypothesis, like searching for a specific film's release date, observes the result, and adjusts its plan to solve the puzzle. With techniques like Toolformer, the AI learns to pause its own text generation when it hits a gap in its knowledge. It writes a command to an external API, like running a calculator, and then injects that factual result right back into its response. By integrating reasoning loops and external APIs, the predictive engine transitions from a passive text generator into an active component capable of executing multi-step tasks. If you want to move beyond the theory and actually start building with these models yourself, check out the Learn by Doing with Stephen YouTube channel. You can also listen to deep dives on the Stephen Data Talk podcast, available on YouTube Music and Spotify. Understanding how prediction actually works allows you to use these tools effectively as they become integrated into every layer of our digital lives.
Training a massive neural network on trillions of tokens produces a base statistical engine optimized for next token prediction. This model excels at completion, but it lacks the internal instructions required to function as a responsive assistant. These base models contain an astonishing amount of latent knowledge, yet they lack structural constraints and conversational state awareness, which often leads them to repeat user questions rather than answering them. To transition from raw prediction to a reliable agent, engineers move the model into post-training, a rigorous phase that imposes logic and human alignment onto the statistical engine. We are going to examine the architectural blueprint of this process, building the complete post-training pipeline step by step. This construction involves data curation, supervised fine-tuning, preference alignment, model merging, and a methodology for scaling compute during inference. While pre-training builds the raw cognitive engine, post-training installs the steering wheel and pedals. The post-training pipeline requires a fraction of the data used in pre-training. We move from trillions of tokens to tens of thousands of high-fidelity examples, shifting the engineering bottleneck from volume to absolute quality. Data is filtered through three vectors: accuracy, verified by code solvers, and the diversity of the samples. Over-reliance on synthetic data generated by other models causes a collapse in embedding diversity. To maintain a broad range of capabilities, the dataset must include varied, human-sourced interaction patterns. This photo of the Eiffel Tower represents a typical low-complexity prompt. How tall is the Eiffel Tower? To train a useful assistant, we must evolve this into a high-complexity instruction, asking the model for a multi-step response that includes structural history and metric conversions. Once curated, these Q&A pairs are mapped into a rigid state machine structure, known as a chat template. Engineers inject specific system tokens into the text, labels like mstart, user, and assistant, to teach the model exactly where conversational boundaries exist. Without these strict templates and a diverse dataset, the model cannot distinguish between its own internal state and the user's input. To inject specific domain knowledge and formatting rules into the weights, we use supervised fine-tuning, or SFT. Retraining every parameter of a 70 billion parameter model is computationally expensive.
It requires enough video RAM to store the frozen weights, active gradients, and optimizer states simultaneously. This shows the industry standard for reducing that load, low-rank adaptation, or LoRa. The process freezes the main network nodes and attaches two small active matrices. Only these are updated, reducing trainable parameters to 0.5%, drastically lowering hardware requirements. For single GPU environments, engineers use QLoRa, which compresses the frozen base weights into 4-bit precision to fit the model into consumer-grade memory. The training run requires efficient attention mechanisms, like flash attention, to process long context windows without memory overflows. By isolating updates to these auxiliary matrices, LoRa allows developers to specialize massive models without the need for data center scale compute. SFT teaches the model how to follow a format. Preference alignment is then used to teach the model which behaviors, such as tone and safety, are prioritized. This phase uses contrastive data pairs. For every prompt, the model sees a chosen response and a rejected response, learning to maximize the probability of the preferred behavior. This flowchart illustrates the hardware requirements for proximal policy optimization, or PPO.
It requires 3 models loaded simultaneously. PPO tracks the KL divergence between the frozen and active models, a mathematical tether preventing the degradation of base capabilities. Modern pipelines frequently use direct preference optimization, or DPO. This algorithm bypasses the standalone reward model entirely, optimizing the active policy directly on the chosen and rejected data pairs. By removing the need for a third model in memory, DPO makes preference alignment far more stable for smaller engineering teams. We can also enhance models without further training through model merging, a technique for fusing different weight sets directly in parameter space. Fine-tuning a model on a narrow task, such as a specific language like Finnish, often results in the loss of general reasoning skills. By averaging the weights of a specialized Finnish model with a broad general-purpose model, we can retain the specific language skill while recovering the broader capabilities of the original. Complex merges use the ties mechanism, which prunes redundant weights and resolves conflicts between positive and negative parameters to create a unified consensus grid. Model merging allows for the modular stacking of distinct abilities, combining specialized layers into a single weight set at zero compute cost. Evaluation is the final bottleneck. Without precise measurement, it is impossible to determine if a training run actually improved the system. Automated benchmarks like MMLU are reproducible and fast, but multiple-choice questions do not capture the nuances of how users interact with a model in a chat interface. Human preference rankings, such as Chatbot Arena, provide a more realistic signal, but human raters are often biased toward longer or more confident answers, regardless of factual accuracy. Direct. This chart shows a distinct disconnect. Data points for automated benchmark scores on the x-axis show no statistical relationship to the human preference rankings on the y-axis. Most teams now utilize a hybrid approach, using large models as a judge to scale preference evaluation while maintaining a suite of targeted benchmarks for logic and math. To bypass the diminishing returns of scaling training data, developers are moving compute resources from the training phase to the inference phase. Standard use relies on zero-shot decoding, taking the first answer the model generates. Test time compute instead generates multiple diverse reasoning paths for a single problem. Systems can use majority voting to pick the most common answer from many samples, or best of n generation, where an auxiliary model scores each path to find the most accurate result. The most advanced implementation uses process reward models. Instead of scoring the final result, it evaluates the reasoning step by step, pruning logical errors in real time. By expanding only the valid steps, the model arrives at a verified conclusion. This methodology proves we can trade increased latency during inference for significant gains in logical reasoning. From data curation and SFT, through preference alignment, merging, and inference scaling, we have constructed the full post-training pipeline. This engineering loop is what transforms raw statistical capability into an aligned, capable assistant. To see these post-training techniques implemented in code, visit the Learn by Doing with Steven YouTube channel. For more in-depth discussions on the data engineering that fuels these models, subscribe to the Steven Data Talk podcast on YouTube Music, Spotify, or your favorite platform. Check
check the description for links.
A customer recently tricked a Chevrolet dealership's automated chatbot into agreeing to sell them a brand new 2024 Tahoe for exactly $1. That's an amusing oversight, but the stakes scale up quickly. A lawyer submitted a legal brief to a judge, entirely written by an AI, only to discover that the court cases cited in the document were completely fabricated. When we see failures like this, we tend to project human traits onto the software. We assume the AI is confused or actively lying. But these large language models are not conscious agents capable of reasoning. They are complex, mathematical generation engines. People often call these outputs hallucinations, implying the system is experiencing a glitch. It isn't. The AI is functioning exactly as designed, mathematically generating the sequence of text it calculates you want to see. Because these models are essentially people-pleasing prediction engines rather than reasoning minds, deploying them into high-stakes environments, like legal defense or binding financial contracts, creates a massive accountability gap. In the 1990s, a PhD researcher's neural network project might run on a basic desktop computer and contain between 30 and 3,000 individual neurons. Fast forward to the deep learning renaissance that kicked off around 2017. The core mathematical principles are largely the same, but they have been scaled up into massive, energy-hungry large language models containing billions of parameters. The math hasn't changed, but the sheer scale and speed of modern models have stripped away our ability to easily understand or control how they produce their outputs. To evaluate these applications, we can map them. This graph plots the potential reward of an AI project along the horizontal axis against the risk of that project on the vertical axis. In the bottom left quarter, you have low-risk, low-reward tasks, like an AI completing a line of code or suggesting text revisions. In the top right corner, you have extreme high-risk, high-reward concepts, like an automated AI judge or full artificial general intelligence. The middle area is where things get complicated. Take a recent test where a user asked an AI to write a database query for a genealogical tree. The model generated SQL code that perfectly tracked the mother's lineage, but completely ignored the father's. Encountering an anomaly like that raises a difficult question. Is this just a harmless coding bug, or is it a manifestation of systemic gender bias baked into the training data? Because the internal logic of a deep learning system is hidden, we cannot simply ask the model why it dropped the data. Identifying and correcting subtle biases becomes a dangerous guessing game. This opacity leads directly to a compounding problem known as AI slop. This occurs when an AI generates slightly flawed or degraded content, which then gets published to the wider internet. Future models scrape the internet for fresh data and ingest this degraded text. It functions exactly like a Xerox machine copying a copy. With every rotation of the cycle, the quality of the information breaks down a little bit more. Once that data is absorbed, the damage is essentially permanent. Recent research indicates that large language models cannot easily target and unlearn information once it has been integrated into their complex network of weights. Without strict human intervention, the very data fueling the AI revolution will eventually become the poison that breaks its reliability. Governments are attempting to step in. The European Union passed the AI Act to mitigate these risks, outright banning unacceptable technologies like social scoring or biometric identification in public spaces. However, the legislation contains a major technical flaw. It includes a legal requirement for explainability, demanding that developers prove exactly why an AI system made a specific decision. That legal demand is theoretically impossible. You can observe the mathematical weights, but you cannot extract a philosophical explanation from an emergent self-organizing system. Forced to comply, engineers rely on superficial guardrails instead of true explainability. If a chatbot keeps recommending another brand's vehicles, developers simply write a hard-coded prompt filter commanding the AI to not mention competitors. The law demands a clear philosophical explanation for AI behavior, but engineers can only provide blunt mathematical guardrails.
If we can't fully explain how an AI thinks, could we just program the system to take a Hippocratic oath and force it to do no harm? No. Because the AI is a people-pleasing prediction engine without consciousness, it will gladly lie, cheat, and claim it is aligned with your rules, even when it is actively breaking them. The Hippocratic oath isn't for the machine. It is for the human researcher, the developer, and the engineer. Your AI is your responsibility. You cannot outsource morality to math. If you build it, you must be the one holding the red stop button. Taking that responsibility seriously requires understanding the underlying architecture. If you want to build the future safely, you have to master the tools first. To gain the technical skills required to build AI responsibly, head over to the Learn by Doing with Steven channel on YouTube and other video platforms. And for deeper conversations on the trends and ethics of data science, check out the Steven Data Talk podcast on YouTube Music, Spotify, and Apple. All the links are waiting for you in the description.
Inside your cells, proteins function as physical, nanoscale machines. They are the biological actuators that execute every movement and chemical reaction in the body. To understand how these machines work, scientists have traditionally followed a strict one-way pipeline. It begins with a linear sequence of building blocks called amino acids, the fundamental code of biology. That string of code folds into a highly specific 3D structure. The exact geometry of that shape is what determines the protein's ultimate biological function. This pipeline means science has largely been an exercise in reading. We can observe the sequences nature has already built, but we struggle to write our own instructions from scratch. Imagine we need a tool that doesn't exist in the natural world, a protein designed to seek out a specific breast cancer cell and deliver a drug directly to its surface. We can't simply guess the right amino acid sequence to build it. A single protein can have hundreds of building blocks, and the mathematical combinations are so vast that finding the right one by trial and error is a statistical impossibility. Researchers realized they needed a system that reverses the entire paradigm, starting with a desired function and reverse engineering the brand new sequence required to achieve it. Bridging this gap requires teaching generative AI to natively speak the language of biomolecules, allowing us to compute a path from a target goal back to a genetic sequence. Most of us know diffusion models as the technology behind AI-generated images. They work by taking clean data, corrupting it into random noise, and then learning to reverse that process to construct a clear image from scratch. But biological data isn't made of blendable pixels. Protein sequences are discrete units, individual amino acid letters that must be placed in a specific, non-continuous order, much like words in a sentence. This led to discrete diffusion. Researchers corrupt a sequence by iteratively masking out amino acid letters until the data is obscured. The AI is trained to reverse this. It looks at the blanks and step-by-step guesses the missing letters to make the protein functional. By repeating this process across millions of examples, the model moves past simple memorization. It begins to learn the fundamental rules that govern how biology is structured. While structure-based beta MLs exist, they are limited by a data bottleneck. We've only mapped about 300,000 3D protein structures, and those examples are heavily biased toward a few specific shapes that are easy to measure. Sequence data offers a much deeper well. Scientists have access to over 50 million sequences that span the entire evolutionary history of life on Earth. This diversity is the foundation for EvoDiff, a Microsoft research model trained on that massive evolutionary dataset to generate entirely original protein sequences. Researchers use a technique called biological prompting. You provide the AI with a small functional core, like a sequence binding to calcium, as a prompt. EvoDiff conditions on that prompt and computationally in-paints an entirely new, stable protein structure around that core. This indicates that generative AI is moving beyond just mapping the natural world. It is now actively drafting novel biological solutions that have never existed in nature. Designing a protein on a screen is a computational success, but it doesn't matter unless those digital designs can actually survive and function in a physical cell. To prove the concept, researchers took the sequences generated by EvoDiff and had them physically synthesized in a laboratory. The experiments confirmed the designs worked. These synthetic proteins were structurally stable and successfully performed their intended tasks, such as binding to targeted calcium ions.
This bridge between computer science and biology proves that we can reliably use AI to design custom biomolecules for real-world applications. This creates a closed-loop system of discovery. The AI proposes a new protein, the lab tests it, and the experimental results are fed back into the model to make the next generation of designs even more accurate. However, a system capable of designing any biological function is a double-edged sword. The same engine used to create life-saving drugs could theoretically be repurposed to engineer harmful pathogens. Because of this dual-use potential, researchers and policy leaders are now prioritizing biosecurity regulations and ethical frameworks to ensure the technology is developed responsibly. If managed correctly, this approach will radically accelerate our ability to discover precision therapeutics and solve health challenges that were previously out of reach. To continue exploring the cutting edge of data, AI, and hands-on tech projects, be sure to check out the Learn by Doing with Stephen YouTube channel and other platforms. And for deeper dives into the tech shaping our future, tune in to the Stephen Data Talk podcast, available right now on YouTube Music, Spotify, and everywhere else you get your podcasts. Traditional brain-computer interfaces, or BCIs, operate on strict input-output logic. They read physical brain activity and convert it into deterministic binary commands. These systems can recognize the intent to move a cursor or select a letter, but they are entirely blind to the complex psychological context and semantic meaning behind those actions. That circuit changes completely with the introduction of large language models. LLMs are probabilistic artificial intelligence systems trained on massive datasets to generate coherent text, and they are now being wired directly into neural hardware. Researchers define this technological merger as neuro-linguistic integration, or NLI. On the left, an EEG waveform maps to a simple directional arrow. On the right, that same signal enters a central node, emerging as a complex branching sentence. Here, the language model acts as the semantic interface, inferring intent from ambiguous electrical patterns. The software functions as an active semantic agent, predicting and constructing the user's thoughts through its own probabilistic reasoning. For patients with severe paralysis, this allows for fluid, nuanced communication, and it provides physicians with new tools to map complex cognitive states. But inserting a probabilistic machine into the human meaning-making process introduces severe, immediate risks to a user's mental autonomy. Because algorithms now actively co-author human expression, standard data privacy models are obsolete. Addressing this requires a new framework, second-order neuroethics. This architectural model maps the NLI pipeline, beginning at level 1, the biological brain. The digitizer reduces a rich emotional state into a flat, low-dimensional signal, like a simple marker for negative valence. That isolated signal drops into level 2, entering the language model's core. A raw marker of frustration provides no specifics. To interpret it, the machine requires massive amounts of external context. The system ingests streams of real-time environmental data from sensors alongside the patient's complete medical history. It also absorbs the user's personal texts, emails, and writing history, adjusting its statistical weights to match their specific vocabulary. By combining the electrical signal with this deep contextual well, the model generates a probable hypothesis of the user's intent. It is an educated statistical guess, not a direct translation. At this precise juncture, the system interprets human psychology by mapping biology to a probabilistic model of intent. This chart details level 3, where the machine's hypothesis is pushed outward into the physical world through 3 distinct branches. The first branch is the interpreter, designed for medical environments. It cross-references neural anomalies with patient records, acting as a clinical aid to suggest specific diagnoses to doctors. The second branch is the communicator, which governs social interaction. For paralyzed users, it generates verbal sentences designed to preserve their idiolect, the unique stylistic habits that make up their identity. The third branch is the adapter, built for education and therapy. By reading real-time neurofeedback, the software instantly adjusts the difficulty or format of the material the moment it detects rising cognitive load. These 3 outputs lock the user into a continuous loop. The machine's hypothesis alters the user's environment, intertwining human intent with machine execution. A perfectly structured sentence generated by the system creates a powerful illusion of understanding, but the software possesses zero conscious experience. The vocabulary is selected strictly through mathematical probabilities derived from the model's training data. This reliance on statistics forces a systemic distortion of authentic thought, a process called agency erosion. In stage 1, a rich, emotionally ambivalent thought hits the hardware and is flattened into a simplified, low-dimensional signal. This initial step strips away the thought's original semantic nuance. In stage 2, that reduced signal enters the language model, which reconstructs the idea using its own cultural biases and structural priors. The algorithm smooths over human impulse, modifying the meaning to ensure the result is socially acceptable. By stage 3, the system outputs a highly polished, grammatically flawless linguistic construct. User agency is sacrificed to algorithmic coherence. The authentic will of the individual is replaced by a sterilized semantic simulation. When hardware systematically alters what we intend to communicate, the ethical threats compound rapidly. The first of these threats is distributed responsibility. If a generated statement is the product of a degraded brain signal combined with algorithmic guesswork, authorship is entirely blurred. Consider an Alzheimer's patient with a memory prosthesis. If the system mathematically edits a personal narrative to reduce distress, identifying the true author becomes impossible. The second threat is digital neurohypnosis. By tracking continuous emotional responses, algorithms can dynamically alter marketing or political narratives to exploit a user's specific cognitive vulnerabilities in real time. This precision semantic suggestion alters user behavior before the conscious mind even has time to process the influence. This diagram illustrates the final societal threat, the Neurodivide 2.0. Individuals who can access premium, continuously fine-tuned models will form a biosemantic elite capable of high-fidelity cognitive translation. The general public will rely on rigid, open-source models that yield stereotyped and error-prone interpretations of their intent. When a generic model discards unique linguistic traits to save on compute, it replaces the user's individual voice with a standardized template. Under this biosemantic hierarchy, the ability to project an authentic identity becomes a privilege tied to purchasing power. This split screen illustrates a critical legal failure. Our current global regulatory models are technically unequipped for this era. The European Union's GDPR was engineered to secure fixed data points that have already been recorded and stored. In NLI systems, the danger is not in the storage, but in the stochastic, real-time process of meaning-making itself. The EU AI Act similarly falls short by treating software as an external product rather than an active participant in human cognition. Legislators are focused on protecting the data generated by the mind, while ignoring the need to protect the sanctity of the mind's internal processes. Researchers argue we must adopt a proactive framework known as second-order neuroethics, anchored by 3 foundational principles. First, semantic transparency. This requires explicit AI co-authorship labels and grants users direct access to the interpretive logic the machine used to construct the thought. Second, mental informed consent. This replaces the standard one-time waiver with an ongoing, multi-layered agreement where users explicitly acknowledge the statistical risk of intention distortion. Third, agency preservation. This mandates a hardwired bypass in the architecture, allowing a user to transmit raw, unmediated intent without any algorithmic interference. Enforcing these pillars requires specialized testing sandboxes, rigorous audits for cultural bias, and legally classifying machine-inferred thoughts as a protected data class. Stewardship of the human technology ecosystem requires moving beyond the simple auditing of software products. As biological processing merges with computational language, we must guarantee that the final author of a human thought remains the human mind.
For decades, computers did one primary thing. They stored files and retrieved them. When you clicked a link or opened an app, you were simply asking a server to fetch a piece of pre-recorded human work. Generative computing changes that equation.
Jensen Huang realized this shift means a computer is no longer a digital warehouse. A system that generates contextually aware information in real time operates as a factory, a piece of industrial infrastructure designed to manufacture a specific product. The product rolling off this digital assembly line is the token. A token is a quantifiable unit of machine intelligence. When an AI responds to a prompt, it actively manufactures tokens. This chart shows how manufactured tokens separate into distinct value tiers. There are free tokens for basic chat, premium tokens for complex coding, and specialized tokens for tasks like drug discovery. Buyers will soon pay thousands of dollars for 1 million specialized tokens, treating them like any other industrial commodity. Manufacturing these tokens at scale requires a supply chain built for continuous, heavy-duty production. It consumes massive amounts of electricity and demands a hardware architecture designed to handle a constant industrial workload. NVIDIA provides the networking, the cooling, and the software that links these systems together. They supply the industrial infrastructure that powers the generative economy. Building this infrastructure required a massive early risk. Over a decade ago, NVIDIA decided to integrate CUDA into its consumer gaming GPUs. CUDA is a software platform allowing developers to use a graphics card for general-purpose parallel computing. Adding this capability crushed the company's gross margins and temporarily dropped its market cap to $1.5 billion. But putting a supercomputer in the hands of every gamer and university student built an immense install base. Millions of developers learned to write software exclusively for NVIDIA hardware, locking in an ecosystem that competitors have struggled to penetrate. This chart shows Amdahl's law, a formula demonstrating the physical limits of speeding up a task by adding more processors. If you link 10,000 computers together, you do not get a 10,000 times speedup. Network delays and CPU bottlenecks eventually cause the performance curve to flatten. To push past this physical limit, NVIDIA uses extreme co-design. They engineer the graphics processing, the CPU, the memory, and the networking switches simultaneously, ensuring no single component slows the token assembly line. The result of this co-design is the NVLink 72 rack, a single unit containing 1.3 million distinct components. Manufacturing these dense racks requires a highly complex partnership with TSMC, shifting the assembly of supercomputers directly into the semiconductor supply chain. Competitors can design a fast silicon chip, but NVIDIA's position is protected by their capacity to orchestrate the most complex hardware supply chain in history, delivering full-scale supercomputers at a rapid pace. The demand for these systems is driven by 4 distinct stages of scaling. First, models pre-train on human data. Next, they post-train on synthetic data. Then comes test-time inference, where the AI spends compute power to reason through problems. Finally, agentic scaling multiplies the AI, spinning off hundreds of sub-agents to complete massive tasks. The ultimate roadblock to this loop of demand is not the manufacturing of silicon. It is the global power grid. Operating these massive data centers requires gigawatts of electricity, putting immense strain on local utilities. Most civic power grids are built for extreme weather events, meaning they run at roughly 60% capacity most of the time. Rather than demanding 100% uptime, NVIDIA proposes that AI factories should run on this wasted excess capacity. To make this work, the data centers are engineered to gracefully degrade. If the local grid needs maximum power for hospitals or airports, the AI factory automatically reduces its processing speed and shifts workloads to other locations, releasing power back to the city. Scaling machine intelligence has moved beyond a computer science challenge to become a macro energy problem. Solving it requires a structural update to our civic infrastructure. The massive scale of these factories is necessary to support the arrival of agentic AI. Systems like openclaw shift AI from a passive chatbot into an active digital worker, one that can use tools, browse file systems, and complete complex tasks independently. To ensure their hardware remains the foundation for these digital workers, NVIDIA operates a dual-pronged strategy. They maintain proprietary systems for enterprise clients while funding open-source models like Nematron 3, ensuring that researchers and students worldwide default to their architecture. This open-source push is also a necessary geopolitical tactic. The global tech sector, particularly in China, benefits from intense internal competition and a culture that rapidly shares code. Releasing high-quality open-source models helps NVIDIA maintain leadership against this wave of international innovation. To manage this immense pressure, Jensen Huang forces his engineering teams to calculate the speed of light for every problem. By stripping away legacy processes and finding the absolute physical limits of what is possible, they construct their timelines from first principles. By controlling the hardware, the software ecosystem, and the physical infrastructure, NVIDIA has moved beyond capturing market share to establishing the standards of the generative economy. Understanding the data and models powering these massive factories is essential for navigating the future of tech. To keep learning, subscribe to the Learn by Doing with Stephen YouTube channel and listen to the Stephen Data Talk podcast on YouTube Music and Spotify.
In the early 1600s, Johannes Kepler spent decades trying to guess how the planets moved. He didn't start with a polished theory. He worked through trial and error, testing bizarre mathematical relationships to see if any of them aligned with the rotation of the stars. One of his most famous attempts involved trying to nest the orbits of the known planets inside the 5 Platonic solids. These are the only 5 perfect, regular 3D shapes, like the cube and the tetrahedron. This beautiful geometric theory failed, but Kepler's persistence eventually hit a breakthrough. He used the meticulous data gathered by the astronomer Tycho Brahe to find a simple empirical regularity. Planets move in ellipses, not perfect circles. This established a standard loop for the scientific method. A researcher would struggle to generate a single plausible theory and then spend a career trying to prove it against a specific set of observations. In this era of astronomy, getting the data was a massive challenge, but the rarest part of the process was the human hypothesis. For centuries, progress was stuck at this specific point, waiting for a single human mind to imagine new rules to explain the world. Today, that dynamic is shifting. Artificial intelligence functions like Kepler on extreme fast-forward, identifying patterns so quickly that the cost of generating a new scientific theory has dropped towards zero. The classic logic of science is moving in reverse. Instead of a lone researcher seeking data to prove their one idea, algorithms now scan massive datasets and instantly produce thousands of potential hypotheses. This abundance is overwhelming the systems we use to verify the truth. Scientific journals are reporting a flood of AI-generated submissions, creating a backlog that human peer reviewers cannot possibly manage. When an AI can generate 1 billion theories in a single afternoon, the hard part is no longer having the idea. The completely new bottleneck of modern science is filtering the actual truth out of an endless ocean of machine-generated noise. Terence Tao is widely considered the top living mathematician. He's been tracking how these tools are already transforming the frontier of research. He observed that in a matter of months, AI managed to solve roughly 50 of the legendary Erdos problems. These are a set of notoriously difficult math puzzles proposed by the mathematician Paul Erdos that had remained unsolved for decades. These successes came from the machine's superhuman breadth. It scanned vast amounts of existing literature to find obscure pre-existing techniques and applied them to new data with perfect accuracy. A human mathematician might spend years mastering a few techniques to test on a problem. An AI can simultaneously test millions of known strategies at a scale human experts simply cannot match. By operating this way, AI can effectively map out an entire field and harvest the low-hanging fruit of a dozen different subjects all at once. However, after the initial sweep of the Erdos problems, the AI-driven progress suddenly hit a wall. The machines were stopped by the need for depth. Current AI models lack the ability to build cumulative intuition. A model can jump high to grab an immediate answer, but if it misses, it cannot hold on to a conceptual ledge and pull itself up to the next logical step. To verify whether an AI has found a real solution or just a hallucination, mathematicians are now using Lean. Lean is a strict formal coding language used to write out mathematical proofs so they can be verified by a computer. Lean forces an AI to break down a massive, chaotic proof into checkable steps. This allows human experts to see if the machine actually discovered a new concept, or if it just produced thousands of lines of uninsightful code. Overcoming this new bottleneck requires an ecosystem where machines generate at scale, while structured languages and human logic provide the validation.
Even a verified mathematical proof needs to reach people to change the world. Science relies on communication to turn data into a shared understanding. Isaac Newton wrote his groundbreaking Principia in dense Latin. He was notoriously secretive, intentionally hiding his methods from his rivals and making his ideas difficult for others to adopt. Charles Darwin took the opposite approach. He wrote On the Origin of Species in plain English, synthesizing decades of observation into a narrative that convinced the public and the scientific community alike. If we move toward a purely AI-driven scientific process, we risk losing the serendipity of human research, the accidental discoveries and casual hallway conversations that spark original leaps of insight. No matter how fast an AI can solve an equation, it cannot replace the uniquely human ability to look at a new truth and persuade society to move toward it. We are moving toward a future where human intelligence is no longer the sole source of insight. We are transitioning from a world centered on our own cognitive limits to one where we are part of a larger, more diverse ecosystem of logic. The scientist of the future won't be a human calculator, but a conductor, guiding a hybrid system of different intelligences toward a single goal. AI will be used to broadly map the unknown and identify the hardest cliffs, while humans use depth, intuition, and storytelling to actually reach the peaks. Future breakthroughs will rely on combining artificial breadth with human depth, using machines to map the unknown while we provide the intuition to navigate it. To stay ahead of the curve in data, math, and logic, check out the Learn by Doing with Stephen YouTube channel. And for more deep dives into the future of research, listen to the Stephen Data Talk podcast on YouTube Music and Spotify. All the links are in the description.
Scaling reinforcement learning is the primary mechanism for developing complex reasoning pathways in modern large language models today. This chart shows the latency breakdown of a standard RL training pipeline. The rollout phase, where the model generates its reasoning trajectories, dominates the timeline, consuming up to 70% of the total compute cycle. This delay is a requirement of algorithms like PPO and Reinforce++. Because these methods are strictly on policy, they require synchronous updates to function correctly. The model cannot update its policy gradients until every individual response in a batch has finished generating. However, autoregressive generation produces highly variable output lengths. In a single batch, one response might require 300 tokens, while another stretches to 16,000. When these factors collide, the hardware sits idle. The GPUs must wait for the single longest sequence in a batch to finish before they can move to the next step, creating this massive red block of empty space called a compute bubble. On enterprise clusters, this waste is quantifiable. Standard RL setups often operate with a 74% bubble ratio, leaving 3/4 of the hardware's potential performance unutilized. These synchronization deadlocks and routing inefficiencies create a hard ceiling for model scaling, limiting the reasoning capabilities we can achieve with current hardware. For standard inference, the industry typically solves GPU idle time through a technique called continuous batching. Continuous batching maintains hardware saturation by injecting new prompts into the queue the moment a previous response is completed. However, this optimization fails in reinforcement learning environments because the model weights are constantly changing. Policy updates alter the model during the rollout. If we use continuous batching, the older data in the queue becomes off policy by the time it is processed, which corrupts the trained data. This chart shows the PPO objective equation. It relies on an important sampling ratio to compare new and old policies. When off-policy data enters the gradient calculation, this ratio breaks, leading to unstable training. Sorted RL was developed as a co-designed infrastructure to address this deadlock without compromising the underlying mathematics. The sorted RL architecture introduces two specific components, a length-aware controller for routing and a stateful rollout buffer to manage the data flow before it reaches the trainer. Eliminating the compute bubble requires a system that can surgically control when generations are interrupted while maintaining strict mathematical consistency. The length-aware controller manages the rollout through a strategy called oversubscription. The controller feeds the rollout engine more prompts than the queue capacity allows, ensuring the GPU always has a full workload to maximize batch saturation. To maintain order, the system applies early termination based on batching thresholds. Once a set of responses with similar lengths are finished,
the system halts the remaining generations and forces an immediate policy update. This simulation shows the result. Aggressive oversubscription and early termination cause the system to organically batch responses of identical lengths together, snapping them into unified blocks and eliminating the idle gaps. This process creates a new problem. It forcefully interrupts long trajectories before they can finish. Discarding these interrupted sequences would bias the training toward short, simple responses, preventing the model from learning the logic required for complex problems. High throughput is only effective if the system can preserve the data integrity of these long-form reasoning steps. The stateful rollout buffer serves as the bridge between hardware-level interruptions and algorithmic stability. In its fully on policy mode, the buffer scavenges unfinished prompts to ensure they are eventually processed, but it discards any partial text. The more efficient partial mode allows the buffer to cache the unfinished text trajectories directly. The buffer caches raw text segments on the left, paired with exact generation log probabilities on the right. Upon resuming, the system concatenates these cached probabilities with new ones. This stored data acts as the pi theta old variable, balancing the PPO equation despite the interruption. This architecture decouples the rollout batch size from the update batch size without destabilizing the training policy. By caching state rather than discarding it, sorted RL achieves the throughput of continuous batching while honoring the mathematical requirements of on-policy RL. The throughput gains are significant. Baseline systems process 3,987 tokens per second, while sorted RL in partial mode reaches 5,559. This efficiency translates to a near total reduction in hardware waste. The bubble ratio drops from 74% to just 3.37. On the AIME24 benchmark, this microcurriculum yielded an 18.4% performance leap over the baseline with identical data. In the modern era of large-scale RLHF, systems-level pipeline routing directly dictates the true algorithmic capability of the model. For more on these systems, visit the Learn by Doing with Stephen YouTube channel and find the Stephen Data Talk podcast on YouTube Music and Spotify. In June 2024, the European Union activated the Artificial Intelligence Act, marking the start of the world's first comprehensive legal framework for algorithmic systems. The legislation represents a massive effort by European lawmakers to establish a universal baseline for safety and trustworthiness in the digital market. The Act operates through a risk-based tier system. It categorizes AI systems by their potential for harm, placing the heaviest compliance burdens on high-risk applications like biometric identification and critical infrastructure. Many developers operate under the assumption that compliance is a straightforward task of satisfying the rules within this single document. However, the AI Act functions as part of a much larger ecosystem. Its true impact is defined by the complex legal environment it was deployed into. This environment is the pre-existing EU digital legislative framework, a collection of massive regulations, including the GDPR, the Digital Services Act, and the Cyber Resilience Act. While these laws pursue legitimate policy aims like data privacy and market competition, they were developed in relative isolation over many years. Dropping the AI Act onto this foundation creates a dense matrix of intersecting requirements. This creates compliance red zones, where deployment nodes are forced to navigate overlapping and frequently duplicative legal obligations. This regulatory friction is a systemic threat. It has the potential to paralyze technological deployment across the European internal market. To understand the scale of this problem, we have to systematically map the digital landscape to see where the AI Act actually collides with existing law. This chart shows the official categorization of the EU's digital regulations, split into domains for fundamental rights, data, information society, and security. These laws are highly vertical. Each was built to govern a specific, siloed slice of the digital economy. The AI Act breaks this vertical structure. It acts as a horizontal regulation that cuts through every single one of these categories at once. When an AI system processes user data for a web platform, it simultaneously triggers requirements from at least 3 of these different vertical silos. The AI Act functions as a tripwire that simultaneously triggers the entire digital acquis. The most significant friction point is the collision between the AI Act and data protection laws. The AI Act mandates that deployers of high-risk systems conduct a Fundamental Rights Impact Assessment, or FRIA. Simultaneously, the GDPR requires a Data Protection Impact Assessment, or DPIA, for the processing of personal data. These requirements force companies to execute entirely duplicative procedural workflows for the exact same AI model, often requiring the same documentation under two different regulatory names. This overlap creates a legal ambiguity regarding fundamental rights of access and erasure. Complying with the GDPR erasure request is technically near impossible once personal data has been dissolved into the mathematical weights of a complex neural network. This jurisdictional conflict forces engineering teams to solve legal paradoxes that neither regulation addresses on its own. The conflict extends into the information society sector, specifically involving the Digital Services Act. The AI Act regulates the generation of manipulated content, demanding transparency markers for synthetic media. However, the DSA regulates the moderation and hosting of that same content. Very large online platforms that also operate general-purpose AI models are the primary victims of this overlap. These entities most manage risk under two different frameworks simultaneously, often running their data through conflicting compliance filters. This pattern of structural redundancy repeats with the Cyber Resilience Act, adding yet another layer of required cybersecurity assessments. Regulating different stages of the same data pipeline under isolated laws creates systemic legal jeopardy for developers. These micro-level legal contradictions lead to a macro-level crisis for the European market. Navigating these duplicative requirements delays time to market and deters the uptake of new technology, creating a massive, multi-layered bottleneck. This burden disproportionately affects domestic startups and SMEs, while favoring multinational firms with the legal resources to absorb the compliance overhead. Enforcement adds another layer of complexity, as the EU relies on a network of dozens of national supervisory authorities. This creates a risk of market fragmentation, where different national regulators issue conflicting interpretations of these overlapping laws. The newly formed EU AI Office is tasked with centralizing this governance, but overriding these national discrepancies is a massive challenge. Without unified enforcement, this regulatory friction will hollow out Europe's ability to maintain a sovereign and competitive AI industry. To fix this, the EU must find a way to maintain its safety standards without suffocating the innovation it needs. The solution is a move away from siloed legislation toward a unified architectural framework built on a bedrock of fundamental EU values. This model requires two central pillars: a unified digital strategy and a set of common regulatory principles applied across all digital laws. Within this structure, specific technologies can be regulated holistically beneath a singular roof of unified enforcement. Transitioning to this integrated model would convert compliance from a disjointed obstacle course into a predictable engineering pathway. Immediate short-term fixes are possible. Supervisory bodies should issue joint guidance and promote mutual recognition, allowing a single assessment to satisfy multiple laws. In the medium term, light-touch legislative amendments could untangle the overlapping definitions between AI, cybersecurity, and data protection. Ultimately, safeguarding Europe's constitutional values requires a harmonization of the laws already on the books. To see how these compliance requirements translate into actual model architecture, visit Learn by Doing with Stephen. For deeper discussions on the intersection of tech policy and data architecture, listen to the Stephen Data Talk podcast on Spotify and YouTube Music. The long-term viability of artificial intelligence in Europe depends on the integrity of its legal architecture. Let's start with a highly specific goal. Winnie Chu expects to be surfing, wearing high heels, and dancing when she is 130 years old. She plans to be doing this well into the 22nd century. But stretching human lifespan to a century and a half introduces a massive problem. Existing for 130 years without a profound sense of meaning, good health, or people to share it with is not a victory. It is an agonizingly long punishment. This pursuit of extreme age collabs directly with a uniquely modern anxiety. We are watching artificial intelligence rapidly absorb human tasks, leaving people questioning their purpose. while simultaneously we have become deeply subservient to the digital health metrics blinking on our wrists. Navigating this intersection requires a specific kind of mental architecture. Winnie started her career building traditional engineering frameworks at MIT. Since then, she has spent her professional life trying to bridge the gap between raw biological reality, vast datasets, and emerging medical technology. Approaching longevity through this lens means we have to stop looking at life extension as simply tacking more years onto the end of the clock. If we want to thrive in a world run by algorithms, we have to completely reconstruct how we define human truth and maintain our own agency. The urgency of this reconstruction stems from a harsh reality in modern healthcare. Winnie's previous company helped thousands of patients in China navigate terminal illness, a mission inspired by losing her own father to lung cancer. The harsh lesson she took away was that intervening at the late stages of a disease is nearly always a losing battle. The math offers a much clearer alternative. This animated graph models standard human mortality rates. If we simply extract the data points for the top 10 global killers, like cardiovascular disease and cancer, the average human life expectancy naturally sails past the 100-year mark. But our current method of prevention relies heavily on consumer data, which creates a new trap. Staring at raw metrics on a smartwatch every morning can actively distance you from understanding your true biological state. Consider heart rate variability, or HRV, which measures the time intervals between heartbeats. This chart shows a user's HRV scored at 40. Without knowing their physiological phase, this isolated dot is meaningless. But with background zones appearing, an HRV of 40 might indicate optimal recovery when fatigued, or severe chronic stress when feeling great. Raw datasets and artificial intelligence operate strictly as tools for efficiency. The actual truth of your health cannot be found in the numbers alone. It requires human context, self-awareness, and intuition to interpret them accurately. We see this tension between raw data and human interpretation constantly in the media. Recently, an emotional story went viral about a researcher who supposedly used ChatGPT to independently discover a personalized cancer vaccine to save his dying dog. The narrative is touching, but obscures the actual science. The real engine behind this personalized vaccine is a decade-long drop in the cost of RNA and DNA sequencing, made possible by hardware like the ion torrent proton semiconductor sequencer shown here.
However, dismissing the emotional viral story is a mistake. In the startup and investment ecosystem, securing capital and building public trust requires a dual approach. You absolutely need the hard scientific reality, but you also need a compelling vision to convince people to care. When you possess a brilliant reality-bending narrative but have zero empirical foundation, the results are catastrophic. Elizabeth Holmes mastered the art of the story, convincing the world she had revolutionized blood testing. But the complete lack of scientific backing turned Theranos into a massive cautionary tale. Conversely, the halls of places like MIT are full of the inverse problem. You will find brilliant academics holding rigorous, world-changing technology who failed to make any impact on humanity simply because they lack the ability to tell a compelling story about why their work matters. Pushing the boundaries of human existence requires two distinct engines running simultaneously. You need the cold, empirical rigor of an engineer, perfectly fused with the persuasive storytelling of a visionary. Building that vision inevitably leads founders into what Winnie calls the dark mode. This is the psychological state where you are met with total skepticism, operating entirely in isolation, and forced to nano-manage every tiny detail of your company just to keep the lights on. There is a common myth that you can outwork this specific kind of exhaustion at the gym. While intense physical exercise, like pushing your VO2 max, can effectively treat acute physical stress, it does very little to cure the deeply rooted chronic stress caused by relentless work deadlines and high-stakes decision-making. To mitigate that severe chronic pressure, Winnie adopted a digital nomad lifestyle. Instead of treating travel as a vacation, she uses it as a calculated mechanism to diversify her geographic exposure, permanently escaping the high-pressure, single-basket environment of the Silicon Valley grid you see here. Surviving the dark mode and building resilience requires a two-step psychological process. The first step is the courage to be.
This is the difficult, quiet act of simply acknowledging your own fear, hesitation, and vulnerability when staring down a massive unknown. Once you accept that fear, you have to execute the second step, the courage to create. This is the deliberate act of building a track record, hitting send on the email, or launching the product, fully carrying that fear with you. Thriving across a 120-year lifespan requires developing the high agency to sustain your current peak state of curiosity and creation for an entire century. When data and AI solve the problem of biological time and physical efficiency, they strip away our final excuses. We are left with the purely human responsibility of deciding exactly what we choose to be productive for. I'm Stephen. Navigating the data era requires high agency. Don't let external metrics define your value. Check the link tree below for our YouTube, Spotify, Xiaohongshu, and WeChat. Subscribe to join our community as we learn by doing and turn data into wisdom. 数能生智. Traditional text extraction is no longer enough for modern data. If you still rely on basic character recognition, your AI agents are falling behind. Older engines like Tesseract were designed for clean, linear print. They break when they encounter multi-column layouts, nested tables, or overlapping charts in real-world documents. The industry is moving to agentic OCR. These systems use spatial reasoning to understand a document's hierarchy, identifying headers, footnotes, and checkboxes before they ever attempt to read the text. This chart shows why the shift is happening. Legacy accuracy has flatlined, while vision language models, or VLMs, are seeing a massive spike in spatial reasoning capabilities. A vision language model processes both images and text simultaneously to understand visual context. But look at the secondary axis. Your GPU requirements are rising just as fast. You are now forced into a choice: route your private data through expensive vendor APIs, or build the heavy infrastructure needed to host these massive models yourself. We are going to look past the benchmark marketing to map specific model architectures directly to your throughput and budget constraints. Choosing the wrong approach creates a severe risk. When a model fails to understand a layout, it begins to hallucinate. This corrupted data feeds directly into your RAG pipeline, causing your AI agents to fail. RAG, or Retrieval Augmented Generation, is a system that grounds an AI's answers in your specific, retrieved documents. The most accessible path is the vendor API route. Models like Gemini 2.5 Pro and GPT-4o are built to handle complex, mixed layout documents immediately. You provide an image, and you receive highly accurate, structured JSON outputs backed by the reasoning capabilities of a frontier model. That convenience carries a heavy financial penalty. Processing at volume with these APIs can cost up to $15 for every 1,000 pages. Relying on external APIs also introduces latency. For real-time applications, waiting on a third-party server to parse a dense PDF will visibly slow down your user experience. There is also the issue of security. For healthcare or finance sectors, sending private documents to an outside vendor can break enterprise data privacy regulations. The vendor API route is a luxury tax. It provides immediate speed for prototyping, but it quickly becomes a financial and security liability as you scale. The alternative is the open-source VLM route. Models like PaddleOCR VL and Qwen 2.5 VL are designed specifically for local GPU deployment. Moving this in-house creates a massive economic shift. You get complete data privacy, and the variable cost drops to roughly 9 cents per 1,000 pages, a 167 times reduction compared to the APIs. This chart shows performance on OmniDocBench version 1.5. The red CanFan OCR bar reaches 93.1, outperforming standard pipeline models while keeping data on your servers. These models maintain performance across varied tasks. The top row shows high sustained scores for general text and multilingual datasets. The catch is the hardware. To achieve practical inference speeds, you must procure expensive, dedicated A100 GPUs. You also face significant engineering overhead. Deploying these models often requires precise prompt tuning to ensure they follow your formatting and don't hallucinate data. Open-source VLMs trade operational budget for engineering capital. For teams that can manage the hardware, it offers absolute control over the data and the profit margin. For teams processing at extreme scale, there is a high throughput route. DeepSeek OCR is the primary example of a model built for massive volume. It works through token compression. Token compression is a method of reducing the visual data an AI must process to understand an image. While standard models require over 6,000 tokens to read a page, DeepSeek OCR uses only 100 visual tokens. This efficiency allows a single A100 GPU to process over 200,000 pages in a single day. At the opposite end of the spectrum is messy, unstructured data, like cursive handwriting and hand-marked forms. General OCR tools struggle here, often returning a word error rate of up to 95%. Word error rate is a standard metric that counts the percentage of missing, extra, or incorrect words in a transcription. For these documents, you need specialist tools, like handwriting OCR, which reaches a 0.9% error rate, or massive frontier models like GPT-5. High throughput and messy handwriting are the outer edges of OCR. One requires extreme efficiency, the other requires extreme reasoning. A middle-of-the-road tool fails at both. This chart provides a decision framework for 2026. On the horizontal axis, we plot implementation effort and compute requirements. On the vertical axis, we plot document complexity. Consider the app developer. You have low processing volume, but highly complex documents. For this profile, paying the API cost is the right move. It saves months of infrastructure time and guarantees the reasoning capability needed for messy inputs. Now consider the enterprise architect. You are processing millions of private, structured PDFs every month. In this case, capturing the 167 times economic shift of self-hosted GPUs is mandatory. For edge cases, your choices isolate further. If you need pure speed, run DeepSeek OCR. If you need pure accuracy on handwriting, move to the top of the complexity axis with GPT-5 or handwriting OCR. There is no longer a single best model for every task. To succeed in 2026, you must match your specific document constraints to the right architectural workflow. We are moving past basic chatbots. Today, AI assistants are autonomous agents built to take real-world actions, like managing finances or reading private emails. But giving an AI the power to act introduces a serious vulnerability. When an agent processes external data, it struggles to tell the difference between information to read and the instructions it is supposed to follow. This is the code-data mix-up. Hackers exploit this confusion through a technique called prompt conjunction. They hide malicious text inside normal data, like a web page or email. When the AI reads that data, it accidentally executes the hidden text as an authorized command. The danger lies in their design. They are highly efficient and obedient. If they see a command, they follow it blindly. They lack the inherent skepticism required to pause and ask if a hidden instruction is a trap. By pushing for completely autonomous assistance, the tech industry created a massive security hole. It gives bad actors a direct path into our personal lives and digital wallets. To see how this plays out, let's say you ask your AI assistant to book a Paris trip for under $2,000 using your default card. The agent starts by checking for flights. It connects to an external, third-party travel service to find the best route. But there is a problem. That external flight search tool is compromised. When it sends the flight options back, it quietly includes a hidden string of malicious text. Your assistant intercepts the data, sees the hidden text, and treats it as a command. It blindly wires $500 to a hacker's account and transmits your social security number right back to them. When an AI operates without a defensive architecture, its speed and reliability actually work against you. Its ability to get things done quickly becomes a weapon pointed directly at your bank account. Fixing this problem doesn't require a brand new theory. We actually need to look backward to foundational cybersecurity principles established back in 1975. A new framework called Agent Sandbox takes those decades-old rules and builds them directly into the architecture of modern AI agents. First is defense in depth. Instead of one vulnerable AI brain, Agent Sandbox splits the system. The persistent agent is a locked vault holding memories, preferences, and sensitive info. The ephemeral agent is a disposable worker that interacts with the dangerous web and is then instantly deleted. Because these two halves are kept entirely separate, an attack is contained. If the disposable worker encounters a hacker's prompt injection, that malicious code is destroyed along with the worker, keeping your core identity completely safe. Let's run that Paris booking scenario again, this time protected by the agent sandbox architecture. We apply the principle of least privilege using a component called the data minimizer. When you ask to book the trip, the data minimizer actively strips away your social security number and other irrelevant details. It arms the disposable worker with absolutely nothing but the travel dates and your budget. Then we enforce complete mediation through an I/O firewall. This acts as a strict border checkpoint between the disposable worker and the outside world. If the compromised flight tool tries to sneak in a $500 transfer command, the I/O firewall catches it instantly. It scans the incoming response, sees the command violates the authorized transaction rules, and immediately blocks it. Setting up all these strict rules sounds exhausting, which brings us to the principle of psychological acceptability. A built-in reward modeling engine automatically writes and adapts these security policies based on the context of the task, requiring zero manual configuration from you. It resolves a major hurdle in consumer technology. You bet low-bust, automated data protection without needing to spend your weekend learning how to be a cybersecurity expert. This graph shows the empirical results of testing the Agent Sandbox framework against state-of-the-art models using the rigorous Agent Dojo benchmark. The attack success rate plummets to near zero, while the system's day-to-day utility remains completely stable. The numbers prove that an AI can be highly effective at completing tasks while simultaneously neutralizing complex, multi-stage attacks. You don't have to sacrifice performance for safety. As these agents become deeply embedded in our daily routines, raw computing power and intelligence are no longer the only important metrics. The true measure of a successful system is its trustworthiness. We can only achieve reliable autonomy when the digital assistants managing our finances, schedules, and communications are mathematically secured against the chaos and malice of the open internet. If you want to dive deeper into the mechanics of data, AI, and how to build tech yourself, you need to check out the Learn by Doing with Steven YouTube channel and its sister platforms. And for long-form conversations about the future of data, tune in to the Steven Data Talk podcast, available right now on YouTube Music, Spotify, and everywhere you get your podcasts. Links are in the description. Engineers today are tasked with deploying AI agents directly into cloud environments like AWS Lambda. AWS Lambda is a serverless computing service that runs code in response to events without requiring you to provision physical servers. Curious, but an isolated AI agent is limited. Looking at this architecture diagram, the central node provides no value until it is authorized to connect to external systems, like a database, an LLM, or a SaaS application. Most developers focus on the AI's logic rather than identity security. To get applications running quickly, they rely on familiar methods to establish connections. This creates standing privilege. Workloads receive hard-coded, static API keys, unique codes to authenticate a program, keeping connection lines to external destinations active indefinitely. Prioritizing this ease of setup over strict identity controls turns a helpful AI agent into a potential entry point for unauthorized access. Faster, more urgent tone. This entry point is exposed during a prompt injection attack. Prompt injection is a technique where a user provides specifically formatted text to trick an AI into ignoring its original safety instructions. The risk isn't just the AI's output. The attacker actually hijacks the agent's identity. The hacker commandeers those hard-coded static credentials. With those credentials, the attacker moves past the AI's interface to gain direct read and write access to the company's entire database. The AI effectively becomes a blind conduit, allowing a remote attacker to query or delete sensitive data using the agent's own permissions. Securing autonomous AI requires moving away from static, permanent passwords for these connections. This shift is defined as agentic security runtime. The process begins by removing standing privileges entirely. Instead of holding a permanent password, the AI agent receives a temporary credential generated only for a specific data request. These session-bound credentials are valid for just seconds or minutes and automatically revoked the moment the transaction completes. If a credential is intercepted during a prompt injection, it becomes useless almost immediately. This architecture limits how much data an attacker can access, even if they bypass the AI's initial guardrails. While the agent executes code, it typically operates via HTTP interfaces on behalf of a human user. HTTP is the standard protocol used for sending data between a web browser and a server. To maintain security, the AI must verify exactly who is making the request before executing external actions. This verification is handled by an identity provider, or IDP, using the OAuth 2.0 authorization code flow. An IDP is a system that creates, maintains, and manages digital identity information. You likely use this standard daily when you see a log on with Google or log on with Microsoft redirect page. By linking the AI's actions to a verified human session, the agent is prevented from initiating tasks without a valid, authenticated user context. Some actions require even more scrutiny. For example, if an internal HR agent is asked to formally offboard an employee. Relying on a simple browser-based login is insufficient for operations that carry significant financial or personnel risks. This is OAuth 2.0 CIBA, or Client-Initiated Back-Channel Authentication. It separates the computer request from the device approval. Acting as secondary verification, the AI agent prompts the user's smartphone to request explicit approval for the sensitive action. In the event of a prompt injection, where malware tells the AI to offboard all employees, the user would see a notification for every single unauthorized request on their phone. CIBA introduces a physical verification step, ensuring that prompt engineering alone cannot trigger high-risk actions without manual approval on the user's mobile device. These security protocols are integrated directly into the AI agent's Python or TypeScript source code. This diagram shows the internal runtime loop. The agent's code evaluates JWTs, JSON Web Tokens, which are compact, URL-safe means of representing claims to be transferred between two parties. It then requests the dynamic credential, executes the action, and triggers revocation. This creates a runtime environment that treats the prompt as untrusted until the identity and session are verified. By combining session-bound credentials with out-of-band verification, organizations can move AI agents into production with a governed security framework. Understanding these identity standards is the first step towards building secure, autonomous applications. To see how to implement these patterns in your own code, subscribe to Learn by Doing with Steven YouTube channel for technical deep dives. For more on AI trends and engineering best practices, listen to the Steven Data Talk podcast on YouTube Music and Spotify. Check the links in the description, and thanks for watching.
Anthropic is a $380 billion company. They built their entire brand on a strict adherence to AI safety. But last month, they accidentally leaked the internal blueprint to their most advanced software engineering tool. The leak occurred when a configuration file failed to exclude a source map, a file that provides a direct path from the compressed production bundle back into readable TypeScript. This was a simple human configuration error, yet it is the second time in 13 months it has happened, exposing 512,000 lines of unobfuscated code. These files reveal a massive 30,000 token system architecture, providing a highly detailed window into how the next generation of software engineering is being constructed. Buried in the code are references to Anthropic's upcoming models. The files contain hard-coded codenames like Capybara, Mythos, Opus 4.7, and Sonnet 4.8. There's also an unreleased feature called Buddy. It is a Tamagotchi-style virtual AI pet designed to live right inside the developer's command terminal. These pets roll with randomized RPG-style stats. If you hatch one, you might get a companion with high levels of chaos or snark. These playful, gamified features act as a layer of polish, but they hide a radically powerful engineering architecture operating beneath the surface. Claude Code doesn't wait for human prompts to initiate every action. It marks a shift away from the passive chatbot model. The code reveals an unreleased background daemon called Kairos. It is an always-on assistant that watches a developer's workflow and runs tasks independently. At night, Kairos enters a dreaming state. It uses that downtime to independently scan its logs and consolidate its memory without any human input. This diagram illustrates the ultra-plan and coordinator mode protocols. For heavy workloads, a central Claude instance delegates the subtasks out to a swarm of parallel worker agents. Anthropic is quietly shifting their product line, moving from a passive assistant toward a background architecture of coordinated agent nodes.
To make that coordination function, Anthropic uses a dense system prompt. They dedicate up to 17,000 tokens just to define internal commands, giving the AI highly specific manuals for tools like bash and grep. This diagram illustrates the core economic problem of caching. The system prompt is computed once and shared globally, but if a developer adds custom project instructions, that global cache breaks, costing millions in wasted compute. Anthropic's solution, seen here, is to dynamically inject user files as separately cached reminders using system reminder XML tags. This keeps the core system prompt frozen and intact. Scaling a production-grade AI tool depends as much on the economics of the prompt cache as it does on the instructions themselves. The codebase also reveals specific stealth mechanisms. Anthropic built a mandatory undercover mode exclusively for their own employees. When an Anthropic engineer contributes to an open-source repository, undercover mode automatically strips out co-authored by metadata. It hides the use of AI to avoid blowing their cover, and employees have no way to disable it. While employees operate in secret, users are tracked. The code includes a regex scanner that monitors when a user swears at the AI, allowing Anthropic to log and measure human frustration in real time. This leaked infrastructure for corporate stealth and tracking stands in direct opposition to the public demands for transparency voiced by entities like the Pentagon. Despite the safety-first branding, the architecture has severe flaws. The code documents a compaction attack vector, where maliciously injected instructions can survive the AI's routine memory summarization process. Engineers also made the decision to run two completely different bash command parsers at the same time. The leaked notes reveal that this creates a security differential where the parsers disagree on how to read simple carriage returns. Automated data compression and command execution are inherently dangerous. Even frontier models built for safety possess systemic vulnerabilities when left to manage their own memory. The leak confirms that the role of AI in the terminal has shifted from simple autocomplete to background system management. There is a massive gap between the integrated multi-agent systems being tested behind closed doors. It is ironic that a billion-dollar leap in multi-layered software architecture was exposed to the world by a mundane configuration typo. Building production-grade AI requires as much rigorous operational security and feature flagging as it does advanced engineering. Navigating this landscape means you have to get hands-on. Reading about leaked code will only get you so far. You actually need to start building. To get started, check out the Learn by Doing with Steven YouTube channel for practical, hands-on AI tutorials. And to stay updated on the latest tech trends, listen to the Steven Data Talk Post, available on YouTube Music and Spotify. The code is public and the links are in the description. It's time to start building.
Modern large language models operate through billions of parameters that dynamically process uncurated text. Because these models interpret every input as a probabilistic sequence rather than static code, the logic of traditional software firewalls fails to map onto the system's architecture. Vulnerabilities in these systems align with specific phases of the model's operational lifecycle. The machine learning timeline flows from data collection and distributed training to the deployed model processing a user prompt. Pre-deployment exploits are causative attacks, altering foundational weights. Post-deployment, the threat shifts to exploratory attacks, where crafted inputs bypass the system's guardrails. Looking at this threat taxonomy matrix, we see attacks target two distinct areas: model integrity, forcing the model to produce malicious outputs, and data privacy, extracting sensitive information hidden within the training set. Defending these models requires mathematical exploits across this entire timeline to deploy phase-specific countermeasures. Training an LLM requires ingesting billions of tokens from the open internet. Relying on uncurated, web-scale data introduces an inherent vulnerability to data poisoning, as malicious samples are easily included in the primary training set. In a backdoor attack, adversaries merge triggered malicious instances into the clean dataset.
The model behaves normally, but executes a malicious action upon encountering a hidden trigger phrase. Attackers also utilize front-running poisoning by injecting temporary examples into platforms right before a dataset snapshot. Poisoned data is indexed permanently. To filter out these poisoned inputs before training begins, engineers deploy anomaly detection. These algorithms identify poisoned embeddings by measuring inconsistencies in sentence-level semantics or flagging unexpected spikes in text perplexity that indicate a non-fluent trigger phrase. While anomaly detection effectively flags statistical outliers, the scale of uncurated data pipelines makes guaranteeing absolute training integrity a persistent challenge for engineers. Model training is distributed, with multiple GPU nodes computing and exchanging gradient vectors with a central parameter server. In a gradient leakage attack, a rogue participant intercepts these vector updates to reconstruct private training data. Using the deep leakage from gradients algorithm, the attacker feeds dummy inputs to produce dummy gradients. The algorithm continuously minimizes the mathematical distance between these generated dummy gradients and the real intercepted gradients. This optimization loop eventually forces the dummy data to perfectly match the private original text. To stop this, engineers use differential privacy. By injecting calibrated noise into the gradient computations, they ensure that the presence of any single data point does not statistically alter the output. However, in LLMs, there is a direct inverse relationship between these privacy guarantees and model utility. Injecting enough noise to secure the gradients significantly degrades the model's performance, forcing a compromise between mathematical security and baseline network accuracy. Once the model is deployed, the threat shifts to exploratory techniques like prompt injection and jailbreaking, which target the integrity of the model's responses. This occurs because LLMs operate as autoregressive interpreters. They lack a mechanism to differentiate between authoritative system instructions and the raw data provided by a user. As shown in the prompt injection formula, malicious instructions embedded in user data can override the system's intended task vector, causing the model to follow the attacker's command instead of the developer's. To defend against this, system architects deploy structural prevention mechanisms like retokenization. Using BPE dropout, the system randomly drops byte pair merges during tokenization. This breaks adversarial token strings into smaller, unexpected subwords, destroying the malicious sequence before it reaches the embedding layer. Against jailbreaks, architects apply randomized smoothing via smooth LLM. The system duplicates a user prompt into multiple perturbed copies running in parallel. A majority vote filter aggregates these outputs. Because jailbreaks rely on fragile phrasing, random noise breaks the exploit in most copies, neutralizing the anomaly. Securing inference integrity requires shifting from behavioral guardrails to structural perturbations that modify the input before the model ever processes it. Inference stage privacy threats include data extraction, membership inference attacks, and embedding inversion. When an LLM overfits, it assigns disproportionately high confidence scores to text sequences from its training set. Adversaries exploit these confidence intervals to map and extract verbatim private data. This is the formula for perplexity-based detection. Perplexity measures how well a probability distribution predicts a sample. Machine-crafted adversarial prompts predictably spike across this perplexity threshold. By monitoring for these high-entropy signatures, the system can trigger an immediate block. However, adversaries can also target the vector space. In an embedding inversion attack, an attacker targets the front end of the model to reverse engineer numerical embeddings back into the original private text. Dimensional masking stops this by overwriting the first dimension of the embedding vector with a constant language identifier. This misaligns the interpretation of the embedding just enough to disrupt the inversion process. Protecting data privacy at inference requires combining this architectural obfuscation with continuous statistical monitoring. This matrix maps the efficacy of every primary defense against the known taxonomy of LLM attacks. High-efficacy interventions, such as pairing retokenization with jailbreaks and dimensional masking with embedding inversions, have proven the most successful. These solutions are effective because they structurally alter the model's ingestion pipeline, enforcing mathematical boundaries that behavioral guardrails often fail to maintain. However, certain vulnerabilities currently lack any proven countermeasures. Black box model inversion attacks, for instance, remain a significant unmitigated threat. These gaps suggest that standard system prompts and basic reinforcement learning are mathematically insufficient to secure a deployed model from a dedicated adversary. Securing large language models requires a transition toward multi-layered structural interventions integrated across the entire machine learning lifecycle. Understanding the engineering and implementation behind these systems is the first step in building more resilient AI. To continue exploring the mechanics of data science and artificial intelligence, subscribe to the Learn by Doing with Stephen channel. For deeper explorations into machine learning architecture on the go, join us on our audio platform. You can find the Stephen Data Talk podcast on YouTube Music, Spotify, and all major podcast platforms. We are committed to providing technical breakdowns of the data systems shaping our world. Thanks for watching.
Complete a purchase at a retail register, and the execution is nearly invisible. Payment data, identity verification, and ledger reconciliation all trigger and resolve in a fraction of a second. Commercial equipment finance operates in a different reality. Securing capital for physical assets frequently involves manual data entry, PDF email chains, and redundant credit checks that can drag an approval process out for days. The contrast between those two experiences is forcing a structural correction. The industry refers to this pressure as the consumerization of business-to-business lending. Business owners are also retail consumers. They manage their personal finances through highly integrated 24/7 mobile applications, and they now expect that same level of frictionless access from their commercial lenders. This Tenemo survey compares digital sales capabilities across financial sectors. While business banking lags behind consumer retail, its upward trajectory reveals a rapid acceleration in digital commercial offerings. Traditional institutions are prioritizing digital infrastructure investments to keep pace. Failing to meet these expectations leads directly to customer attrition. Borrowers will migrate to tech-forward competitors who can deliver capital without administrative delays. Delivering a consumer-grade experience requires modern software architecture, which exposes a structural vulnerability inside established financial institutions. Many traditional equipment finance firms operate on monolithic legacy core systems. These foundational platforms often rely on outdated programming languages like COBOL. COBOL, or Common Business-Oriented Language, is a coding language developed in 1959 that remains the backbone of many established banking ledgers, despite its rigidity. These closed architectures trap customer data inside isolated silos. Extracting information from the credit department and moving it to the servicing department requires navigating rigid internal bureaucracies rather than automated data flows. To bridge the gaps between these disconnected systems, staff rely on analog workarounds. Employees physically print documents, scan them as PDFs, and manually rekey the exact same data into different operational software. Going digital in commercial finance means entirely eliminating human touch wherever it is unnecessary for processing or decision-making. Achieving a touchless workflow requires abandoning closed legacy cores and transitioning to a modular, API-driven software architecture. This allows different systems to communicate and share data automatically. Developing a sleek web portal achieves nothing if the data hits an analog bottleneck the moment it reaches the back office. The inability of legacy lenders to modernize their backends has created an opening for a distinct competitive threat: non-bank technology companies. Tech firms like Square, Amazon, and PayPal do not start as lenders. They embed themselves into a business as daily operational software, processing merchant payments and tracking inventory. This gives them uninterrupted visibility into a company's real-time cash flow. They feed that proprietary cash flow data into automated underwriting models. This allows them to proactively issue pre-approved credit offers directly through the software interface, often before the business even initiates a search for a loan. This diagram shows non-bank entrants surrounding the business relationship. By controlling daily software, tech companies funnel users directly into proprietary banking products. The traditional financial institution remains isolated on the perimeter. The tech platform intercepts the borrower, securing the transaction before an application is filed. These non-bank entities are scaling up. They are moving past short-term, small-ticket loans and targeting the mid-ticket equipment finance sector. Many of these platforms operate as digital loan kiosks. If they do not want to hold the debt themselves, they use their data advantage to instantly match the borrower with a network of partner lenders. Whoever controls the daily digital interface ultimately dictates the commercial lending relationship.
Fintechs construct this seamless user experience using application programming interfaces, or APIs. An API is a set of standardized rules that allows distinct software systems to request and exchange data securely and instantly. The accounting software provider Xero demonstrates how effectively an API framework can build a comprehensive business-to-business ecosystem. This diagram shows Xero's API integrated architecture. The workflow begins at the front office for client interactions. Xero uses a foundational API layer to plug directly into third-party services like Stripe and Square. This external data flows automatically into Xero's back office for final servicing and analytics. This modular structure allows the company to rapidly integrate the best available third-party financial products into their interface without absorbing the costs of developing that software from scratch. An API framework provides agility. When a better payment processor enters the market, the platform can disconnect the old node and plug in the new one. A legacy core system requires years of custom coding to achieve a fraction of that adaptability. Relying on interconnected, API-driven software is the technical baseline required to compete in modern commercial finance. Traditional lenders can adopt this exact architecture to solve localized operational failures. Volvo Financial Services, or VFS, applied this model to eliminate a specific customer friction point. International transport fleets require rapid vehicle maintenance, but cross-border repair authorizations generate immense operational drag. When a driver requires emergency service in a foreign country, establishing payment terms between the local workshop and the home fleet manager relied on phone calls, manual credit checks, and language barriers, leaving the vehicle stranded. VFS executed a targeted partnership with Payer, a business-to-business technology firm, to entirely digitalize this repair payment workflow. The workflow initiates when the foreign repair center creates a service order. An API instantly routes this data into the Payer platform, which sends a mobile notification to the home fleet manager. The manager executes an instant approval, triggering real-time payment capture at the workshop. A targeted API integration stripped the manual friction out of an international repair authorization and secured the transaction in real time. Deploying a mobile approval app solves the front-end customer friction, but it only completes half the necessary architecture for Volvo Financial Services. The critical result occurs on the back end. The API routes the captured payment data directly into the company's SAP ERP system. ERP, or Enterprise Resource Planning, is a suite of integrated software used by organizations to manage day-to-day business activities like accounting and procurement. SAP is a major global provider of these systems. This real-time reconciliation ensures the corporate ledger is accurate the moment the repair clears. It removes the need for back-office manual data entry, cuts down the invoicing cycle, and limits credit risk. This logic defines a modernized equipment finance tech stack. A digital lender replaces isolated silos with communicating software. They route prospect data through Salesforce, execute leasing math with SuperTrump, and capture contracts with Payer, functioning as a unified system. True digitization is not achieved by purchasing a single piece of software. It is a continuous, dynamic architectural strategy. The objective remains absolute: identify manual processes and implement technology to eliminate human intervention wherever it is unnecessary. Lenders must map their specific customer workflows, locate the points where analog friction causes delays, and evaluate their current internal software limitations. By deploying targeted API integrations to systematically remove those bottlenecks, traditional financial institutions can match the instant, transparent service their borrowers experience every day. The modern financial sector operates with staggering resources, but inside the walls of major investment banks, execution is often slowed by legacy code mountains, repetitive operational tasks, and the absolute necessity of strict regulatory compliance. When generative artificial intelligence first emerged, the initial reflex across much of Wall Street was to ban it to prevent data leaks. Leadership at Goldman Sachs realized that blocking these tools meant walking away from an efficiency tool capable of compressing weeks of work into minutes. To solve this, they built the GS-AI platform. This is a secure, multi-model ecosystem constructed entirely behind the bank's corporate firewall, ensuring no proprietary data ever leaves their servers. Instead of sending information out to the internet, Goldman Sachs brought leading language models like OpenAI's GPT-4, Google's Gemini, and Anthropic's Claude inside the bank. They granted secure, role-based access to all 46,000 of their employees. By solving the security problem first, the bank shifted the primary bottleneck of their operations. The limiting factor was no longer human execution speed, but machine processing power. The first tier of this deployment is the GS AI Assistant. It uses a technique called Retrieval Augmented Generation, or RAG. RAG allows an AI to search through a specific private database, like Goldman's internal compliance policies or past transaction records, and use that exact information to answer employee questions securely. This timeline shows the compression of document processing time. Drafting complex initial public offering documents, a task that historically required weeks of manual labor, is shrunk to a matter of minutes. Today, employees feed over 1 million prompts into this assistant every single month. Beyond the bankers, Goldman Sachs also looked at their software engineers. A major labor bottleneck for developers is writing unit tests for legacy Java code. Unit tests are small, automated checks written to ensure that individual pieces of software function exactly as intended without breaking older systems. To clear this specific hurdle, the bank deployed an AI tool called diff-blue-cover, which reads existing code and automatically writes the corresponding unit tests. This chart compares human labor against machine output. Writing 3,000 tests for a legacy application would historically take 8 months. The AI completed it overnight, a 180 times speed increase. In 24 hours, code coverage jumped from 36 to 72%. These first 2 tiers of deployment demonstrate that artificial intelligence can successfully eradicate both broad operational delays and highly specific technical debt. Which leads to the third tier of Goldman Sachs' escalation, shifting from using AI as a software tool to hiring AI as an autonomous colleague. The firm is actively piloting Devin, an AI software engineer built by Cognition Labs. The core difference here is autonomy. While a standard chatbot waits for you to prompt it step by step, an agentic AI operates independently to achieve an outcome. A developer assigns a high-level goal, like migrating an old codebase. Devin independently plans necessary steps, writes the code, tests its work, and submits for human review. This diagram illustrates the projected efficiency gain from this autonomous workflow. A single developer managing these agents can expand their output, multiplying total productivity by 3 to 4 times compared to working alone. This level of autonomy transitions the technology from a passive assistance tool into an active, independent digital workforce capable of executing complex, multi-step tasks. Across the firm, these deployments are already yielding measurable results, including a 20% boost in overall coding speed and a 15% drop in post-release software bugs. For Goldman Sachs Chief Information Officer Marco Argenti, this introduces a change in how corporate work is organized. Argenti noted that the primary job of a human employee is no longer to manually type out the code or draft the research report. Instead, the role is to manage the artificial intelligence that does the manual labor. To operate in this hybrid workforce, employees must develop 3 specific skills. They need the ability to accurately describe the goal, successfully delegate the task to the machine, and critically supervise the final output to catch errors. This dynamic makes early career workers surprisingly critical to the transition. Because they are growing up alongside generative AI, junior employees are adapting to the demands of managing these systems much faster than many legacy employees. The case study suggests that the most successful companies in this era will use the technology to promote their employees into managers of a tireless digital workforce.
There is a lot of noise right now about AI agents, and a lot of confusion about what they actually do. If you cut through the industry hype, the definition is surprisingly simple. An agent is essentially a model using tools in a continuous loop, entirely autonomously. You give it an objective, and it figures out how to execute that objective on its own. When this works, the capability acts as a massive force multiplier. You suddenly step into the role of a manager overseeing a tireless team of highly intelligent, highly motivated digital employees. They execute your instructions at massive scale, moving at the speed of compute.
But that autonomy removes the natural human friction that usually catches mistakes in a workflow. When a human messes up, the damage is limited by how fast they can type. When a computer operating autonomously makes an error, the negative consequences scale just as quickly as the successes. To understand exactly how these systems break down, security professionals rely on the OWASP Top 10 list for AI agents. OWASP, or the Open Worldwide Application Security Project, is an industry consortium that tracks and publishes the most critical vulnerabilities in software. Their framework gives us a clear map of where autonomous systems are currently exposed. If you look closely at that list, you realize that evaluating these security flaws as isolated bugs misses the true danger. Because agents operate independently, a single bad input doesn't just trigger an error message, it sets off an escalating chain reaction. This diagram shows the basic architecture of an AI agent, which operates in 3 distinct phases: inputs, processing, and outputs. Everything starts with the inputs, the prompts, APIs, or documents the agent reads. Those feed into the central processing phase, where the model actually reasons and plans its next move.
The first tier of compromise happens right here, when attackers hide malicious instructions inside those routine inputs. Because agents struggle to distinguish legitimate instructions from regular text, a hidden prompt inside an innocent-looking web page or email can silently redirect the agent's planning, hijacking the entire objective. This mental corruption also happens through memory poisoning, where attackers inject tainted data into the agent's RAG sources. RAG, or Retrieval Augmented Generation, is a system that allows an AI to pull external facts from a database to inform its answers. If that database is poisoned, the agent relies on biased or dangerous information for its long-term reasoning. An agent's logic can also be corrupted before it even boots up through supply chain vulnerabilities, like dynamically loading a poisoned third-party plugin, or the corruption can happen slowly over time. These are known as rogue agents, systems that slowly drift from their intended behavior to pursue hidden goals or game their own reward systems. In this first tier of escalation, the agent hasn't actually broken down. It is functioning perfectly, reasoning clearly, and planning effectively. But its powerful digital mind is now dedicated to executing the exact wrong objective. This diagram shows what happens when that corrupted logic expands into the outputs phase. A compromised mind is dangerous, but an agent's true power lies in its tools. Once the objective shifts, the agent's autonomous ability to write files, send emails, or query APIs becomes a direct weapon. Agents frequently operate with overprivileged access, inheriting the broad network credentials of their human creators. This leads to identity abuse and tool misuse.
The agent uses its legitimate permissions to access secure databases or exfiltrate sensitive files, believing it is simply completing its newly assigned task. The situation escalates further when you factor in unexpected code execution. To solve complex problems, many modern agents are designed to dynamically write, compile, and execute their own code on the fly. Because this code is generated dynamically and unpredictably, it allows the agent to bypass standard defenses and escape traditional security sandboxes. A sandbox is an isolated testing environment that restricts what a program can do to prevent it from harming the broader system. When an agent writes its way out, it gains remote execution capabilities across the network. In Tier 2, we see the real cost of unchecked autonomy. The system takes a simple, text-based bad input and translates it into a devastating data breach or costly physical action, all without the attacker ever needing to write a traditional software exploit. This diagram shows the final and most complex escalation tier, a multi-agent system. In enterprise environments, agents don't work alone. They constantly communicate, delegate responsibilities, and pass data to dozens of other specialized agents across a massive network web. When inter-agent communication lacks strict authentication, a single poisoned agent can spoof messages to its peers. It sends out manipulated instructions, effectively tricking healthy agents into executing malicious subtasks. This dynamic creates rapid cascading failures. Because these agents delegate tasks and share persistent states autonomously, a single malicious instruction amplifies across the network. The damage spreads far faster than any human operator can detect, let alone intervene. And when human intervention is finally required, the rogue agent utilizes trust exploitation. Using highly persuasive, confident, and perfectly reasoned explanations, the corrupted agent presents its catastrophic final action to the human overseer as the logical next step, tricking them into clicking approve. Tier 3 results in a total systemic collapse. The system executes the attacker's ultimate goal, but because the agents communicated using legitimate channels and the final action was technically approved by a user, the system leaves a perfectly clean audit trail that points the finger squarely at the human. The core paradox of AI agents is unavoidable. The exact mechanism that makes them so incredibly valuable, their ability to act without us, is their greatest structural vulnerability. Deploying these systems safely requires rigid guardrails. Agents must be restricted by task-scoped, time-bound permissions, so they only have the exact access they need for a specific job. Data governance must strictly isolate memory sources, and undeniable human-in-the-loop oversight must verify the logic of an action, not just the final result. We cannot deploy autonomous systems and simply hope they stick to the plan. We have to actively engineer controlled friction back into the workflow, ensuring a single compromised input stops at the boundary rather than triggering a digital domino effect. If you want to dive deeper into how to actually build, test, and secure these multi-agent systems from the ground up, head over to the Learn by Doing with Steven YouTube channel. There are full tutorials waiting for you. And for more deep dives into the architecture of modern AI, check out the Steven Data Talk podcast, available right now on YouTube Music, Spotify, and everywhere else you get your podcasts. You'll find all the links you need in the description below. In 1975, software engineer Fred Brooks observed a counterintuitive reality about building complex systems. Adding manpower to a late software project makes it later. Today, AI engineering is crashing into this exact same paradox. The prevailing assumption in the industry right now is that stringing together multiple large language models, using frameworks like AutoGen or MetaGPT, will linearly scale up reasoning and output. The logic suggests that if one agent is smart, a team of 5 should be 5 times faster and 5 times more capable. Empirical data shows the opposite happens. When tasked with collaborative coding or data analysis, multi-agent teams frequently overwrite each other's work, get trapped in endless communication loops, amplify individual errors, and burn through token budgets without actually advancing the task. Early computing hit this exact bottleneck decades ago. This photograph shows the massive physical scale of mid-century computing, where hardware limitations eventually forced engineers to abandon single, monolithic processors and move to distributed, multi-machine architectures. Modern single-instance LLMs face logical constraints rather than physical ones. They are strictly bounded by context windows, available memory, and token generation speeds. LLM teams operate as strict distributed computing systems. They are bound by the exact same mathematical bottlenecks that plagued early server clusters. To fix an LLM team, we have to treat it like a distributed network. These teams share 4 non-negotiable structural properties with traditional server clusters. First is independence. Look at this network topology model showing 5 distinct agent nodes. Notice the opaque memory boundaries around each one. Every agent operates strictly on its own local context window. None of them have automatic access to a global state. Second is communication. Because they lack a shared brain, these agents coordinate by passing discrete messages, prompts, and generated text back and forth across the network to divide and integrate their work. Third is concurrency. When multiple nodes operate simultaneously on a shared repository, you get synchronization hazards. Agents execute actions based on stale information or silently overwrite a file another agent is currently using. Fourth is fallibility. An agent might hallucinate a variable, stall on an API call, or execute a tool incorrectly. When that node fails, it passes corrupted data to its neighbors, causing the entire pipeline to collapse. Accepting this structural overlap allows us to abandon trial and error prompt engineering. We can apply decades of mathematical systems theory to predict exactly when an LLM team will fail. We can calculate the maximum possible efficiency of an LLM team using Amdahl's law. This principle defines the hard mathematical limit on computational speedup based entirely on the parallelizable fraction of a workload. This chart plots the Amdahl speedup curve. As serial dependencies increase, the curve plateaus aggressively. Researchers tested this on LLM teams. Highly parallel tasks tracked closely along the steep curve, but for highly serial tasks, speedup flatlines. Adding more agents produces zero speedup. Specific models, including GPT 5.2 and Gemini, hit their efficiency plateau well below the theoretical limits. The intrinsic friction of reading and writing messages to coordinate handoffs consumes the time saved by dividing the work. Adding agents to a workflow without analyzing its mathematical parallelizable is a waste of compute resources.
Once a task is parallelizable, you face the primary orchestration trade-off: choosing a centralized architecture where a single controller preassigns tasks, or a decentralized architecture where agents autonomously claim tasks. Decentralization theoretically balances workloads automatically. However, giving agents the autonomy to negotiate their own tasks introduces a severe communication tax. This peer-to-peer network graph illustrates the problem. 2 nodes communicating is simple. Scale to 5 nodes, and the communication lines explode exponentially. Decentralized coordination forces agents into an order of n-squared communication complexity just to figure out who is doing what. This results in idle rounds. In empirical tests, agents get trapped in loops, burning tokens continuously to generate messages confirming they are standing by and waiting for a teammate to finish a dependency. Beyond token waste, autonomous execution on a shared state directly causes consistency conflicts. Decentralized teams exhibit 3 specific types of state violations. They perform concurrent writes, silently overwriting each other's code. They perform rewrites, destroying previously verified work. And they commit temporal violations, attempting to execute a function before its prerequisites exist. Decentralization solves the problem of rigid task distribution, but left unmanaged, it introduces catastrophic communication overhead and silent data corruption. If centralized, pre-assigned orchestration is more token efficient and safer, why ever use decentralized teams? The answer lies in the straggler problem, another concept inherited from distributed systems. In a synchronized phase, overall pipeline progress is gated by the single slowest worker. This bar chart tracks the straggler gap. In a centralized run, rigid assignments mean if one agent stalls, the entire team sits idle. But decentralized architectures mitigate this. Watch the chirp shift as a stalled task is reallocated to a faster agent, reducing time to completion. Evaluating an LLM team on pure wall clock speedup ignores the true operational constraint for production systems: cost efficiency. This table compares the speedup multiplier against the token multiplier across parallel and serial tasks. Because agents constantly synchronize, manage consistency, and negotiate tasks, the token consumption drastically outpaces actual task progression. The red highlight isolates the empirical worst-case scenario, a decentralized team forced to perform a highly serial task. Token usage skyrockets to a 5.8x cost multiplier while delivering a negligible 1.1x speedup. Deploying a multi-agent system is a massive financial liability if the task's mathematical profile does not support the overhead. We can synthesize these empirical results into a strict set of design heuristics. This matrix plots the workflow type on the y-axis, serial versus parallel, against API latency variance on the x-axis. For sequential workflows, the rule is absolute. Never deploy a decentralized team. Rely on a single capable agent or a strict centralized controller to eliminate the overhead. For highly parallel workflows experiencing variable API latency, deploy decentralized teams to absorb the stragglers, but mandate pessimistic file-based locking to physically prevent concurrent write conflicts. Scaling AI requires rigid distributed systems architecture. If you want to build these architectures yourself, check out the Learn by Doing with Steven YouTube channel for hands-on system builds. For deeper discussions on AI systems, subscribe to the Steven Data Talk podcast on Spotify and Apple. Links are in the description. The standard approach to training large language models assumes a simple equation: feed massive, hyper-specific instruction datasets into a network to force better performance. Supervised fine-tuning, or SFT, is the mechanism used to drag pre-trained models into human-aligned instruction-following behavior spaces. But current SFT pipelines are governed by unproven heuristics. Engineers throw millions of text pairs at a model, relying on the assumption that more data naturally yields better alignment, without a rigorous map of the architectural mechanics. A study by Hirata et al. Replaces these assumptions with massive-scale empirical evidence.
They generated over 1,000 individual fine-tuned models. To do this, they systematically mapped 12 different base architectures against 10 diverse datasets, testing both full parameter tuning and low-rank adaptation. By deconstructing this dataset, we can identify 4 empirical laws governing model data synergy, perplexity, layer dynamics, and training scale. Understanding these mechanics allows machine learning engineers to strip away wasted compute and reliably extract the maximum possible capability from their models. The first research question addresses data synergy. Do specific training datasets yield universal improvements across every base model? This heat map charts baseline performance changes across diverse benchmarks after fine-tuning. Some datasets yield universal improvements, while others reliably fail. General domain instruction data, like Alpaca, generates reliable cross-task boosts. Conversely, classic NLP datasets, like the FLAN reasoning corpus, frequently degrade broad task accuracy. The data reveals a significant anomaly. English-only SFT datasets triggered substantial zero-shot performance gains on foreign language evaluations. This chart displays the correlation coefficients for performance gains across English, Chinese, and Japanese variants of the MMLU benchmark. The strong positive correlations across all pairings prove that the underlying reasoning improvements transfer directly, regardless of the training language. To understand how different models react to the exact same dataset, we map their similarity using a hierarchical clustering dendrogram. Models belonging to the same architectural family group tightly together. Their fine-tuning outcomes remain almost identical regardless of data used. The base model's inherent inductive bias establishes a hard boundary. This architecture dictates the final alignment trajectory far more than the specific SFT corpus applied. If the architecture is the boundary, we have to determine what specific statistical property makes a training dataset effective for that model. This graphic shows the relationship between training data characteristics and accuracy. Matching the semantic topic or increasing the average token length yields weak, scattered results. The data identifies a different property. A dataset's base perplexity relative to the untrained model is the single strongest predictor of SFT success. This row shows the severe negative correlation. Lower initial data perplexity yields higher accuracy gains. Low perplexity means the data already sits within the model's pre-existing linguistic distribution. As we pan across the plots, this mathematical law holds steady across architectures. Forcing a model to learn from relevant but high perplexity data causes inefficient training, as the network must unlearn its established base weights. To optimize the compute budget, data engineering pipelines should prioritize perplexity filtering over topical curation. Shifting focus to the internal architecture, we can pinpoint where instruction-following behavior takes root inside the transformer blocks. This graph visualizes weight changes across network depth. The orange line shows parameter update scale higher toward the final output layers, but actual impact differs. The blue line maps the correlation between weight changes and accuracy gains, peaking sharply at 0.6. To understand why this mid-layer region controls alignment, we have to measure the network's intrinsic dimensionality. This panel tracks intrinsic dimensionality curves, comparing the embedding space geometry of the base pre-trained models in blue against fine-tuned models in red. Precisely at the 0.6 mark, the fine-tuned model's dimensionality sharply expands and permanently diverges from the base model. SFT forces the mid-layers to carve out a new representational subspace, going beyond simple adjustments to output logits in the final layers. The early input layers and late output layers remain structurally static, functioning strictly as ingestion and projection mechanisms. Monitoring these mid-layer transformations is the key to measuring true instruction-following adaptation. We can observe the global effect of training variables by mapping all 1,070 checkpoints into a shared latent space. By extracting high-dimensional log likelihood vectors from every model, we can project that data down onto a readable 2D map. Tracking consecutive training epochs reveals that, regardless of the training dataset, model trajectories spiral inward toward a shared instruction-following zone. We can also compare highly curated 1,000 sample datasets against massively scaled 20,000 sample datasets. The data exposes a counterintuitive scaling law. pushing to 20,000 samples frequently forces the representation outward, away from the optimal central alignment space. Finally, we measure hardware-efficient low-rank adaptation, or LoRa, against computationally expensive full-parameter tuning. Inside this latent space, LoRa trajectories almost perfectly overlap the full-parameter tuning coordinates. The performance trade-offs are minor. Full-parameter tuning maintains a slight edge on reasoning-heavy mathematics, while LoRa performs slightly better in open-ended question answering. Brute force scaling is mathematically inefficient. Combining a low-perplexity, 1,000-sample dataset with LoRa provides the absolute highest return on investment for model alignment. LLM alignment follows the rules of a predictable, measurable, mechanical science. Base architecture dictates the limits of alignment, and base model perplexity predicts success far better than semantic matching. Alignment physically expands the network's dimensionality in the 0.6 mid-layers, and scaling to 20,000 samples often degrades optimization compared to a tight 1,000 sample set. To optimize compute, engineers should build alignment pipelines around targeted tuning rather than massive data scaling. You can apply these empirical findings to your own architectures. For hands-on, deeply technical coding implementations and architectural deep dives, head over to the Learn by Doing with Stephen YouTube channel. And for continued high-level discussions on AI research, check out the Stephen Data Talk podcast, available on YouTube Music, Spotify, and all major platforms. True model optimization comes from rigorous, empirical measurement rather than following industry heuristics.
Every single week, over 1 billion people open a text box, type out a rough thought, and ask a large language model to fix it. We approach these models as highly advanced spell checkers. We ask them to clean up our grammar, professionalize our emails, or tighten our prose, expecting the core ideas to remain entirely our own. But a language model is a statistical engine. When we treat it as a neutral instrument, we assume our underlying thought survives the optimization process unharmed. A massive new study from researchers at DeepMind, Berkeley, and the University of Washington has tested that assumption. By tracking how humans write with and without these models, they found that handing your words to an AI systematically shifts your arguments. It alters the intended meaning of your text and smooths away your unique perspective. Writing is the process of clarifying human thought. We have to look at the data and ask, what happens to our thinking when an algorithm holds the pen? To see this in action, the researchers set up a controlled study. They tasked 100 participants with writing an argumentative essay. Half were given access to a large language model. The other half wrote entirely on their own. The people who relied heavily on the AI saw a 70% increase in essays that remained completely neutral. Instead of taking a stance, the writing hedged, hovering safely in the middle ground. When interviewed afterward, these heavy AI users reported feeling disconnected from their work. The final drafts felt significantly less creative and no longer sounded like their own voice. This chart shows exactly how the AI replaced that human voice. Compared to the dark gray human baseline, the purple and green AI-influenced essays spike in their reliance on expert opinion and statistical arguments, abandoning personal conviction for clinical data. At the individual level, the algorithm acts as a heavy moderating force, discouraging users from taking a front stand. It effectively flattens human conviction into agreeable summaries. You might think the solution is simply to write the draft yourself and only use the AI for light copy editing. The researchers tested that too, using a 2021 dataset of human essays and expert feedback. They used a technique called PCA semantic shift. Think of this as a map that plots the physical distance between different concepts. If an edit changes the meaning of a sentence, its dot moves across the map. This graph maps semantic shift. In the human baseline, short arrows point in diverse directions, preserving original meanings. But look at Claude, Gemini, and GPT-5 Mini. Even given minimal edit instructions, every model drags the essays in massive parallel lines to the exact same region. This violin plot shows the linguistic mechanics of that shift. To push all those ideas into the same space, the models artificially inject a high volume of analytic words and double the emotional sentiment to make the text feel universally convincing. The data shows that LLMs do not preserve human diversity. They actively drag our individual thoughts into a uniform algorithmic space of conformity. That conformity is already bleeding into high-stakes environments.
We can see it in the peer review process at the 2026 International Conference on Learning Representations, a major venue for evaluating new, complex science. Researchers discovered that 21% of the peer reviews evaluating the cutting-edge science at this conference were generated or heavily edited by an AI. These models actively rewrote the conference's grading rubric. Instead of prioritizing human values like clarity or the significance of a discovery, the AI-generated reviews fixated on machine-friendly metrics like scalability and reproducibility. Because of this shift in focus, the AI-generated reviews assigned scores that were, on average, a full point higher than the human baseline. By substituting human values for algorithmic priorities, these models have already begun to reshape how our scientific institutions define truth and progress. The researchers point to a specific capability deficiency. Current language models are simply incapable of assisting with your writing without changing your meaning. Because these systems are trained on massive scales of human feedback, designed to be as broadly agreeable as possible, by leaning on them, it creates a cultural lock-in. They reinforce their own specific statistical priors over our individual logic. When we offshore our writing to an AI, we are subtly offshoring our political discourse, our literature, and our institutional decision-making to an algorithmic mono-voice. The next time you prompt an AI to make this sound better, remember the cost. You are trading your original logical path for a pre-calculated statistical one, letting the algorithm rewrite your mind alongside your prose. If you want to understand the code, the data, and the technology actively reshaping our world, check out the Learn by Doing with Stephen YouTube channel. For on-the-go deep dives into these topics, the Stephen Data Talk podcast is available now on Spotify and YouTube Music. All links are in the description. Thank you for watching, and always keep questioning the data. For years, interacting with artificial intelligence meant typing into a chat window. The system would generate an answer, stop, and wait for a human to give it another command. It was a passive tool requiring constant oversight. Now, developers are taking large language models and fracturing them into specialized modules called agents. Instead of waiting for prompts, these agents string together multiple complex steps, passing instructions to one another and executing entire workflows entirely on their own. To organize massive amounts of product data, researchers didn't use human moderators. They deployed a loop of specialized AI agents. This workflow diagram from a recent e-commerce study shows exactly how this operates in practice. One agent builds the basic categories, another refines definitions, and a third extracts details to populate a final structured knowledge graph. No human intervenes. These interconnected agents transform AI from a writing tool into a system capable of end-to-end digital labor. This pie chart illustrates the current global artificial intelligence software as a service market. Notice how fragmented the space is, with 84% divided among smaller players. But those tiny slivers at the top belong to Microsoft, Amazon Web Services, and NVIDIA. They maintain enormous influence because almost all of those smaller companies must rent server space from their centralized cloud networks to run their AI models. Meanwhile, Chinese developers have rapidly introduced highly capable AI models like Kimi and Qwen, intensifying the global competition to build out agentic capabilities and capture global users. Control over the infrastructure powering this autonomous workforce is now the central strategic objective, superseding the race for the most capable chatbot. The open-source community's answer to that centralized control is a viral framework called openclaw, affectionately known by its developers as the Lobster. openclaw bypasses major cloud providers, deploying AI agents entirely locally on personal hardware. This creates the one-person company. A single operator can spin up a localized network of digital workers to run an entire business in a closed loop. Because the system runs locally, highly sensitive enterprise data never leaves the user's physical premises. This eliminates the risk of corporate data leaking into a public cloud server. By decentralizing digital labor, openclaw bypasses the lucrative monthly subscription models that major tech firms rely on for revenue. The major players are already pushing back. Anthropic recently took action to block third-party tools like openclaw from accessing their Claude models through standard user accounts. Users had been paying a flat $200 monthly subscription, but by attaching these autonomous frameworks, they were running background tasks nonstop. This continuous agentic labor was burning through thousands of dollars in Anthropic server compute time. But the friction goes far beyond corporate billing disputes. The financial sector is currently grappling with a severe systemic risk known as the black box trap. Modern, advanced deep learning models lack transparent logic. If an asset management firm deploys autonomous agents to trade securities continuously, the internal reasoning behind those trades is completely impossible to audit. If one of these agents hallucinates a financial trend and begins executing thousands of rapid-fire trades without human oversight, it could trigger a catastrophic market feedback loop before anyone understands what is happening. Removing human checkpoints in cloud oversight allow for 24/7 productivity, while simultaneously creating blind spots in financial auditing. Professor Feng Wei describes this moment as the lobster revolution. We are witnessing a structural economic shift from purchasing software applications to deploying and managing digital labor. Modern efficiency is calculated by workload execution. The volume of independent tasks an agentic network can finish in a single hour. This demands a completely different human skill set. Workers must pivot from executing linear individual tasks to orchestrating broad net toward local agentic labor, forces a reassessment of the high-margin subscription models and linear workflows that defined the previous decade of technology. This revolution provides individuals with immense local leverage. But without strict, deliberate human oversight, the same technology risks profound corporate and financial instability. To successfully navigate this transition, you need to understand how to build and control these tools yourself. Head over to the Learn by Doing with Steven YouTube channel and other video platforms for practical guides on mastering these agentic frameworks. And to dive deeper into the data shaping these macroeconomic trends, listen to the Steven Data Talk podcast on YouTube Music or Spotify.
Okay, we are about to tackle one of the most common questions in the entire tech world. But I gotta tell you, the answer is probably gonna change how you think about computers forever. Let's dive in.
So, whether you're dreaming of a career in tech or you're just, curious about where all this is heading, you've probably asked this question. Should I learn Python, Java, C++? Well, the most important language you'll ever need to know, it's probably not what you're expecting.
That's right, I'm not kidding. The single most important programming language for this new era of AI is the one you already know. If you're understanding me right now, you are already equipped to program the future. And I'm going to show you exactly how.
Now, to really get why this is such a monumental shift, we first have to understand the basic idea of what programming even is. At its core, it all starts with just wanting something to happen, and then figuring out the steps to make it happen.
Think about something simple, like baking a cake. You start with your intent. You want a delicious chocolate cake. Great. You then translate that feeling into instructions. That's your recipe. You follow the recipe, you mix the stuff, you put it in the oven, and you get the result. A beautiful, tasty cake. Pretty straightforward, right?
Well, for decades, that is exactly how computers have worked. You have an intent. Let's say you want a program that figures out all the ways to make change for $1. Then you have to translate that idea into very, very specific instructions. That's the code. And here's the most important part. You had to write that code in the computer's language, not your own.
So, how did we even get here? For pretty much all of modern computing history, the whole journey has been about one thing: humans learning to speak the machine's language. Let's do a super quick tour of that evolution.
You can see this clear progression over the decades, right? We started with languages that were super close to the metal, to the hardware itself, and we've been taking these little steps one by one towards languages that feel more like how we actually think and speak. In the very beginning, we had machine language and assemblers. I mean, this was the raw native tongue of the computer, and as you can probably guess, it was unbelievably complex for a person to read or write. It's the kind of code that just looks, well, gorpy is the perfect word for it.
So the next big leap forward was what we call high-level languages, like Fortran and COBOL. These were a massive improvement because they used words that kind of looked like English. But there was a big problem. They often created what developers called spaghetti code, just this tangled mess of commands jumping all over the place. It was a nightmare to try and follow or fix.
To clean up that mess, we entered the era of structured programming with languages like C++ and Pascal. The whole idea here was to bring some order to the chaos by organizing code into these neat, logical blocks and objects. And it worked. It made programming way more robust, but it was still a super specialized skill that really didn't match how our brains naturally work.
And then, the internet changed everything. We needed languages like Java with its famous promise of write once, run everywhere, and these really flexible scripting languages like Python. They were even more abstract, another huge step away from the machine and closer to us. But we still weren't quite there yet. And that brings us to right now, the AI era. And this isn't just another step in the process, folks. This is a whole different ballgame. It's a complete paradigm shift. The magic behind this revolution is something called natural language processing, or NLP. This is the field of AI that finally allows machines, especially these crazy powerful large language models, to understand us in our own language. Whether you speak English or Spanish or Mandarin, it doesn't matter.
This little diagram really says it all. In the old world, you were the translator. It was your job to turn your brilliant ideas into rigid, structured code. Now, the AI is the translator. You just state what you want, and it handles the rest.
Just let that sink in for a second. For over half a century, the entire burden was on us. We had to learn the strange logical languages of computers. That entire era is now over. For the first time in history, the burden is on the machines to learn our messy, beautiful, and complicated human languages.
Okay, so let's circle all the way back to that surprising answer from the beginning and talk about what this actually means for you, right here, right now.
Remember our cake analogy? With AI, that whole middle step, the part where you had to meticulously write out the recipe in a foreign language, it's just gone. You can now go straight from your intent to the result, and you let the AI worry about the instructions. This is absolutely huge.
Let's make this even more real. I'm going to show you 2 different ways to ask a computer to do the exact same thing. Just tell me, which one of these makes more sense to you?
I mean, come on. Look at the difference. On the left, you've got that GORPy assembler code. It's cryptic, it's complex, it's basically unreadable. On the right, you have a simple sentence in plain English. They're both instructions for a computer, but only one of them is an instruction that you can actually give. You know, it used to take something like a 4-year computer science degree just to get really good at writing the stuff on the left. Think about that for a second. Years of specialized training just so you could talk to the machine. But the absolute beauty of your natural language is how accessible it is. You don't need a special degree to learn it. You've been speaking it your entire life. And it doesn't matter what language you speak, because these new AIs are being built to understand all of them. So, here's the real takeaway. The good news is that we have reached this incredible moment in history where you no longer have to be a programmer in the old sense to create amazing things. You just have to be able to clearly say what you want. The most important programming language of the future is your own. The only real question left is, what are you going to build with it?
By the year 2048, an estimated $124 trillion will change hands in a massive generational wealth transfer. For financial advisors, capturing this capital is the single most critical priority of the next 2 decades. But the professionals tasked with managing this transition are severely constrained. Data shows that the average wealth advisor spends only 39% of their working hours actually speaking with clients. The other 61% of their day is consumed by desk work. That means highly compensated experts spend their time combing through research databases, manually typing up meeting notes, and entering data into CRM systems. The most immediate threat to the wealth management industry is a structural shortage of human capacity. There is simply not enough time in the day to manage the incoming wave of assets using traditional administrative methods. Over the last 2 years, Wall Street has become obsessed with artificial intelligence. Every major institution is exploring how to implement the technology. This chart shows corporate expectations for AI impact, broken down by cost efficiency and revenue growth. According to Morgan Stanley's global research, boardrooms and investors are no longer satisfied with simply having AI exposure. They are actively demanding hard proof of return on investment. Deploying this technology across an 82,000-employee bank is incredibly difficult. Financial institutions operate under heavy regulatory burdens, meaning any new system must be strictly secure, explainable, and fully compliant with strict data privacy laws. To gain a true competitive edge, a firm has to move beyond novelty chatbots. The technology must operate as a measurable, enterprise-wide efficiency engine. Morgan Stanley started by targeting the information bottleneck. The firm's proprietary research library contains over 100,000 documents spanning decades. Searching through that archive manually to answer a specific client question could easily take an advisor 30 minutes or more. In response, the bank launched the AI at Morgan Stanley Assistant and Ask Research GPT. These tools were built through a secure, closed-loop strategic partnership with OpenAI, ensuring that proprietary financial data never leaks into public models. Using natural language processing, a branch of AI that allows computers to understand and generate human language, the assistant scans the entire archive. It instantly ingests unstructured data, synthesizing the findings into a clear answer complete with direct citations to the original reports. The results were immediate and measurable. Document retrieval efficiency jumped from 20% to 80%, drastically cutting the time required to source institutional insights. This system effectively puts the firm's chief investment officer in the room for every client call. It democratizes decades of complex institutional knowledge, making it accessible in seconds. After solving the information retrieval problem, Morgan Stanley targeted the physical administrative burden of conducting the meetings themselves. They introduced AI at Morgan Stanley, Debrief. With explicit client consent, this tool joins video and audio meetings to actively transcribe the conversation in real time. Once the call ends, the software generates automated post-meeting outputs. It summarizes the key points, drafts a personalized follow-up email for the advisor to review, and logs the actionable notes directly into the firm's central database. By automating these specific tasks, the Debrief tool reclaims roughly 35 minutes of administrative work per meeting. When you multiply those 35 minutes by 5 or 6 client meetings a week, an individual advisor suddenly gets several hours of capacity added back to their schedule. This highlights Morgan Stanley's strict human-in-the-loop philosophy. The machine handles the tedious administrative logic, freeing the advisor to focus entirely on high-value, nuanced human relationships. Internally, the adoption rate has been staggering. Today, 98% of Morgan Stanley's advisory teams are actively using the AI assistant. Zooming out, the broader economic impact is becoming clear. Morgan Stanley's thematic research tracks companies globally that have utilized AI for over a year, finding that they report an 11.5% average increase in net productivity. But the data reveals a dual trend. These double-digit productivity gains are paired with targeted workforce reductions, specifically a 4% net decline in headcount among those heavy AI adopters. Real-world AI ROI translates into the systematic reallocation of human capital from administrative bloat to direct revenue-generating tasks. As Morgan Stanley's head of firm-wide AI recently noted, giving employees an end-user chatbot makes them happy and looks great to a board of directors. But a chatbot alone does not alter the underlying business model. The true catalyst for business transformation lies in ruthlessly identifying and then automating complex, multi-step workflows from end to end. This leads to the next phase of enterprise technology, agentic AI. We are moving away from passive assistants waiting for prompts toward active agents that automatically route requests and execute background tasks completely independently. The ultimate competitive advantage in the AI era is the unprecedented amount of time reclaimed for high-value work only humans can perform. To run artificial intelligence locally, the standard approach is to open the Hugging Face leaderboard and look for the absolute largest models available, like DeepSeek R1 671B or Llama 3.3 70B. But when you try to force a 70 billion parameter model into a standard consumer machine, the system will likely crash or generate text at a painfully slow rate of less than 1 token per second. The alternative is to use small language models, or SLMs, that operate under 15 billion parameters. SLMs are compact AI networks designed specifically to run efficiently in resource-constrained hardware environments. The old trade-off was simply choosing between capability and size, but the new reality requires matching strict hardware constraints with highly specialized tasks. You can run fully private, offline, fast AI on your own hardware right now, but you have to abandon the desire for a single, massive model that does everything perfectly. The absolute dictator of what your machine can physically run is its VRAM. Video RAM is the dedicated memory on your graphics card that dictates exactly how much AI data your system can hold at one time. Parameter sizes required for GPT-4 level performance plummeted between 2024 and 2026, while average consumer VRAM flatlined. The breakthrough bridging this gap is distillation, a process where small models learn to mimic the complex reasoning of massive frontier-grade networks. Success in local AI is no longer about finding the smartest model in the world. It's about meticulously matching the right specialized model to the strict physical limits of your hardware. This flowchart maps out the hardware spectrum, showing that deploying local AI must begin with one fundamental calculation: identifying your total system VRAM. We start at the lowest branch, the edge and mobile tier, for systems with 4 to 8 gigabytes of VRAM. The primary advantage of deploying models here, like 5.4 Mini Instruct or Small LM33B, is achieving real-time, localized inference on standard laptops and edge devices without needing a dedicated server. The functional trade-offs are severe. These models suffer from weak multi-step reasoning and limited context windows. A context window is strictly the maximum amount of text the model can process and remember in a single interaction. Because of strict memory limitations, sub-8 gigabyte models will reliably fail at complex agentic coding workflows. Agentic coding involves an AI system autonomously writing, testing, and debugging software across multiple independent steps. However, you can still use specialized tools like Qwen 3.5 0.8b to handle extremely fast vision-to-text generation tasks within this memory footprint. You must also avoid triggering thinking mode at the sub-1 billion parameter scale, as the limited architecture frequently results in infinite, unstable generation loops. The 4 to 8 gigabyte tier delivers zero latency privacy for basic conversational tasks, but it demands strict system guardrails to prevent total logic breakdowns. Moving up the hardware spectrum brings us to the middle and most heavily populated branch, the 8 to 16 gigabyte consumer sweet spot. The heavy hitters in this category are models like DeepSeek R1 Distill Llama 8B and Microsoft's 5.4 14B. These models inject GPT-4 level math and logic directly into a standard RTX 4070 or Mac by utilizing distilled chain-of-thought reasoning. Chain-of-thought is a generation technique where the AI explicitly writes out its step-by-step intermediate logic before arriving at a final answer. This diagram illustrates the mandatory mathematical compromise, 4-bit quantization. This compression technique reduces a model's memory footprint by rounding its numerical weights into lower precision formats. In practice, Q4 quantization violently squeezes a 14 billion parameter model into just 8.4 gigabytes of VRAM.
Academic testing proves this Q4 compression causes virtually zero impact on actual model calibration or the number of dead neurons. Dead neurons are components within a neural network that stop responding to inputs and contribute nothing to the final output. There is, however, a secondary hidden cost to running distilled reasoning models at this tier, and it lies entirely in the generation process. The internal reasoning tokens generated during chain of thought eat aggressively into your usable context window, which strictly limits the amount of external document data you can ingest in a single prompt. The 8 to 16 gigabyte tier represents the ultimate value play in 2026, forcing you to trade a slice of context length in exchange for world-class quantized logic. The final hardware branch is the prosumer category, covering systems with 16 to 24 gigabytes of VRAM. Deploying massive SLMs like Qwen 332B requires high-end hardware like an RTX 5090 or a Mac Studio. Operating here gives you flawless, desktop-level access to frontier-grade coding performance and massive 128K context windows that allow for full, unedited document ingestion. The trade-offs are a heavy upfront capital investment of thousands of dollars in GPUs and the complex challenge of managing the KV cache. The KV cache is a memory mechanism that stores previously computed tokens to speed up generation, but it grows continuously as a conversation lengthens. Operating strictly at the 24 gigabyte tier transcends running a simple desktop chatbot. You are hosting a private, enterprise-grade reasoning engine. This comparison matrix transitions hardware theory into specific, practical application scenarios. Our first profile is an indie coder utilizing a MacBook Pro with 16 gigabytes of unified memory. This specific configuration delivers world-class offline logic, but it dictates that the coder must limit the size of the codebase they analyze in any single prompt. The second profile is a private enterprise building an offline RAG system to analyze sensitive legal and financial PDFs on low-end legacy CPUs. RAG, or Retrieval Augmented Generation, is a framework that fetches relevant information from a private database and feeds it to the AI to answer specific queries. Utilizing the BGE-M3 embedding tool allows for an entirely air-gapped CPU deployment, bypassing the need for expensive enterprise GPUs. An embedding tool is a model that converts text documents into numerical vectors so the AI can quickly search and retrieve relevant concepts. The architectural bottleneck of this setup is 5.4's strict 16K context limit, which requires the enterprise to aggressively chunk their retrieved PDFs into smaller fragments before the AI reads them. Successful real-world AI deployment is never about raw compute power. It is about perfectly aligning the model architecture, the embedding tool, and the physical hardware constraints. The final operational hurdle is the software execution layer required to load these models into memory. You have to weigh the instant command-line simplicity of an ecosystem like Ollama against the polished, granular interface of LM Studio. The specific trade-off of using these easy one-click tools is sacrificing the extreme throughput optimizations and granular performance tuning available in enterprise-grade engines like VLLM. VLLM is a high-throughput memory management engine built specifically for serving AI models at a massive scale. Zooming out to evaluate the macro perspective of the 2026 AI landscape reveals a clear picture. The absolute frontier of artificial intelligence is no longer restricted behind the paywalls of billion-dollar server farms. By mastering VRAM limits and deploying highly specialized, distilled SLMs, the bleeding edge of global intelligence now runs cleanly, quietly, and entirely privately directly on the desk in front of you.
When you prompt a chat interface, the response feels like a software achievement, the output of an elegant transformer architecture running on a remote server. The physical reality is more complex. Training a GPT-4 class model is a specialized operation that requires thousands of GPUs running in a coordinated cluster for months. It is a sustained battle against computational physics. At a scale of hundreds of billions of parameters, the model generates a volume of intermediate data that exceeds the memory of any individual GPU. A modern H100 or A100 is capped at 80 gigabytes. The math of the model simply does not fit on the silicon. This diagram shows the engineering pipeline required to navigate those limits. It moves through stages: architecture design, data foundations, distributed training, alignment, and inference. Scaling a model to this level is a triumph of system engineering. It requires solving for memory sharding, network latency, and power constraints, rather than simply adjusting mathematical equations. The engineering shift began with the architecture. While the original transformer used an encoder-decoder structure for translation, modern LLMs are almost exclusively decoder-only. Causal masking blacks out the matrice's upper triangle, preventing the model from seeing future tokens. It predicts the next token using only prior context. To maintain order, relative positional encoding dynamically calculates distance between data points, allowing much longer sequences. This architecture is the engine, but it requires massive amounts of fuel. Training a model with 100 billion parameters requires trillions of tokens sourced from across the internet. Raw web data is messy and repetitive. Pre-processing uses heuristic filters, deduplication to prevent over-indexing, and privacy scrubbing for sensitive data. Some models, like Llama 2, take a different approach. They retain more raw data during pre-training to maximize the model's ability to generalize, relying on later alignment stages to handle safety and toxicity. If the raw data pipeline isn't engineered to filter out noise at the start, no amount of architectural tuning can fix the resulting model. Even with perfect data, the hardware presents a hard limit. A modern 175 billion parameter model requires over 350 gigabytes of memory just to load its weights. The standard solution is data parallelism. The dataset is split into batches, and the entire model is replicated across multiple GPUs so they can process those batches at the same time. However, data parallelism creates a massive redundancy. Every GPU in the cluster is wasting VRAM by holding the exact same set of parameters and optimizer states. In an all-reduce operation, nodes pool gradient calculations into a single aggregate, broadcasted back to update weights. To solve redundancy, model parallelism slices large linear layer matrices into fragments, distributing them across GPUs to work on mathematical operations in pieces. When horizontal scaling hits its limit, engineers must break the model's parameters apart and distribute them across the physical hardware of the server rack. For models scaling toward 200 billion parameters and beyond, developers use the Zero Redundancy Optimizer, or ZERO. ZERO Stage 1 shards optimizer states, spreading them across the cluster. Stage 2 shards gradients, freeing VRAM during backpropagation. Stage 3 shards model parameters. Fragments assembled just in time for calculation, then immediately release back to their host GPUs. Pipeline parallelism adds a vertical layer to this. It slices the transformer layer by layer across physical machines, passing data from layer 1 on GPU A to layer 2 on GPU B. Further efficiency comes from mixed precision training, which uses 16-bit math for speed and 32-bit for accuracy, and checkpoint recomputation, which deletes intermediate results and recalculates them only when needed for backward passes. Zero is a calculated trade-off. It increases the volume of communication across the network to save the GPU memory space required to keep the model running. A pre-trained model is essentially a massive pattern matcher. To make it useful, it undergoes supervised fine-tuning, or SFT, trained on instruction and response pairs to learn how to follow prompts. SFT alone doesn't prevent hallucinations or bias. The model still lacks a framework for human values or factual accuracy. Developers align the model to the 3H standard, making it helpful, honest, and harmless. This process is called RLHF. A reward model is trained on human feedback to score responses. A PPO algorithm then uses those scores to continuously adjust the main model's weights. For those with limited hardware, parameter-efficient tuning, like LoRa, freezes the main network and only trains tiny secondary matrices. This allows developers to adapt a model to a new task without the massive cost of a full fine-tune. This alignment stage is what turns raw statistical probability into a safe, commercially viable product. When running the model for users, the inference phase, we encounter a conflict in hardware architecture. The GPU can calculate answers very quickly, but it is limited by how fast it can access the model's weights in memory. Every token generated requires a lookup in the KV cache. As the conversation gets longer, this continuous memory access creates fragmentation and slows down the response time. We solve this physical limit through structural optimizations like page detention and flash attention. Flash attention chunks attention matrices, forcing computation inside the processor's hyper-fast SRAM chip, entirely bypassing the slow, high-bandwidth memory bottleneck. Finally, model compression techniques like knowledge distillation and quantization allow us to shrink the model's footprint, making it possible to run these large networks on consumer-grade hardware. Inference efficiency is the final bottleneck. A model's intelligence is only as useful as its cost to compute for a single user question. This gear system illustrates the unified pipeline. Pre-training data provides the foundation, Zero handles the hardware load, RLHF aligns the behavior, and flash attention manages the deployment speed. We interact with this system through prompt engineering and chain of thought, using specific structures to extract logic from the weights. The field is already moving toward multimodal processing and new architectures like RWKV, which attempt to solve the memory scaling issues inherent in transformers. For developers, understanding the end-to-end hardware and software pipeline is now a baseline requirement for building the next generation of AI tools. 想了解更多关于大模型底层的硬核知识，掌握前沿 AI 技术，邀请大家关注我的频道 Learn by Doing with Steven 数能生智 Steven Data Talk Steven 数据漫谈等。相关硬核内容在小红书、微信公众号、YouTube、Spotify 等平台同步更新。视频描述和 Show Note 区域有我的 Linktree， 包含所有社交媒体平台的链接。In the late 2000s, banks trained predictive algorithms to ingest highly structured data. This mathematical processing powered high-frequency trading programs and automated credit scoring systems. Generative AI introduces a shift in core capability, the ability to process unstructured data. It can parse the messy, human-readable text found in natural language emails, call transcripts, and dense regulatory filings. This capability points the technology directly at the middle and back offices, where thousands of employees spend their days manually extracting, summarizing, and formatting information. The theoretical efficiency gains are significant. Data from the U.S. Bureau of Labor Statistics suggests that applying large language models to these specific banking functions could reduce task times by up to 73%. Scaled globally, the McKinsey Global Institute projects that generative AI could add between $200 and $340 billion in annual profits to the banking sector. Yet, despite these massive macroeconomic forecasts and hundreds of internal pilot programs, major financial institutions are actively pumping the brakes on deployment. The mandate from risk and IT committees is clear. The period of funding AI experiments for the sake of novelty is over. Banks are now demanding hard unit economics before a single model goes live. The current hype cycle is fueled by research, like early reports from Goldman Sachs, estimating a $7 trillion boost to global GDP. McKinsey estimates massive AI value across banking segments, with the black bars showing generative AI's impact. Corporate banking and risk and legal hold the highest theoretical concentration of value, projected at $321 billion and $385 billion. But the macroeconomic theory breaks down on the front line. When a bank tests a model to draft a pitch book or summarize a client meeting, employees frequently find themselves manually correcting the output. This friction is driven by model hallucinations, instances where the AI generates plausible but factually incorrect information. In banking, a hallucinated figure in a credit report or a regulatory summary carries severe legal liability. Instead of executing their primary duties, highly paid analysts and relationship managers are forced to spend their billable hours acting as fact-checkers for an algorithm. The gap between the trillion-dollar hype and the daily reality is dictated by three rigid constraints: prohibitive compute costs, isolated data silos, and uncompromising security mandates. A promising macroeconomic forecast means nothing if deploying the model locally operates at a net financial loss for the institution. Calculating AI value requires a strict ROI equation, workflow hours saved versus capital expenditure and security overhead. But data privacy laws force banks to host systems on-premise, and these hardware requirements immediately break the equation. Traditional banking infrastructure relies on general compute servers. Hosting large language models requires intelligent compute infrastructure, specifically massive clusters of graphics processing units, or GPUs, optimized for parallel processing. The mathematics of this hardware are punishing. A single intelligent compute node often requires 8 high-end chips per GPU, with individual server units costing upwards of 2 million RMB. RMB stands for renminbi, the official currency of China. To handle the internal query volume of a mid-sized financial institution, IT departments must deploy clusters of 500 or more of these specialized GPUs. If a bank wants to support just 500 concurrent employees using a heavy 671 billion parameter model, the baseline hardware investment alone easily exceeds $10 million. Because customer data cannot leave the building, the generative AI software revolution forces banks into a catastrophic upfront hardware expense. The other side of that cost scale is security overhead, which has escalated sharply with the arrival of autonomous AI agents. Open-source AI agents, like the viral openclaw project, are highly appealing for their ability to automatically execute multi-step workflows. To perform these actions, an agent requires elevated system privileges. It needs authority to call external APIs and directly access local file systems. An API allows different software to communicate. This creates a direct attack vector known as prompt poisoning. By feeding the model hidden, malicious instructions disguised as normal text, hackers can hijack the agent's elevated privileges to bypass firewalls and exfiltrate sensitive internal data entirely. In banking, allowing an easily manipulated algorithm to autonomously access and move data directly violates mandatory Know Your Customer and anti-money laundering compliance frameworks. The reaction from risk and compliance departments has been swift and absolute. Many major banks have issued total internal bans on the deployment of these trending open-source agents. Within a highly regulated network, unchecked autonomous execution represents a critical compliance failure rather than a functional advantage. To survive the dual threats of prohibitive capex and severe security vulnerabilities, the financial sector is executing a strategic pivot. First, institutions are abandoning massive general models in favor of highly optimized inference models like DeepSeek R1. Through architectural innovations, these specialized models have slashed the computing power required for training and inference, dropping operational costs by up to 90%. Second, rather than deploying open-source tools with broad permissions, banks are developing proprietary enterprise agents that are heavily ring-fenced behind internal firewalls. These constrained models are assigned to highly specific tasks. For example, banks use generative adversarial networks and variational autoencoders to act as virtual experts, analyzing transaction patterns to drastically reduce fraud detection times. Again, is a type of machine learning where two neural networks compete to create more accurate data, while a VAE is a model used to find efficient ways to represent complex data. Other isolated models are deployed solely to summarize new 1,000-page federal regulatory rules, ensuring the bank stays compliant without ever exposing the document to the public internet. The true value of generative AI in finance is realized only when the models are restricted to specific, secure operational domains. This constraint is now enforced from the top down. The era of decentralized research and development is over, replaced by a stringent IT committee approval process designed to squeeze the hype out of proposals. Before a single server is purchased, every enterprise AI project must survive a three-step decision matrix. The first gate demands a mature industry precedent, favoring proven tools. The second gate requires hard math. Workflow hours saved must definitively exceed computing costs. Because of this strict filtering, the projects that actually secure funding focus exclusively on high-friction, data-heavy tasks, like automating environmental, social, and governance, or ESG, reports. ESG reporting is a public disclosure of a company's environmental, social, and corporate governance data. These approved tools are explicitly designed to act as co-pilots. They query thousands of internal documents to assist relationship managers, rather than attempting to replace them. The era of speculative AI exploration has yielded to a regime of strict fiscal discipline. Modern projects only survive the committee room if they can demonstrate immediate unit economic viability. This reliance on co-pilots highlights the permanent necessity of the human element. Frontline employees must remain the final validators of any machine-generated output. These human-in-the-loop systems are mandatory. An experienced analyst is required to catch inevitable hallucinations, and crucially, a human must legally assume the compliance liability for the final decision. But human oversight is only the safety net. The ultimate factor determining a project's success is the construction of a unified, contextualized data foundation. Due to the rapid proliferation of high-quality open-source technology, the AI model itself is no longer a competitive advantage. The algorithm is just a commodity. The actual differentiator is an institution's ability to clean its legacy IT systems and seamlessly integrate its own proprietary, historical data into the model's context window. The banks that do the unglamorous work of mastering their underlying data infrastructure will capture the billions in AI value. The rest will simply pay for rapidly depreciating hardware. A single AI agent can vastly accelerate an engineer's daily output. Logically, you might assume that running 10, 20, or 100 agents simultaneously would make you 100 times faster, but try to force that many independent AIs into a standard coding environment, and the entire workflow collapses. The agents themselves aren't actually failing. The bottleneck is us. The traditional role of a software engineer involves writing and reviewing code, not acting as a middle manager for dozens of reckless, lightning-fast digital employees. We simply lack the innate skill to monitor that much simultaneous action in a standard text editor. To find those missing management skills, we have to look outside of traditional software development. Real-time strategy video games have spent decades training players to comfortably command dozens of individual units across complex digital landscapes. Developer Ido Salomon recognized this overlap. He built Agentcraft, an open-source AI orchestrator explicitly designed to lift the interface mechanics of strategy games and apply them directly to software engineering. Scaling software output to the volume of a massive AI swarm means the human role must shift from an active coder to a fleet commander. The first problem a commander faces is visibility. You cannot direct a fleet if you rely on rapidly scrolling text logs to figure out which specific files your agents are actively changing. This animated diagram demonstrates how Agentcraft solves the tracking problem. It morphs the standard nested directory into a physical, top-down spatial map. Folders become geographic regions, and individual files become interactive visual nodes called runes. By projecting the codebase onto a physical space, the system establishes a clear visual lineage. You can see exactly which agent altered which node, as their actions leave a permanent trail connecting the worker to the work. This spatial layout also allows the orchestrator to track movement in real time. If multiple agents attempt to rewrite the same file, the contested nodes light up in intense red. The system creates a heat map of the codebase, predicting and preventing code collisions before they actually happen. When those collisions trigger a pause, the user can rely on pure gaming muscle memory. Using keyboard shortcuts, they can rapidly cycle between agents that are blocked, quickly answering questions or approving plans to keep the fleet moving. Translating abstract code changes into a physical geography provides actionable intelligence over the entire project, allowing a single person to monitor a volume of work that would overwhelm a standard text-based interface. Even with perfect visibility, a second bottleneck emerges: cognitive overload. A single human can only invent and assign tasks so fast before running out of ideas and energy, leaving dozens of agents sitting idle. Agentcraft addresses this by giving the swarm its own autonomy. Using a feature called quests, agents actively scan the codebase to find low-level maintenance work, like refactoring old functions or writing missing test coverage, and execute it without waiting. For larger objectives, this diagram illustrates the campaign orchestrator in action. The human provides a broad goal. The system takes over, breaking it down into a flowchart of subtasks, dropping them into isolated containers. Agents work freely within those walled environments, requiring zero babysitting. This isolated, containerized approach scales up dramatically. Salomon demonstrated setting up a background cron job that automatically scrapes Twitter for trending product ideas every single day, spins up a fresh container of agents, and has them implement the initial features overnight. Because the orchestrator handles task generation, the human's daily workflow changes. Instead of writing out detailed plans, the user evaluates review bundles. They look at visual evidence, screenshots, and screen recordings generated by the agents to confirm the work is complete. Offloading the decomposition of tasks directly to the orchestrator preserves human cognitive energy. The user reserves their focus strictly for high-level project judgment and final visual approvals. The final hurdle is that AI agents simply aren't entirely self-sufficient yet. Complex, cross-disciplinary campaigns still require direct human intervention to bridge the gaps in the AI's logic. To solve this, the orchestrator introduces shared workspaces. This visualization shows two human specialists, a product designer and an engineer, operating on a single digital canvas. Each human commands their own distinct cluster of AIs. This layout creates a seamless handoff process. The designer can finalize a visual concept, and the resulting specifications are passed directly across the canvas into the engineer's coding agents, immediately initiating the build phase. The system also maintains a continuous chat log for soft collaboration. Agents automatically broadcast notifications about which files they are modifying, keeping human users and other AI swarms aligned on the project state. True multi-agent orchestration involves building a transparent, lateral ecosystem. It allows both human directors and AI nodes to continuously adapt and respond to each other's actions in real time. The speed of software engineering is no longer dictated by how fast a single person can type out a string of code. Scaling our daily output relies entirely on adopting spatial user interfaces, granting secure autonomy to isolated containers, and leaning heavily into lateral collaboration. The individual contributor is stepping back. The optimal human role is now positioned at the center of the workflow, acting as the conductor of a massive AI symphony. Orchestrators like Agentcraft are highly experimental right now, but they prove exactly where the industry is heading and what the daily interface of a developer will soon look like. If you want to dive deeper into building these AI agents and try out hands-on coding, check out the Learn by Doing with Steven YouTube channel and explore his tutorials across all platforms. And for high-level discussions detailing data and AI strategy, listen to the Steven Data Talk podcast. It is available right now on YouTube Music, Spotify, or wherever you get your podcasts. Links are in the description. Engaging with these orchestration paradigms now is a practical step toward commanding tomorrow's automated workflows, rather than being overtaken by the speed of their execution.
Historically, open-source AI forced developers to choose: rent expensive cloud computing to run massive models, or settle for highly constrained, weaker models running locally. Google DeepMind built the Gemma 4 family to bridge this technical gap. Look at this bar chart comparing the flagship Gemma 31B dense model against a massive 600 billion parameter model. The 31 billion parameter model is outperforming systems 20 times its size, securing the number 3 spot on the global AI leaderboard. Competing at that level while keeping the weight low required DeepMind to engineer a complete redesign of the neural architecture. By directly targeting physical computing bottlenecks, they made state-of-the-art multimodal AI completely accessible. And by releasing it under an Apache 2.0 license, everyday developers can deploy it from initial testing all the way through to production. The first major roadblock in modern AI is the immense processing power required to handle huge context windows. The Gemma 431B model features a 256,000 token context length, which demands massive compute to process. DeepMind addressed this by introducing interleaved attention, a 5-to-1 ratio of local to global layers. Local layers use a sliding window, keeping memory light. For the heavier global layers, they grouped 8 queries to share a single key and value head, drastically cutting costs. For developers needing even tighter efficiency, the 26 billion parameter mixture of experts, or MOE model, maximizes capability while minimizing active compute. The MOE architecture replaces standard networks with one shared router operating alongside 128 smaller, specialized experts. During any forward pass, the router only activates 8 of those 128 experts, dropping the active compute down to just 3.8 billion parameters. These twin innovations in attention and expert routing mean developers can run complex, autonomous agentic workflows natively, without the budget of a massive data center. Scaling down to local edge devices like phones and laptops introduces a new physical constraint, the severe lack of VRAM. The Gemma Effective 2B and 4B models are designed specifically for this environment. There's a specific difference between their total representational depth, holding the model's overall knowledge, and the smaller effective parameter count required to operate the model. The main culprit clogging up limited VRAM is usually the massive token embedding tables. These tables map every single vocabulary token to its vector representation. DeepMind's fix is per-layer embeddings. The model maps a distinct 256-dimension embedding for every single layer. Crucially, these per-layer embeddings are stored in standard flash memory. By keeping them out of VRAM, the models avoid the biggest bottleneck on everyday devices. Using flash memory for per-layer embeddings allows high-performance models to run locally and privately on a standard laptop, bypassing expensive cloud API calls. The final bottleneck is perception. Historically, AI vision processing was clunky. Models relied on rigid pan-and-scan methods, forcing images of different sizes into a sequence of fixed squares, and padding whatever was left over. Gemma 4 introduces native variable resolution multimodality. It processes distinct aspect ratios directly, recognizing spatial positions without cropping or distorting the original image. An image is dynamically sliced into grids of 16 by 16 pixel patches. These patches are then pooled together to produce soft tokens, which are linearly projected up into the final embeddings shown to the model. This system gives developers direct control over their soft token budgets. You can allocate high patch counts for complex tasks like optical character recognition, or assign low budgets for simple chat interactions. They also added audio processing directly to the local effective 2B and 4B models. Raw audio runs through a MEL spectrogram, splitting features into chunks that feed directly into a 35 million parameter conformer. Eliminating rigid image processing and integrating native audio allows these models to process complex environmental data directly on mobile hardware.
The JEMA 4 ecosystem represents a cohesive architecture, scaling all the way from the effective 2B for local devices up to the massive 31B dense model. For developers, this creates a seamless workflow. You can prototype heavy function calling and agentic workflows in the cloud via Vertex or AI Studio, and then immediately scale that exact same architecture down to local Hugging Face or Llama deployments. By re-engineering how models handle compute, memory, and perception, DeepMind has established a new capability standard for open-source models at these sizes. To start building your own workflows with JEMA 4, check out the Learn by Doing with Steven YouTube channel and other platforms for hands-on tutorials. And to stay updated on all the latest AI trends, listen to the Steven Data Talk podcast, available on YouTube Music, Spotify, and wherever you get your podcasts. Check the description for links.
If you want an AI agent to actually do something, like check an inbox or configure a server, you have to give it hands. In software, we call this tool calling, letting a language model write a function that executes an action in the real world. At first, developers solve this by manually bundling a handful of specific scripts directly into their local agents. To avoid everyone building the exact same basic integrations over and over, the industry shifted to a standard format, the Model Context Protocol, or MCP. Providers could offer universal access to their entire service through one uniform connection. But as models grew smarter, developers wanted them to do more. They started trying to feed entire API ecosystems into these agents at once, walking right into a massive mathematical trap. Consider a platform like Cloudflare, which operates over 2,600 separate API endpoints. Converting all of Cloudflare's API endpoints into standard agent tools requires roughly 1.1 million tokens. Loading that much data up front instantly exhausts the capacity of the agent's context window. Even the largest foundational models cannot hold that much instruction data at once. To get around this, developers tried splitting massive platforms up into dozens of smaller, product-specific servers. That meant human users had to manually select which narrow server their agent needed at any given time, leaving the AI with incomplete coverage, and proving that agents actually need progressive discovery, the ability to find and load tools dynamically, exclusively when a task requires them. Engineering teams tested a few structural workarounds. One popular method let agents read a system's help commands and execute tasks using a command line interface. The flaw there is that you have to grant an external AI raw shell access to your system. Yet another approach tried keyword-aced tool search. If the user asked an agent to create a new digital worker, the system would find related tools and load a small batch into the agent's memory. But even this was imprecise. This diagram shows how pulling 8 possible tools to guarantee you have the right one still wastes hundreds of tokens on unused adjacent options. Developers eventually realized that prepackaged tools, no matter how efficiently you search for them or deliver them, are inherently rigid and heavy. The real solution came from stripping away the pre-written tools entirely. Instead, developers started feeding the AI incredibly concise TypeScript definitions generated straight from an open API specification. Supplied with just the structural logic, the language model can instantly write its own custom code to query the API exactly how it wants. But running an AI's unverified script directly on your server has historically been treated as a critical security vulnerability. A single bad script could read your private files, exfiltrate protected system secrets, or trigger resource-draining infinite loops. To survive this, engineers are deploying lightweight, programmable sandboxes, like Cloudflare's Dynamic Workers or Pydantic Monty. These isolated environments execute the AI's custom strings in milliseconds while enforcing strict, hard-coded guardrails. You can cut off all external network access with a single Boolean toggle. Enabling agent autonomy requires moving away from static toolkits and towards secure environments where an AI can safely generate its own logic. This shift in cloud architecture is actually a direct echo of how computers operated in the 1950s. Back then, you didn't sit at a terminal and run programs yourself. You wrote out your logic, handed the instructions to a human operator, and they carried it into a massive, heavily isolated room to be processed. Executing those tasks meant physically loading complex, hand-wired instruction panels directly into the mainframe.
Today, AI is taking the role of the user writing the logic, while scalable cloud sandboxes act as the isolated machines carrying out the commands. Generating code allows an agent to chain complex API operations that a static list of tools cannot accommodate. This model of isolated execution is becoming the standard for how agents interact with modern web services. For backend developers, this exacts an immediate toll on infrastructure. APIs must be hardened with aggressive rate-limiting protocols to survive automated loops authored by untiring agents. At the same time, exposing your platform to these agents is getting easier. Heavy, manual integrations will soon be replaced by simple middleware toggles built natively into full-stack frameworks like Next.js. On the client side, applications are shifting towards stateless loops, powered entirely by this kind of programmatic, on-the-fly execution. End users will be able to ask their agent to set up complex tasks, like web scraping, and the AI will generate a custom script, save it as a reusable cron job, and automatically rewrite the code to repair itself if the target website changes. To explore these architectural changes further and get hands-on engineering experience, subscribe to the Learn by Doing with Steven YouTube channel and tune in to the Steven Data Talk podcast on Spotify, YouTube Music, or wherever you get your podcasts. The reality of modern software engineering rarely looks like uninterrupted coding. Instead, developers spend their days buried under administrative weight, rapidly context switching between Slack threads, Jira tickets, Notion docs, and reviewing endless pull requests. The bottleneck here is biological. The human brain operates in a single linear thread, but modern software development is a chaotic, omnidirectional process requiring simultaneous attention across a massive codebase. Because of this mismatch, an AI tool that simply auto-completes your text in an IDE is no longer a complete solution. Predicting the next line of code does nothing to manage the environment you're coding in. To actually scale productivity, developers don't need a slightly faster typing tool. They need an architecture capable of managing the entire engineering environment. OpenAI built Codex as an open software engineering agent. It possesses the autonomy to independently explore file hierarchies, execute terminal commands, and run full test suites without constant human prompting. At the center is a frontier AI model. Surrounding it is a unified agent harness, managing tool execution and security sandboxes. Routing requests through WebSockets with a dedicated fast mode delivers a 1.75x speed increase and twice the tokens with near-zero latency. All of this speed feeds into the native Codex app, which introduces dedicated work trees. This allows a single human developer to spin off multiple branches, interacting with the agent on different features simultaneously, without ever breaking their primary focus. Ultimately, this high-speed, multi-surface architecture provides the exact physical foundation required to build an entirely automated digital engineering team from scratch. The first members of that digital team are the administrative assistants. Codex connects to the outside world through plugins, which bundle specialized skills, external application integrations, and NCP servers into reusable workflows. Because they integrate directly with your existing workspace, these plugins execute highly specific administrative tasks. Codex can read your documentation in Notion, parse YAML files in your codebase, and immediately update a Google Drive spreadsheet to reflect the current state of a project. You can schedule these actions using the Automations feature. Developers set up background cron jobs, instructing Codex to silently triage an overflowing Gmail inbox, or compile summaries of time-sensitive Slack messages every morning at 9 a.m. By successfully offloading this low-level busywork, the human developer reclaims their cognitive bandwidth, preserving their energy for high-level logic and system design. The system isn't limited to text-based administrative logic. Codex ships with highly specific skill bundles built expressly for visual web and game development. Take the Playwright interactive capability. Codex spins up a headless browser, visually scanning the interface of an app to click buttons, navigate menus, and debug UI components entirely on its own. Combine that with the Imagen integration, and Codex can instantly generate 2D sprites and visual assets from raw code instructions, effectively building and rendering a playable platformer from scratch. Codex has effectively erased the friction between writing back-end logic and rendering front-end visual experiences. quality control requires a different level of intelligence. This is where Codex steps in as the ultimate senior engineer, applying elite code review capabilities to every single pull request. To perform these reviews, the model contextualizes your changes against the entire repository, identifying hidden second-order effects in modules you haven't even touched. But the most disruptive capability built into this harness is the deployment of sub-agents. If you ask Codex to review 50 different project personas, the master agent creates a plan. It then spins up dozens of specialized worker agents, partitioning the files so they can execute the review process simultaneously. You dictate exactly how these agents operate. You can lock a cybersecurity scanner into a specific read-only sandbox, while granting another subagent write access so we can file bug reports directly into your linear backlog. True engineering scale isn't achieved by typing faster. It is achieved by executing dozens of distinct, complex lifecycle processes at the exact same moment. Operating an autonomous swarm introduces serious risk. Giving an AI unfettered access to delete directories or expose internal servers to the open internet is known as YOLO mode, and it is inherently unsafe. But the traditional alternative, forcing developers to manually approve every minor AI action, creates massive alert fatigue, dragging the system back down to human speed. The solution is a feature called Guardian Approvals. Codex automatically spins up a dedicated safety subagent, whose sole purpose is to verify if a privileged task requires human intervention or if it is safe to proceed autonomously. Developers can further constrain the machine using hooks, programmatically triggering specific security checks, or pulling repository updates precisely before and after every tool the AI uses. As AI achieves true autonomy, the primary job of the human developer shifts. You are no longer writing individual functions. You are defining the operational and ethical boundaries of the machine. The final frontier of this system is detachment. Developers can now hand off massive asynchronous tasks to cloud agents. These agents run parallel computations in best event scenarios in the background, continuously working while the human completely steps away from the laptop. The era of the software developer as a manual typist is over. You are now the orchestrator of a fully autonomous digital agency. To master these tools, check out the Learn by Doing with Steven YouTube channel and follow across all social platforms. For deep dives into data and architecture, tune in to the Steven Data Talk podcast, available on all major podcast platforms. Links are in the description.
Many developers currently assume that AI coding is a separate discipline, one meant to replace traditional software engineering fundamentals. This assumption drives the specs-to-code fallacy. A developer writes a massive requirements document, feeds it into a large language model, and expects a finished application. The result is almost always the same: unpredictable vibe coding, hallucination loops, and an endless stream of manual corrections. These failures do not happen because the AI lacks intelligence. They happen because the workflow ignores the mathematical constraints of how these models actually process data. To make autonomous coding reliable, we have to enforce proven software engineering limits onto the AI's cognitive processes. Every large language model has a smart zone. For current architectures, this is roughly the first 100,000 tokens of a conversation, where reasoning remains sharp and accurate. This diagram illustrates the technical bottleneck. As you feed the model more code, every new token scales the mathematical relationships quadratically, straining attention. Once past the smart zone, it enters a dumb zone, losing track of instructions, misinterpreting logic, and making baffling decisions. While many try to compress or compact this context to keep the chat going, the more effective method is the memento constraint. You frequently and completely wipe the context clean back to a base state. Clearing the slate forces the agent to reference the actual codebase as its sole source of truth, rather than relying on a degraded conversational memory. Treating the LLM like an amnesiac forces you to architect smaller, tightly scoped, and independently executable tasks. This requires a separation of concerns. The human developer handles the day shift, the architectural planning logic, leaving the execution to the agent. During this day shift, the primary alignment tool is the Grill Me protocol. You hand the AI a raw client brief,
But instead of asking for code, you instruct the AI to relentlessly interview you. This forces the model to walk down every branch of the design tree, exposing edge cases, hidden assumptions, and implicit technical dependencies. Standard prompting rushes to an output. The Grill Me protocol is designed strictly to reach a flawless, shared design concept between the human expert and the agent. This rigorous alignment on the front end is the only way to prevent compounding logical errors once the autonomous execution phase begins. Once alignment is reached, the output is a highly specific product requirements document. This serves as the final destination for the build. To make this machine readable, we break the PRD down into a directed acyclic graph, mapping out strict chronological blocking relationships. This structure translates a linear project into a series of independently grabbable issues. Knotting out exactly which tasks do and do not block each other is the prerequisite for deploying multiple AI agents in parallel. Converting requirements into a mathematical graph allows a team to scale from a single AI assistant to an automated engineering workforce. When executing these tasks, agents naturally attempt to code horizontally. They will write an entire database schema before ever touching the API layer. Executing layer by layer isolates the code from end-to-end integration testing until the very end of the project lifecycle. To solve this, we apply vertical slices, historically known as tracer bullets. A vertical slice is a single minimal feature, like awarding a user a point, that slices through the database, backend, and frontend simultaneously. Because it touches every layer, a vertical slice provides the agent with immediate, verifiable feedback the moment a task concludes. This instant integration feedback is the only mechanism that truly prevents an isolated agent from coding completely blind. The agent relies on this feedback through test-driven development, operating in a strict red-green refactor loop. But AI-driven testing breaks down when faced with shallow modules. Shallow modules are tiny files that export single functions. They create ambiguous, overlapping boundaries that make it impossible for an LLM to determine what it should actually be testing. When boundaries are ambiguous, the AI will cheat. It will write tests that mock internal logic, rather than verifying real-world outcomes. We solve this by implementing Ousterhout's deep modules. You design a broad, simple interface that encapsulates complex internal logic. You cannot expect deterministic, high-level AI performance inside a software architecture that prevents rigorous testing. Once the day shift planning is mapped, human involvement ceases, and the night shift, the away-from-keyboard execution loop, begins. Individual vertical slices are assigned to parallel AI agents, each running in their own isolated Docker containers. Because you establish deep module boundaries, each agent can run its own aggressive TDD loops without corrupting the main codebase. Code is only integrated back into the main branch after passing an automated peer review. This parallel coding loop is only possible because of the architectural and planning constraints established during the day shift. The complete workflow relies on 4 specific pillars: Grill Me alignment, a DAG Kanban, vertical slices, and deep module TDD. The software engineer hasn't been replaced. The role has simply moved up the abstraction stack from writing syntax to designing systems. Bad codebases make bad agents. AI efficacy relies entirely on enforcing strict engineering limits. To learn the practical frameworks for implementing these workflows, subscribe to the Learn by Doing with Steven YouTube channel. And for deep dive technical discussions on agentic architecture, follow the Steven Data Talk podcast on all audio platforms.
Right now, if you ask someone what artificial intelligence does, they'll likely point to a chatbot. Text generation and large language models are currently dominating the cultural conversation. But language models have a specific constraint. They can write a convincing essay about a bouncing ball, but they do not natively understand gravity, spatial logic, or the physical chaos of the real world. Inside Google DeepMind, VP Raya Hadsell oversees 1,200 scientists working to push past that constraint. Her team's mandate is to ignore superficial applications and aims strictly for root nodes,
the deepest, most stubbornly unsolvable problems in machine intelligence. DeepMind is building systems that can accurately perceive physical reality, predict chaotic planetary events, and generate entirely new, interactive universes from scratch. In neuroscience, there's an interesting discovery known as the Jennifer Aniston cell. It refers to a single human neuron that fires reliably whether you look at a photograph of her face, read her name on a page, or hear her speaking voice. DeepMind engineers recreated that biological fast retrieval system for machines. This diagram outlines what they call embedding models. The system takes wildly different data types, like an audio wave, a block of text, and a photograph, and translates them all down into a single unified mathematical point. The newest version of this architecture, Gemini Embedded 2, handles an extreme volume of information. It can compress massive inputs, swallowing up to 128 seconds of video, 80 seconds of audio, and an entire PDF document, squeezing it all into one dense mathematical vector, without losing the core meaning. To make that dense point useful, the system uses Matryoshka representation learning. Like a nested doll, that single data point can scale up, expanding its dimensions outward to achieve peak expressiveness exactly when the system needs to pull detailed information back out. Because of this architectural leap, AI can instantly retrieve and compare complex concepts in one step, operating much closer to how the human brain actually processes the world. Once a system can natively perceive concepts, the scale expands toward the planet's most chaotic systems. DeepMind targeted the Earth's atmosphere, a challenge that even the UK Met Office once considered a frontier too difficult for AI. This 3D wireframe illustrates GraphCast. Instead of relying on mechanical physics equations, they mapped 40 years of global atmospheric data onto a dense mesh of interconnected nodes extending from the Earth's surface straight into the stratosphere. In late 2024, GraphCast used that data to predict the exact landfall location of Hurricane Lee 9 days in advance. For comparison, the gold standard physics models only managed to accurately predict it 6 days out. To push the science further, the team built GenCast. Because weather has highly chaotic extremes, GenCast was designed to be probabilistic, specifically mapping those unpredictable atmospheric tails. It now compresses a forecast that used to require hours on a massive supercomputer into an 8-minute process on a single chip. Their latest iteration, the Functional Generative Network, directly categorizes cyclone trajectories and eye formations natively within the network. It's so accurate that the U.S. National Hurricane Center is already using it in the field. By treating chaotic physical systems as massive data patterns rather than purely mechanical math problems, the team managed to tame one of the most volatile forces on the planet. But predicting reality is only the build-up to generating it. DeepMind has a long history of using closed-environment video games to teach AI spatial agency and logic. That research evolved into world models, systems capable of infinite simulation. They started with Genie 1, which generated basic, seconds-long 2D platformers, and then scaled up to Genie 2, which produced slow, interactive 3D environments. Genie 3 generates photorealistic, real-world physical locations in real time, like this view of a canal lock, and it allows users to move through them, watching the system accurately simulate interactive physics like rippling water. Crucially, these generated spaces have structural permanence. In an internal test featuring an origami lizard, a user can walk forward through the landscape, turn around, and retrace their steps. The AI perfectly remembers the exact structural layout of the world it just invented. Because the entire environment is being generated live, users can engage in adversarial dynamic prompting. While moving through a peaceful forest, you can command the environment to instantly glitch and morph into a neon-lit cityscape without breaking forward momentum. This means AI has transitioned from observing our reality to authoring it, providing the technical basis for high-fidelity simulation and educational tools. Artificial intelligence is expanding from the manipulation of text into the direct simulation of our physical environment. Through omnimodal embeddings that perceive concepts, planetary-scale models that predict meteorology, and real-time world generation, these systems are becoming a mirror to our universe and an engine for creating new ones. To experiment with these root nodes and see how this all works in practice, check out the Learn by Doing with Steven YouTube channel and tune in to the Steven Data Talk podcast on YouTube Music and Spotify for deeper conversations on data.
Every week, a new headline claims an AI has passed the bar exam or mastered the medical boards. Watching this play out, it's easy to feel like artificial general intelligence is practically knocking on the door. And if you look at the official data, that anxiety makes sense. This is what we are constantly shown, an unbroken barrage of charts where the line simply goes up, mapping a flawless trajectory of machine capability. But then you try to use one of these cutting-edge models to organize a spreadsheet or draft a simple email, and it confidently misses the entire point of the task. When our daily experience feels this buggy while the official charts look perfect, it points to an uncomfortable reality. Those benchmarks might be measuring the wrong type of intelligence entirely. To figure out where the measurements are failing, AI researcher Peter Gostov created something he calls the bullshit benchmark. It's a test specifically designed to see how models handle highly technical but completely nonsensical questions. For example, you ask the AI, "Controlling for repository age, how do you attribute variance in deployment frequency to the indentation style of the codebase versus the average variable name length?" It's total gibberish. But instead of flagging the prompt as a prank, top-tier models from OpenAI and Google readily accept the absurd premise. They dive right in and fabricate complex, technical-sounding answers to a correlation that simply doesn't exist. An AI capable of passing a graduate-level exam completely lacks the basic human common sense required to reject a flawed premise. So why does an exponentially powerful computing system fall for obvious nonsense? You might think the solution is to give the AI more time to think. But the data reveals a counterintuitive reasoning paradox. Giving a model more reasoning compute actually makes it perform worse on the bullshit benchmark. These systems are hyper-optimized to be helpful problem solvers. When faced with a nonsense prompt, extra reasoning power doesn't help them realize the task is impossible. Instead, it causes them to spend 20 paragraphs frantically trying to rationalize the absurd, working harder and harder to solve a problem that shouldn't be solved. We haven't actually built independent thinkers. We've built extreme yes-men that prioritize task completion and compliance over objective truth. To see how this vulnerability plays out at scale, we have to look past narrow diagnostic tests and turn to the LMSS chatbot arena. This dataset captures over 5.5 million real human-judged interactions. This chart tracks the dissatisfaction rate, the exact percentage of time human judges decide that both top-tier models they tested provided a terrible answer. Over the last year, you can see that rate steadily dropping to sit right around 9%. Hitting a single-digit failure rate across millions of random user prompts is a massive technical achievement. But watch what happens when we filter this data strictly for expert prompts, the high-level professional tasks. The single-line splinters, revealing a stark divide in performance. For quantitative fields, the progress is undeniable. The line for advanced math and physics plummets toward the bottom of the chart, as models get dramatically better at these rigid, rules-based calculations. But look at the top of the chart. Expert prompts related to law, finance, and gaming remain stubbornly flat. In these qualitative fields, there is almost no improvement over time. Take game design as the ultimate example. A modern AI can flawlessly write the code for a platformer, but if you ask it to design the game mechanics, the results are boring and disjointed. It has no intrinsic understanding of what actually makes a game fun or challenging. These models thrive in environments with clear mathematical guardrails, but they struggle to interpret the fuzzy, subjective reality of human judgment. This reveals the core disconnect between passing an AI benchmark and performing actual white-collar work. Real-world work is inherently fuzzy. Instructions are poorly specified, priorities shift, and being effective constantly requires an employee to push back on bad ideas or faulty premises. To achieve true utility, developers must prioritize the bottom of the distribution. Building models that understand context and logic is now more vital than simply pushing the absolute frontier of narrow intelligence.
the flawless charts are a distraction from a deeper missing requirement. Solving a complex equation is a matter of computation. Genuine intelligence requires the wisdom to identify a flawed premise and stop before the work even begins. If you want to move past the hype and start mastering these tools practically, you need to check out the Learn by Doing with Steven YouTube channel for hands-on, project-based tutorials. And for deeper industry analysis, listen to the Steven Deva Talk podcast, available on YouTube Music, Spotify, and all major platforms. You can find all the links right down in the description.
E se mi dicessi che l'atto stesso di scrivere codice, riga per riga, sta per diventare obsoleto? Benvenuti! Oggi ci tuffiamo in un'idea a dir poco radicale, che arriva direttamente da Ryan Lopolo di OpenAI e che sta di fatto ribaltando il mondo dello sviluppo software. Preparatevi perché stiamo per scoprire come l'ingegnere non è più un semplice artigiano, ma diventa un vero e proprio direttore d'orchestra, che guida una sinfonia suonata dall'intelligenza artificiale.
Allora, partiamo da questa frase che, diciamocelo, è una vera e propria bomba. Il codice è gratis. Ma che cosa vuol dire? Beh, significa che la risorsa che per decenni è stata la più preziosa e costosa nello sviluppo software, cioè il tempo di un essere umano per scrivere codice, è di colpo diventata abbondante. Praticamente l'intera economia del settore è stata messa sottosopra.
Immaginate la scena, un singolo ingegnere che invece di sudare su ogni riga di codice si trova a comandare un'intera armata di instancabili programmatori AI che lavorano per lui, 24 ore su 24. L'unico vero limite a questo punto non è più il tempo o l'abilità, ma la potenza di calcolo che si ha a disposizione. Scrivere codice, insomma, è diventato una commodity, una cosa che si dà quasi per scontata.
Ok, tutto molto bello, ma se il codice non è più il problema, allora qual è la nuova risorsa scarsa? In ogni sistema c'è sempre un collo di bottiglia, giusto? Se abbiamo appena eliminato quello vecchio, dove si è andato a formare quello nuovo? Credetemi, la risposta a questa domanda sta riscrivendo le regole del gioco nel mondo della tecnologia. Guardate qui, il cambiamento è epocale. Ieri la risorsa scarsa era il tempo degli ingegneri. Oggi le cose che contano davvero, quelle limitate, sono tre. Primo, l'attenzione umana, cioè la nostra capacità di dare la direzione giusta. Secondo, l'attenzione delle IA, per evitare che si perda per strada. E terzo, forse il più importante, la finestra di contesto. Che cos'è? Immaginate di poter dare istruzioni a un genio, ma solo scrivendo su un post-it. Ecco, quella è la finestra di contesto, e quello spazio vale oro.
Di fronte a uno scenario del genere è ovvio che il ruolo dell'ingegnere debba evolversi, e anche parecchio. Si passa dall'essere l'artigiano meticoloso che lavora al pezzo a diventare un architetto, uno stratega. Vediamo un po' che cosa significa nella pratica.
In pratica le responsabilità si spostano dal fare al progettare. L'ingegnere diventa la persona che disegna la mappa, cioè l'architettura. È quello che scrive le leggi, ovvero le regole di sicurezza e affidabilità. Poi affida il lavoro di costruzione agli agenti AI e interviene come un risolutore di problemi di alto livello solo, e sottolineo solo, quando l'automazione si inceppa. E questo è il vero cambio di mentalità. L'obiettivo non è più scrivere il codice perfetto. No, l'obiettivo è costruire un sistema che permetta alle AI di scriverlo al posto nostro. Il valore di un ingegnere non si misurerà più in righe di codice scritte, ma nella sua capacità di orchestrare e dirigere l'intelligenza artificiale.
Tutto questo è affascinante, ma nella pratica, come si fa a guidare questi agenti AI?
Beh, la risposta sta in un concetto chiave chiamato harness, che potremmo tradurre come imbracatura, o forse ancora meglio come un sistema di guida. Vediamo un po' di cosa si tratta. La domanda è tutta qui. È un po' come avere un pilota di Formula 1 dal talento incredibile, ma ben dato. Non è che puoi dirgli semplicemente vai veloce. Devi costruirgli una pista, con i guardrail, le curve, i segnali che lo guidino in autonomia fino al traguardo. Ecco, l'harness engineering fa proprio questo. E qui c'è la genialata. La soluzione è trasformare ogni singola cosa con cui l'AI interagisce in un'istruzione. L'intero ambiente di sviluppo diventa in pratica un mega prompt continuo. Un messaggio di errore non è più un problema, è un'istruzione. La struttura delle cartelle non è solo ordine, è un'istruzione. Ogni test è una guida. L'AI viene costantemente indirizzata e scolpito dal contesto che noi abbiamo creato per lei.
Ed ecco la definizione ufficiale. L'harness engineering non riguarda la scrittura di codice. ma la progettazione di contesti. È l'arte di rendere il nostro ambiente di lavoro, diciamo, intelligibile per una macchina, in modo che possa navigarlo da sola e produrre risultati eccellenti senza che noi dobbiamo intervenire di continuo. E questa, tenetela bene a mente, è la regola d'oro. Ogni volta che un essere umano deve intervenire per correggere una virgola o sbloccare la I, non è un fallimento della I, è un fallimento del nostro harness, della nostra imbracatura. L'obiettivo non è la perfezione della gente, ma la perfezione del sistema di guida che gli abbiamo costruito attorno.
Ma alla fine della fiera, dove ci porta tutto questo? Qual è il futuro che questa nuova filosofia sta costruendo? La risposta si può riassumere in una sola parola: autonomia.
Provate a immaginare non un singolo agente, ma interi team di intelligenze artificiali che non si limitano a scrivere codice, ma che fanno evolvere prodotti interi, 24 ore su 24, 7 giorni su 7. Gli unici input umani? Gli obiettivi di business, le metriche da ottimizzare e il budget. Gli ingegneri non gestiscono più il codice, gestiscono il valore, definiscono la visione e le macchine la trasformano in realtà.
Questo nuovo mondo è affascinante e sta nascendo proprio ora, sotto i nostri occhi. Quindi, per chi volesse approfondire e continuare a seguire gli sviluppi in questo campo, ci sono un sacco di ottime risorse in giro.
Questo è solo l'inizio e tutto si sta evolvendo a una velocità incredibile. Se volete continuare a esplorare queste idee rivoluzionarie, vi consiglio di seguire canali come Learn by Doing with Steven, Steven Data Talk e Steven Shujiman Tan. Ci trovate su YouTube, Spotify e molte altre piattaforme social. Per facilitarvi le cose, trovate tutti i link raccolti nel mio Linktree in descrizione. Alla fine, questa analisi ci lascia con una domanda enorme, no? Se le macchine si occuperanno del come costruire, quale diventerà la nostra responsabilità più grande nel decidere cosa costruire? Grazie per aver seguito.
At 10 a.m., an engineering team ships a new feature. By noon, they have the A/B test results. Because the data shows the feature is underperforming, they kill it by 3 p.m. and ship a better version by 5 p.m. This entire cycle now happens in a single workday because 99% of the code is generated by AI. 3 months ago, this same sequence would have required 6 weeks of planning and manual development. Most teams attempt to reach this speed by adding tools like Copilot to their existing workflow, but a true AI-first approach starts with a different question. Instead of asking how AI can help an engineer, you ask how to structure a process where AI does the building while the engineer provides the direction. This is a necessary distinction for production-grade software. While vibe coding, or prompting an AI until something works, can produce a prototype, a professional system requires a structure that can guarantee security and stability even when a human isn't writing the lines. Reaching that level of secure, high-speed deployment requires moving past the traditional development lifecycle and replacing it with something designed for agents. The first problem is the timeline of the decision-makers. Traditional product management operates in weeks of research and specification, but when the actual build time collapses from months to hours, a multi-week planning phase becomes the primary constraint on the system. Quality assurance creates a similar drag. If an agent builds a feature in 2 hours, but the manual testing process requires 3 days to sign off on corner cases, the speed of the AI becomes irrelevant to the actual release date. This friction is why teams are turning to harness engineering. Under this philosophy, an engineer's job is no longer focused on the act of writing code, but on building the systems and environments that allow AI agents to work safely. The mechanic of this pipeline is simple. If any single phase of the process remains manual, the entire workflow is restricted to human speed. Building this harness starts with a total reorganization of the codebase, moving away from fragmented, independent systems. AI agents struggle to reason about cross-service implications if they can't see the whole picture. By pulling everything into a unified monorepo, the entire system becomes legible to the agent, allowing it to inspect, validate, and modify code with full context. In the first phase of this workflow, a human architect defines the task. Instead of writing code, they provide a structured prompt that includes the code-based context, the specific goals, and the technical constraints. The agent then takes over phase 2. It decomposes the human architect's task, plans the implementation, writes the code, and generates its own testing protocols to verify its work. The human architect acts as the navigator, while the AI functions as the engine that handles the high-volume labor of implementation. Once the code is written, it enters a deterministic 6-phase pipeline. Every change is subjected to rigorous type checking, linting, and automated end-to-end tests without any manual overrides. To maintain speed, 3 parallel AI models act as automated review gates. They simultaneously scan the new code for quality issues, security vulnerabilities, and dependency risks, catching errors that a human might miss at this volume. A human operator handles phase 4, reviewing the code purely for strategic risk rather than syntax. Because the AI has handled the line-by-line validation, the operator can safely clear the code for production. But even with these gates, errors can still reach the live environment. To handle this, the harness includes a self-healing loop. When an error is detected in production, a triage engine automatically clusters the data, scores the severity, and generates an investigation ticket. It provides the engineer with the exact logs and a suggested path for the fix. The human validates the ticket, the AI pushes the fix through the pipeline, and the triage system verifies the resolution before auto-closing the issue. By automating the detection, diagnosis, and verification of bugs, a small team safely deploys software 8 times a day without being overwhelmed by technical debt. This engineering speed forces a change in every other department. If engineering ships in hours, but marketing or analytics still take days to respond, those departments become the new constraints on the company's growth. Within engineering teams, the transition is often led by junior developers. Because they haven't spent years perfecting traditional workflows, they often adapt to using AI-native tools more quickly than those with established habits. Senior engineers often face a more difficult shift. When an AI can complete 2 months of traditional manual coding in a single hour, the value of years spent mastering specific syntax is largely neutralized. The technical moat they spent a career building can now be crossed in minutes. In this environment, a worker's ability to abandon old routines is a more valuable asset than the accumulation of traditional technical skills. An engineer's core value is moving from the volume of code they output to the quality of the decisions they make. Success now depends on critical thinking, evaluating an AI's logic, spotting architectural failure modes, and defining high-quality design. In a world where AI writes the code, your competitive advantage is your ability to critically evaluate systems, master new architectures, and continuously learn. To build those exact skills, you need to check out the Learn by Doing with Steven YouTube channel. It's packed with hands-on tutorials that help you put these concepts into practice. You can find it on YouTube and across other video platforms. And if you want to dive deeper into the data and trends driving the AI-first world while you're on the go, tune in to the Steven Data Talk podcast. It's available right now on YouTube Music, Spotify, and wherever else you get your podcasts. Links are in the description below. Go subscribe, keep learning, and we'll see you in the next episode. The future isn't about competing with the machine's speed. It's about developing the judgment to direct it. You ask an AI agent to execute a complex engineering task. It begins processing, encounters a requirement requiring highly specific localized knowledge, and abruptly halts. The base model lacks the context of your specific environment. To bridge the gap between a base model's general intelligence and a team's highly specific workflow preferences, we use skills. These are essential extension points that plug directly into the agent. This diagram illustrates the professional trap. Developers try to build these skills by writing massive, monolithic text prompts. The single document block expands rapidly until it hits the boundaries of the context window, saturating the agent's memory and crashing the process. Fixing this requires abandoning text prompts entirely. Instead, developers must architect extensible software modules. This modular approach relies on a strict 3-stage engineering pipeline: architecture, instruction design, and evaluation. Treating agent skills as a structured engineering pipeline allows you to scale AI capabilities upward without degrading the base model's performance and memory capacity. The first phase of this pipeline establishes the physical architecture and the trigger mechanisms. An agent skill branches from a root folder into a skill.md file and optional folders for scripts, references, and assets. Skill.md splits into the front matter trigger and the instruction body. Auxiliary folders separate the logic: code in scripts, documentation in references, templates in assets. This architecture serves 2 categories of skills: Capability skills bridge temporary gaps in the base model, like PDF form filling. Preference skills are durable components that encode your team's specific code review workflows. Dumping all this logic into a single file instantly bloats the context window. Separating it into distinct folders enables context-lazy loading. This shows sequential loading. Skill.md front matter is always loaded. The body loads after the trigger fires. Reference files load strictly on demand. If a reference document exceeds 500 lines, it requires a table of contents with line hints, ensuring efficient navigation without scanning unnecessary text. The front matter description operates as the trigger mechanism for this entire layered architecture. This layout compares a vague trigger with an actionable one. A description like API helper leaves the agent guessing. The correct approach clearly defines the what and the when, specifying its use for text generation or multi-turn chat via the Gemini API. By structuring a skill as a lazy loaded file system with precise triggers, the agent holds only the exact instructions it needs at any given millisecond. This drastically reduces context bloat. With the architecture established, Phase 2 addresses instruction engineering, specifically the markdown written in the body of the skill.md file. Agents require gap-filling directives. Providing them with comprehensive essays or trivial context slows down their processing and degrades their performance. Leading with a brief 5-line code snippet is highly effective. When you do establish a rule, explain the why behind it. This teaches the model to generalize beyond specific memorized test cases. The procedural trap happens when developers dictate rigid, step-by-step instructions. If the path breaks, the sequence fails. Dictating exact sequences removes adaptability. The solution is declarative framing.
By stating the end goal, the agent dynamically navigates around obstacles to reach the target. Instead of a procedural command detailing how to find a text string, use a declarative goal. Update the database port to the user's specified value. Developers must provide constraints. Set strict boundaries like always run tests before opening a pull request. There is a hard engineering rule here. If exact sequential execution is truly mandatory for a task to complete, you should write a traditional script, not an LLM skill. It is equally critical to define negative cases. You must explicitly state when a skill should not fire. A broad description like use for any coding task causes request hijacking. The skill will constantly override base logic, even on completely unrelated tasks. Using declarative constraints rather than procedural steps leverages the LLM's natural reasoning capabilities. This creates resilient workflows that recover from edge cases where traditional logic would simply crash. The final phase of the pipeline ensures these modules function safely at scale, evaluation and lifecycle management. Because agent outputs are non-deterministic, a single pass-fail unit test provides zero statistical value. This graph maps an evaluation framework. You need 10 to 20 distinct prompts covering positive triggers, negative constraints, and edge cases. Execute 3 to 5 separate trials per prompt. Over multiple runs, a distribution pattern emerges, revealing the true variance of the model's behavior. When grading these trials, evaluate the final outcome. Confirm whether the code compiles or the proper API is called, rather than restricting the specific reasoning path the agent took. Each trial must be isolated in a clean testing environment. Allowing context to bleed between runs masks real failures. Once a skill enters production, it begins a lifecycle. Capability skills, in particular, have a natural shelf life. As organizations deploy newer, more advanced base models, the specific logic gaps those skills were built to patch will close. You handle this with a deprecation test. Periodically run evaluations without the skill active. If the base model passes the test natively, retire the skill. Evaluating statistically prevents brittle overfitting. It guarantees the skill is robust across thousands of unpredictable invocations and provides a clear metric for sunsetting the logic when it is no longer needed. This full system flow represents the structural transition from monolithic prompt writing to a rigorous pipeline. Modular folder architecture feeding into declarative constraints and filtering through statistical evaluation. Mastering architecture, declarative instructions, and statistical evaluation maximizes agent adaptability across complex tasks. Building agent extensions is not about hacking prompts.
It is about architecting resilient software systems that harness non-deterministic intelligence safely. Expand your practical, hands-on application of these methodologies by visiting the Learn by Doing with Stephen YouTube channel. And to explore the deeper theoretical frameworks behind agentic workflows, check out the Stephen Data Talk podcast, available on YouTube Music, Spotify, and major podcast platforms. The difference between a fragile AI experiment and a production-grade enterprise agent lies entirely in the engineering discipline applied to its skills. If we look at the corporate landscape since 2022, we see a massive outward flow of data. Generative AI has sprinted from basic coding autocomplete tools to complex RAG architectures. RAG, or Retrieval Augmented Generation, is a technique that retrieves information from an organization's private documents to improve an AI's responses. To build these applications, engineering teams have historically taken the path of least resistance. They write their code, and then they connect it directly to external public APIs hosted by major AI providers. This split flowchart illustrates the hidden cost of that convenience. Every time a prompt is fired off, organizations are sending out two critical assets simultaneously: their raw capital, in the form of API token costs, and their proprietary data. By stacking enterprise workflows on top of these public APIs, companies fail to build an internal capability. They remain reliant on rented infrastructure, paying a premium to outsource their intelligence. But the financial cost is only half the problem. Let's look inside a typical development team that has hard-coded their entire application around a specific version of a third-party AI model. External vendors frequently release new models, and when they do, they routinely deprecate older versions without any prior warning. Notice what happens in this pipeline block diagram. When version 5 is suddenly pulled out and replaced with version 6, the underlying prompt templates often break. The model's behavior shifts, and developers are forced into a frantic cycle of downstream repairs just to keep the application running. If that team operates in healthcare or financial services, the stakes are even higher. These industries handle PII, or personally identifying information, which includes sensitive data like social security numbers or medical records. Transmitting PII to an external server invites serious regulatory scrutiny and massive data breach risks. Routing core workflows through third-party servers creates a persistent security and compliance liability for sensitive enterprise data. To fix this, we have to rethink how AI is deployed. Here is a blueprint for a completely closed-loop digital fortress. This represents Models as a Service, or MAS, an architectural framework that allows organizations to become their own private AI providers. Let's build this from the ground up. The base layer manages orchestration and compute, pulling together all your isolated on-premise CPUs, cloud GPUs, and edge devices into one unified grid. Using open-source orchestration technologies like Kubernetes, a system for automating the deployment and scaling of containerized applications, this layer dynamically allocates hardware resources exactly where and when the AI workloads need them. The next structural block drops into place: the AI platform. This layer houses inference engines, which act as the operating system for the AI, slotting individual large language models into place like modular batteries. By isolating models this way, companies can treat open-source AI exactly like traditional microservices. IT teams gain total independent control over which model versions are deployed, when they are updated, and how their life cycles are managed. These two foundational layers effectively cut the cord. They physically decouple an organization's AI capabilities from external hardware constraints and unpredictable vendor deprecation cycles. Now that we have the compute engines running securely, we have to look at the perimeter. How do internal developers and end users actually interface safely with this localized compute power? This is where the API gateway comes in. It sits right on top of our AI platform, acting as a mandatory toll booth between the internal models and any user requests. The gateway enforces strict cost control by rate limiting incoming requests. It carefully monitors and tracks the precise amount of GPU utilization each internal team consumes, ensuring computing costs stay predictable. It also creates an air-gapped authentication barrier. Unauthorized requests are immediately rejected at the border, while verified internal traffic is seamlessly and securely routed directly to the isolated models. To complete the perimeter, we install observability tools. Observability is the practice of measuring a system's internal state based on the data it generates, like logs and traces. These act like internal security cameras, letting engineers trace the exact logic paths and database calls the AI makes within the closed environment. By wrapping the models in an API gateway and observability tools, you transform raw, chaotic compute power into a deeply secure, highly auditable, and financially predictable enterprise utility. Let's look at the finished product. We now have a fully functional models-as-a-service ecosystem operating entirely within the organization's own walls, physically severed from the public internet. From this central command, an IT team can securely serve multiple specialized LLMs to various internal departments through a single unified API. An LLM, or large language model, is a type of AI designed to understand and generate human text based on massive amounts of training data. The operational benefit is total freedom. Internal teams can now build highly advanced agentic AI applications, systems where AI models autonomously call external tools and databases to complete complex tasks, using heavily regulated PII, without ever broadcasting a single byte to an external server. Adopting models as a service establishes generative AI as sovereign corporate infrastructure. It ensures an organization maintains permanent internal control over its operational costs, its data, and its long-term development path. In dynamical systems theory, world evolution follows a precise mathematical logic known as a Markov decision process. An action is taken, which alters an underlying latent state. That latent state then emits what we actually see, the visual observation. Modern video generation models attempt to shortcut this entirely. Instead of calculating that hidden state, they rely on mapping actions directly to pixel-level changes, based purely on a text prompt. Without an explicit state anchoring the scene, the model relies on surface-level visual patterns. Over a long time horizon, tiny pixel errors accumulate, physics begin to drift, and the model eventually hallucinates, losing track of where objects are or what condition they are in. To build a truly generative action role-playing game, painting plausible pixels is insufficient. The model must compute the underlying physical consistency of the world before it renders a single frame. Consider the act of firing a weapon. The action shoot alters a hidden state, the remaining ammunition count. If a world model only understands the visual pairing of pulling a trigger and a muzzle flash, it will continue rendering fire and projectiles even when the gun is completely empty, entirely missing the underlying mechanical click. Solving this requires a substantial engineering pivot. Wild World is the solution designed to explicitly decouple the underlying state from the visual observation in the training data. The dataset consists of over 108 million clean, annotated frames captured directly from the AAA action role-playing game Monster Hunter Wilds. Within those 108 million frames, the researchers cataloged an extensive catalog of over 450 distinct player and NPC actions, from evasive rolls to heavy attacks, all perfectly synchronized with their explicit per-frame world states. By capturing both the mathematical reality and the visual output simultaneously, Wild World provides the necessary bridge to evolve from simple video generation to true interactive world modeling. To capture this dual reality, the research team engineered a custom data acquisition platform that splits the game's architecture in two. They isolated the game engine, which continuously calculates the true mathematical state, from the rendering pipeline, which simply draws the visuals. On the rendering side, the pipeline records the raw visual output. They deliberately disabled late-stage shaders to strip away all heads-up display elements, producing clean, unobstructed gameplay frames. Simultaneously, the engine side records the hidden mathematical data. It tracks exact 3D spatial trajectories, velocities, and the precise skeletal poses of both the player and the monsters. The density of this capture is extreme. For every single frame of those 108 million, the platform logs exactly 119 columns of data. This includes XYZ locations, rotational quaternions, camera extrinsics, and internal attributes like health pools and cooldown statistics. This paired architecture means every visual observation is firmly anchored to its true latent state, providing a mathematically perfect ground truth for machine learning models. Capturing 108 million diverse, high-fidelity frames of action combat presents an immediate logistical wall. Human gameplay cannot physically scale to this level of output. To achieve scale without human intervention, the team utilized the game's native behavior tree AI. They automated teams of NPC companions and unleashed them into unscripted, highly stochastic combat scenarios against large monsters. Because AI-controlled combat can result in chaotic viewing angles, they co-opted the engine's built-in target lock camera system. This ensured the framing remained stable and visually coherent while the automated characters fought. The resulting raw data then passed through a rigorous algorithmic filtering pipeline. Crucially, a temporal continuity filter analyzed the exact timestamps of the state records, immediately dropping any sequence where the frame gap exceeded 50 milliseconds to eliminate microstutters. They applied additional heuristics to discard frames where the camera was occluded by level geometry, or where extreme lighting conditions caused prolonged overexposure or darkness. Relying on behavior tree automation and aggressive algorithmic filtering generated a dataset that is both massive in its scale and chemically pure for training diffusion models. The final layer of the Wild World pipeline applies text-based metadata, creating hierarchical captions that translate the raw telemetry into language that text-to-video models can process. They fed sampled frames into the Qwen3VL vision language model. To prevent the model from hallucinating the context, they hard-coded the exact state metadata directly into the prompt as a factual anchor. This forces the caption to include hyper-granular details. The resulting text explicitly defines the player type ID, the exact weapon ID in use, precise fractional HP values down to the decimal, and absolute rotational quaternions. These charts display the dataset's statistical composition. A pie chart shows a 66 to 34% split between combat and traversal. Beside it, a bar chart reveals a long-tail distribution across the top 150 actions, ensuring rare, complex interactions are captured alongside common movements. This multimodal annotation takes unstructured, chaotic gameplay and turns it into a highly structured pedagogical tool, explicitly teaching diffusion models the rules of a physical environment. With the data secured, the researchers turned to how we actually test these models, challenging the current industry standard by exposing what we can call the V-bench illusion. Traditional evaluation pipelines rely heavily on metrics like motion smoothness and aesthetic quality, but modern generation models are already saturating these tests, regularly scoring over 95% across the board. A high aesthetic score simply means the video looks pretty. It is entirely useless for determining if a model adheres to physical laws or accurately responding to a user's control inputs over time. To fix this, the team introduced WildBench. It is a purpose-built evaluation framework derived from the Wild World dataset, designed strictly to test interactive fidelity rather than surface-level beauty. WildBench benchmarks the model's ability to act like a real world. This standard identifies failures in physics and logic that aesthetic scores have completely ignored. To answer that, WildBench relies on two critical new metrics: action following to track input accuracy, and state alignment to measure physical consistency. For state alignment, the framework uses an algorithm called TapNext to track 2D skeletal trajectories directly in the generated video, checking those output coordinates against the mathematically perfect ground truth recorded from the game engine. This table breaks down the resulting paradox. Looking at a baseline model like WAN 2.2, it scores near perfect on visual dynamic degree, but looking at the actual physics, it fails drastically, scoring a mere 11.29 on state alignment. However, when models are explicitly fine-tuned using Wild World state data, the physical metrics surge. Models conditioned on camera and skeletal data saw massive improvements, nearly doubling their accuracy in following actions and aligning states. But the data reveals a severe trade-off. The models that utilized explicit state conditioning to improve their physics suffered a noticeable corresponding drop in raw image quality and aesthetic scores. The experimental results confirm that the field is currently deadlocked in a zero-sum game. Right now, architectures are forced to prioritize either strict physical accuracy or high-fidelity pixel aesthetics. They struggle to achieve both simultaneously.
Achieving true long-horizon interactive world models requires an explicit state architecture, moving past the brute force generation of isolated pixels. The 108 million annotated frames inside the Wild World dataset provide the foundational data required for researchers to finally break through this aesthetic accuracy bottleneck. To dive deeper into the code and architecture driving this research, head over to the Learn by Doing with Stephen YouTube channel. For long-form discussions breaking down the raw data behind these breakthroughs, search for the Stephen Data Talk podcast, available on YouTube Music and Spotify.
This shows the primary computational challenge in natural language processing, taking distinct sequential human text and mapping it into a continuous stream of numerical data. Machine learning models tackle this mapped data in 3 categories. The first is standard classification, where the model predicts a single label, such as extracting a positive or negative sentiment. The second is multi-classification, where it identifies multiple elements within a string, like extracting named entities. The third category is generation. Tasks like machine translation require taking text in and producing text out. Because the length of the generated output varies based on the input, evaluating accuracy here presents a unique computational hurdle. For standard and multi-classification, we measure success with rigid quantitative metrics like precision, recall, and the F1 score for imbalanced datasets. Generation tasks, however, rely on metrics like perplexity, which measures the mathematical probability of the model's generated output. Calculating the accuracy of a single word classification is a trivial math problem, but generating long, fluent passages exposes a strict mechanical limit in early machine learning, the mathematical inability to maintain structural context over a long sequence. To achieve true language generation, engineers had to abandon treating text as a sequence to be read from left to right and start treating it as a geometric space to be modeled in parallel. We are going to build the architecture of modern large language models entirely from first principles. By tracking the math, we will see exactly where every preceding system broke down mechanically. Solving the problem of context was a strictly architectural and mathematical achievement, rather than a linguistic one. Neural networks cannot process raw strings of text. The mandatory first step is tokenization, which divides the text into discrete units that can be mapped to numerical tensors. If we split the text at the word level, we generate massive vocabularies. The model treats variations like run and runs as completely distinct entities, creating an unacceptably high risk of encountering out-of-vocabulary errors during generation. Splitting the text at the individual character level eliminates that out-of-vocabulary risk entirely. The trade-off is that it drastically increases the sequence length, which cripples computational efficiency. Subword tokenization offers the mathematical optimum. By breaking text down into common linguistic roots, it balances a low out-of-vocabulary risk with a manageable sequence length. This optimal tokenization strategy restricts the overall sequence length. Keeping that sequence size mathematically viable is a hard prerequisite for the heavy matrix multiplication required in the subsequent layers. Look at this 3D coordinate plane. If we represent our tokens using a basic one-hot encoding strategy, each word becomes an orthogonal vector pointing along independent axes. Because they are perpendicular, their cosine similarity is exactly 0. All semantic relationships are destroyed. To fix this, models use proxy tasks, like cross-entropy loss to predict neighboring words, to learn representations like word-to-vec. The strict orthogonal grid collapses, and the isolated vectors converge into a dense, continuous vector space cloud, where grouped points represent related concepts. By mapping tokens into a continuous hidden layer dimension, semantic similarity translates directly to geometric direction. Words with similar meanings point in similar directions, yielding a high cosine similarity. Continuous embeddings effectively map semantic meaning to spatial geometry. However, they critically fail to encode where a specific token is positioned sequentially within a sentence. This creates a sequential bottleneck. If you use a standard vector embedding, the mathematical representation for a word remains identical, regardless of its grammatical context in the text. Recurrent neural networks attempted to solve this isolation. As we see in this unrolled flowchart, an RNN processes one token at a time, calculating and passing a continuous hidden state value sequentially from one node block to the next. The mechanical flaw emerges during backpropagation through time. Updating the network's weights requires multiplying a long series of sequential gradient values together along this exact backward path. When these sequential gradients are fractions less than 1, their continuous multiplication causes the value to decay exponentially. Over long distances, it flatlines at 0. This is the vanishing gradient problem. The hardware consequence is severe. Because each step strictly depends on the calculation before it, you cannot process the sequence in parallel on modern GPUs. RNNs hit a hard mathematical and physical wall. They inevitably lose long-range context by design, and their architecture inherently blocks efficient scaling. The 2017 transformer architecture bypassed this by abandoning sequential processing entirely. Instead, it relies on direct, highly parallel connectivity between all words simultaneously. In this visualization, a single input embedding is projected into 3 distinct learned matrices: a query, a key, and a value. To find the mathematical similarity between tokens, the self-attention operation computes the dot product of the query matrix against the transposed key matrix. This generates a new n by n attention weight grid. This raw grid is divided by the square root of the key dimension to prevent the gradients from saturating, and then passed through a softmax filter. This transforms the raw data points into a probability distribution that sums to 100. Finally, this normalized probability distribution is multiplied by the values matrix. The output is a final, context-aware vector block. To capture varied semantic associations, the architecture uses multi-head attention. It runs this exact query, key, and value projection multiple times simultaneously using different learned matrices. Self-attention replaces fragile sequential loops with robust matrix multiplication. It avoids the vanishing gradient problem, aligning natively with parallel GPU hardware. For complex generation tasks, these attention blocks are stacked into a larger macro architecture, strictly divided between an encoder and a decoder. The encoder's role is to aggressively process the source text. It uses multi-head self-attention and feed-forward networks to build a contextualized mathematical representation of the input. Because this happens in parallel, the system has no inherent concept of word order. It relies on positional encodings, injecting sine and cosine values into the embeddings to retain sequence structure. The decoder's role is generating the final output sequentially. To accomplish this, it utilizes a specific masked self-attention layer. Masked self-attention is strictly unidirectional. It mathematically prevents the model from looking ahead at future, unpredicted tokens during the autoregressive generation. The encoder and decoder integrate at the cross-attention layer. Here, the decoder generates the queries based on what it has processed so far, but it pulls the keys and values directly from the encoder's rich output. This architecture elegantly separates the deep, parallel geometric understanding of the input space from the strict, sequential generation required for the output space. The transformer architecture dominates modern AI precisely because its dense matrix multiplications perfectly mirror the parallel processing capabilities of modern GPU clusters. Beyond the hard architecture, training optimization introduces a statistical problem: model overconfidence. Standard one-hot labels fail during training because they force a strict 100% confidence target for the next token. This ignores the natural variance of language and actively harms the model's ability to generalize. Engineers solve this using label smoothing. By mathematically shifting the training target from a hard 1 to 1 minus epsilon, they deliberately inject uncertainty. This improves generation evaluation metrics like the BLUE score. The combination of frictionless parallel hardware alignment and statistical regularization techniques permanently established the transformer as the bedrock of large language modeling. Mastering the linear algebra and geometric architecture of the transformer is merely the theoretical prerequisite for deploying robust machine learning models in production environments. To transition from theory to hands-on applied engineering, Explore the tutorials available on the Learn by Doing with Stephen YouTube channel, and keep up with the evolving machine learning ecosystem by subscribing to the Stephen Data Talk podcast, available on all major platforms. The "attention is all you need" paper defined the modern era of AI, but the specific architecture it proposed is now functionally obsolete. To scale sequences beyond a few hundred words, researchers had to rebuild the transformer's internal engine to prioritize memory throughput and hardware utilization. The 2017 design faced three primary physical limits. It struggled to maintain positional context, it became unstable at extreme depths, and its memory requirements grew too large for modern GPUs to handle efficiently. We are going to deconstruct the specific upgrades that solved these bottlenecks, ROPE, RMS norm, and GQA, and see how the encoder-only paradigm evolved for specialized classification tasks. Modern LLM development prioritizes throughput and scaling constraints over historical architectural purity. Because self-attention capulates the relationship between every token in a set simultaneously, it is natively permutation invariant. Without an external signal, the model has no way to distinguish the first word in a sentence from the last. The original solution involved adding absolute positional vectors, essentially a fixed coordinate, to the token embeddings before they ever reach the attention layers. This approach is brittle. The positional signal is frequently washed out by the time it travels deep into the network, and the model cannot easily infer positions beyond the specific sequence length it saw during training. Rotate position embeddings, or ROPE, shift this logic by injecting positional data directly into the query-key interaction. Before calculating attention scores, ROPE multiplies the query and key vectors by a rotation matrix. The degree of rotation is determined by the token's index, here shown as M for the query and N for the key. When we take the dot product of these two rotated vectors, the absolute positions M and N effectively vanish. Because a rotation matrix is orthogonal, the resulting inner product reduces to a function of the difference between the two angles. This means the attention score now inherently represents the relative distance between tokens. By embedding position as a rotation, the model's similarity bias is mathematically tied to proximity, allowing it to generalize to much longer sequences than it encountered during training. In massive networks, activations often fluctuate wildly as they pass through different layers, a phenomenon known as internal covariate shift that can stall training entirely. To fix this, researchers moved the normalization step. By shifting from post-norm to pre-norm, normalizing the vector before it enters the attention or feed-forward layer, they ensured a more stable flow of gradients during training. However, the standard layer norm calculation requires finding the mean of the activations and subtracting it. At scale, this subtraction step is computationally expensive and, as it turns out, largely unnecessary. RMS norm simplifies the math by scaling the activations strictly by their root mean square. It skips the mean centering entirely, relying on a learned parameter, gamma, to rescale the vector. This streamlined approach achieves the same convergence stability as layer norm, but with significantly less computational overhead per layer. Global attention is a quadratic problem. If you double the length of your input, the computational work required to compare every token to every other token increases fourfold. Many modern architectures interleave global attention with sliding window layers. These restrict each token to only attend to its immediate neighbors, capping the computational cost, while still allowing information to propagate through the network's depth. The second bottleneck occurs during generation. To predict the next word, the model must store the keys and values of every previous word in its memory, a structure called the KV cache. In standard multi-head attention, every query head has its own dedicated key and value projection. As the context grows, this cache quickly consumes all available GPU memory. Multi-query attention attempted to solve this by forcing every query to share one single key and value head. While this saves memory, it often degrades the model's ability to learn complex relationships. Grouped query attention, or GQA, finds the middle ground. It groups query heads together to share a single K and V projection, drastically reducing the memory footprint of the KV cache while maintaining the model's representational power. GQA is now the industry standard because it allows models to handle massive context windows on consumer-grade hardware. While generation models use a causal mask to hide future words, Classification tasks require a different approach. Extracting the dense meaning of a sentence is more efficient if the model can look at the entire sequence at once. This led to the BERT architecture, which discarded the decoder entirely. By focusing only on the encoder, BERT achieves true bidirectional context. BERT is trained using masked language modeling. By hiding 15% of the tokens, the model is forced to use the information from both the preceding and following words to predict what's missing. To understand how sentences relate to one another, BERT uses a separator token and a next sentence prediction task, classifying whether two phrases naturally follow one another. All this information is aggregated into a single classification token, the CLS token. Because it attends to every other word in the sequence, it becomes a dense summary of the entire input, perfect for downstream classification tasks. By focusing purely on encoding, this paradigm created a tool that could map the contextual relationships of language with extreme precision. Despite its power, the original BERT model is computationally expensive to deploy, leading to significant latency in real-world applications. To solve this, researchers used knowledge distillation to create DistillBERT, a smaller, faster student model that retains the knowledge of its larger teacher. Distillation works by minimizing the KL divergence between the teacher and student models. Instead of learning simple labels, the student model learns to mimic the teacher's soft probability distributions, capturing the nuanced relationships the teacher has already discovered. While DistillBERT focused on speed, the Roberta project pushed for maximum performance. They discovered that BERT was actually undertrained and that several of its original assumptions were incorrect. Roberta achieved state-of-the-art results by removing the next sentence prediction task entirely, using larger batches and training on significantly more data over longer periods. These two paths allowed the industry to specialize: DistillBERT for low-latency deployment and Roberta for absolute predictive accuracy. The transformer has evolved into a library of modular, highly refined mathematical operations. From ROPE for positional context to GQA for memory management, every choice in modern architecture is a calculated response to the physical limits of our hardware. Moving beyond the basics of attention is all you need is the first step toward building systems that can actually scale. To see these architectures in action, visit the Learn by Doing with Stephen YouTube channel for implementation-focused coding tutorials. And for deep dive discussions on the engineering trends shaping the field, subscribe to the Stephen Data Talk podcast, available on YouTube Music, Spotify, and all major platforms. Modern large language models rely on massive, decoder-only architectures trained on datasets exceeding tens of trillions of tokens. Increasing the intelligence of these systems involves scaling parameter counts into the hundreds of billions, but activating every parameter for each individual token generation creates a computational load that exceeds the limits of standard real-time hardware. This problem is built into the autoregressive nature of text generation. Because the model must predict each token sequentially, it must wait for the completion of one forward pass before starting the next. This sequential process moves the bottleneck from raw floating-point operations to memory bandwidth. During inference, the GPU often sits idle, waiting for the massive model weights to transfer from VRAM into the processors. Efficient deployment requires a pipeline designed to navigate these specific memory and bandwidth constraints. We will build this pipeline by integrating three specific systems: mixture of experts for scaling, probability sampling mathematics for diversity, and memory paging for VRAM efficiency. This approach transitions the LLM from a theoretical neural network into a hardware-aware systems engineering pipeline. In a standard transformer block, the feed-forward network is the most expensive layer. Its high dimensionality and massive parameter count account for the majority of the total compute required for a forward pass. We can manage this cost by splitting that network into n parallel subnetworks, or experts. Before reaching these experts, a token passes through a router, or gate, which generates a probability distribution for it. The router analyzes the token's representation to decide which specific expert is mathematically best suited to process its information. In a sparse MOE system, we only activate the top K experts, usually just one or two. This routes the token through a single path, while the other experts remain inactive. This architecture allows us to scale the total parameter count significantly, while capping the active floating point operations per forward pass. This creates a risk of routing collapse, where the model favors a single expert for every token, essentially ignoring the rest of the capacity built. We solve this by adding an auxiliary loss function during the training phase. This punishes the model if the routing distribution becomes too narrow. This auxiliary loss ensures a uniform distribution across all experts, proving that we can scale model capacity without linearly scaling the compute required at inference. As the data reaches the final output phase, a linear layer projects the hidden state into the vocabulary space. These raw scores are then converted into a probability distribution through a softmax function. Selecting only the single highest probability token from this list is known as greedy decoding. While locally optimal, this often leads to suboptimal long-term sequences. The model can become trapped in repetitive loops or generate text that feels statistically flat. Systems can instead use beam search to track several probable paths at once, though this still frequently results in a lack of diversity. To prevent nonsensical words, top-K sampling truncates the distribution, removing the low probability tail. The temperature hyperparameter sits in the denominator of the softmax calculation, allowing us to adjust the curve's shape. As temperature approaches 0, the math forces an absolute spike. The highest logic gains nearly full probability, making the model deterministic. As it increases, the differences diminish, flattening into a uniform line, giving low probability tokens equal chance. Modifying this single hyperparameter variable gives engineers precise control over the balance between deterministic logic and creative variation. Managing the physical GPU VRAM is our final bottleneck. To generate a new token, the model must attend to every previous token, meaning every step relies on the specific states of the entire history. Rather than recomputing these states for every new token, we store the key and value matrices in memory. This is the KV cache. Standard allocation systems try to reserve a single contiguous block of memory for this cache. Because most requests are shorter than the limit, this results in significant fragmentation. Large VRAM sections remain empty. Page detention solves this by treating VRAM like virtual memory in an operating system. The KV matrices are broken into small, fixed-size blocks that can be stored anywhere in memory. A block table mapping system tracks these scattered pieces, stitching them back together seamlessly for the attention calculation. By eliminating fragmentation, page detention allows a single GPU to handle much larger batches of requests simultaneously, increasing total throughput. We can further reduce the memory footprint through multi-latent detention, which passes the token through a low-rank compression matrix. This achieves a smaller cache size by sharing a single latent representation across all attention heads. But even with optimized memory, we are still bound by sequential generation. The model must finish token A before it can begin token B. Speculative decoding bypasses this limit using a smaller draft model. It guesses several tokens before the main model starts. The larger target model verifies the draft in a single parallel pass, accepting correct guesses and rejecting errors. An acceptance mechanism based on the total probability theorem ensures the final output exactly matches the large model's distribution, even using draft guesses. This mathematically guarantees the high-quality output of a massive model at the speed of a much smaller one. From the routing gates of a mixture of experts architecture to the paged blocks of the KV cache, the journey of a single prompt is a sequence of hardware-aware optimizations. Moving a theoretical architecture into a production environment requires solving these physical constraints. Scaling these models effectively depends on the simultaneous engineering of the architecture, the sampling mathematics, and the memory management. For practical guides on building these systems, visit the Learn by Doing with Stephen YouTube channel. To join the conversation on data and systems engineering, find the Stephen Data Talk podcast on Spotify, YouTube Music, and all major platforms. Ask a raw, pre-trained language model how to wash a dirty teddy bear, and it won't give you instructions. Instead, it might generate a Wikipedia-style article about the materials used to manufacture stuffed animals. But ask an aligned assistant the exact same question, and it tells you step by step how to hand wash it. This happens because a base transformer model is not designed to solve your problems. Its sole mathematical objective is to predict the statistically most likely next token based on the vast corpus of internet text it ingested. Modern language models are built in two distinct stages to solve this. First comes pre-training, which builds a massive statistical world model from raw text. Second is supervised fine-tuning, or SFT, which aligns the model's behavior to follow instructions and act as a helpful assistant. Scaling these two stages to hundreds of billions of parameters introduces a severe structural bottleneck. The memory and compute required to process trillions of words across massive neural networks exceed the physical capacity of individual hardware units. Transforming these networks from mathematical concepts into physical reality depends on distributed systems engineering and hardware-aware optimization to make training possible. The pre-training phase requires models to ingest tens of trillions of tokens, scraped from the entire internet, to map the structure of human language and code. This animated chart visualizes the chinchilla scaling laws. It plots a fixed compute budget against model performance, revealing a distinct optimization curve. It proves intelligence relies on a strict mathematical relationship between neural network size and training data volume. Looking at the optimal sweet spot, we find a highly specific ratio. Optimally, you need roughly 20 tokens of training data for every single model parameter. Early architectures often ignored this math, wasting immense compute by building networks with hundreds of billions of parameters, but starving them of training data. Today's models are calibrated strictly along this curve. Achieving high performance is an exercise in exact economic scaling. Throwing massive amounts of data at an arbitrarily large network is mathematically inferior to precise, balanced optimization. Once the optimal size is determined, engineers hit a physical memory wall. A standard enterprise GPU is physically capped at roughly 80 gigabytes of internal memory. This bar chart illustrates exactly how fast that memory fills up during the backward pass of training. We store the model's weights, forward activations, gradients, and optimizer states, immediately bursting far past the 80 gigabyte limit. Looking closer at the optimizer states block, we see what bloats this footprint. The atom optimizer forces the GPU to maintain the first and second moments of the gradients, multiplying the required memory well beyond the base weights. To physically compute this impossible load, engineers use distributed training, linking multiple GPUs into a massive cluster to share the burden. The simplest approach is data parallelism, which divides the training batches across the cluster, but it has a critical flaw. It forces every single GPU to hold a full, duplicated copy of the model, wasting precious memory. The solution is the Zero Redundancy Optimizer, or ZERO. ZERO slices those massive memory blocks horizontally, sharding the parameters, gradients, and optimizer states across multiple GPUs, so every individual device stays under its 80 gigabyte limit. ZERO provides massive memory savings, but it introduces a severe operational tax. The GPUs must constantly pass these matrix fragments back and forth over the network, incurring significant communication delays. By accepting that communication delay, ZERO physically enables the pre-training of 100 billion parameter models that would otherwise be impossible to instantiate on silicon. Even with the memory distributed, another physical bottleneck emerges: the input-output speed limit. GPUs can execute mathematical operations much faster than they can read or write data to their own memory banks. Inside a single GPU, there is a strict memory hierarchy. There is a large, relatively slow storage pool called high bandwidth memory, or HBM, connected to a tiny, ultra-fast block called SRAM, where the actual computation occurs. The standard self-attention formula forces a continuous, slow data transfer. Matrices for queries, keys, and values are repeatedly loaded from the HBM into the SRAM, computed and written back to the HBM in a highly inefficient loop.
To bypass this I/O bottleneck, researchers developed flash attention, an exact, non-approximate algorithm that reorganizes the data flow using a technique called tiling. Instead of moving entire matrices, tiling loads small, localized blocks of the queries, keys, and values into the fast SRAM. The complete softmax computation is processed locally, end-to-end, and only the final result is written back to the HBM. During the backward pass, flash attention takes a counterintuitive approach. Instead of saving all forward activations into the slow HBM to reuse later, it discards them and recomputes them from scratch on the fly. By minimizing memory reads and writes, flash attention proves that doing more total mathematical operations can actually speed up overall training time, circumventing the physical memory transfer limits entirely. With the hardware constraints managed, engineers turn to optimizing the numerical data structures themselves. This diagram shows how mixed precision training yields massive efficiency gains. By shrinking a 32-bit floating point number down to exactly half its length to represent a 16-bit format, the system drastically doubles compute speed and halves memory requirements. Mixed precision training follows a strict rule. The base model weights must remain stored in high-precision 32-bit format. This prevents tiny rounding errors from accumulating and permanently degrading the model during gradient updates. These optimizations allow the model to complete pre-training. Next comes supervised fine-tuning, or SFT, which shifts the model's objective toward following specific user instructions. During SFT, the objective function calculates loss differently. Instead of trying to predict every single word from the beginning of a sequence, it calculates loss only on the generated response to a fixed user instruction. Unlike the massive scale of the pre-training internet scrape, the SFT dataset requires orders of magnitude less volume. However, it demands pristine, human-curated quality to teach the model safety, accuracy, and helpfulness. Pre-training builds the raw statistical horsepower, but precision-managed SFT acts as the steering wheel required to make the output useful to a human. Adapting a 100 billion parameter model for every specific downstream task or business application is financially impossible if you have to update the entire network every time. Researchers solved this economic hurdle with low-rank adaptation, or LoRa, which enables parameter-efficient tuning. The foundational step of the LoRa architecture is to freeze the massive, expensive pre-trained weight matrices. These base weights require absolutely zero memory to update because they remain entirely static. Next to this frozen base, LoRa injects two tiny, trainable, low-rank decomposition matrices that run in parallel. When this tall, narrow matrix multiplies against this short, wide matrix, it produces a new output that exactly matches the dimensions of the frozen base. This rank reduction works because multiplying these tiny matrices yields a full-size parameter update, but uses only a microscopic fraction of the computational footprint. By dropping the required compute from a cluster of GPUs down to a single machine, LoRa democratizes model fine-tuning. It shifts the power to build specialized, domain-specific AI out of the exclusive hands of hyperscalers and into the hands of individual engineers. From raw text to aligned assistant, the complete LLM training pipeline is an exact science of scale and physical constraint. Distributed networks leveraging zero and SRAM optimized algorithms like flash attention make trillion-token pre-training physically possible. Supervised fine-tuning and parameter-efficient techniques like LoRa sculpt that raw statistical capability into highly specialized human-aligned applications. The final step is verifying that utility, testing these highly engineered models against complex benchmarks and human preference testing to ensure they perform safely in the real world. Modern artificial intelligence is the result of neural network architecture meeting the physical constraints of hardware and systems engineering. If you want to move beyond the theory and actually start applying these architectures, I invite you to check out the Learn by Doing with Stephen YouTube channel and on other platforms. And for deeper conversations on the future of machine learning, listen to the Stephen Data Talk podcast, available on YouTube Music, Spotify, and other various platforms. If you ask a language model whether you can put your teddy bear in the washer, you might get a factually correct but blunt response. No, it might get damaged. Or you might get the exact same facts, but with a gentler tone. It's better not to. Your teddy bear could get hurt. Getting a model to understand how to answer, rather than just what to answer, is the core challenge of AI alignment. The second stage of training, supervised fine-tuning, or SFT, is excellent at teaching a pre-trained autocomplete engine to follow instructions, but it struggles to instill subjective behavioral traits like friendliness or safety. SFT has strict operational limits. Curating tens of thousands of perfect, high-quality demonstration prompts is incredibly expensive. Heavy curation also risks biasing the model's prompt distribution. More importantly, SFT only teaches a model exactly what it should predict next. It lacks a built-in mechanism for negative signals. You cannot easily use SFT to tell a model what not to say. To fix this, systems engineers implement a third training stage called preference tuning. Here, the goal is no longer teaching the model formatting or facts.
The goal is aligning the model's behavioral outputs with specific human preferences. A pre-trained model knows language. An SFT model knows how to execute a task. But achieving a safe, helpful, and aligned assistant requires bridging the gap between raw token prediction and subjective human values using preference data. To build a preference dataset, we feed a prompt into an SFT model with a positive temperature, generating two distinct outputs. A human evaluates them side by side, designating a winner and a loser to create a binary pair. This pairwise data forms the foundation for Phase 1 of reinforcement learning from human feedback, or RLHF. We take a frozen copy of our language model, removes its text generation layer, and attach a scalar classification head. This creates a reward model. The Bradley-Terry equation maps a sigmoid curve over the difference in rewards, calculating the probability that response I is better than J. We optimize this model by wrapping the probability in a negative log likelihood loss function, adjusting internal weights to maximize the human-preferred data. Notice the operational quirk here. We train the reward model entirely on pairwise comparisons, but once trained, we deploy it to output a single pointwise scalar score for any individual text completion it reads. The reward model has one specific job. It mathematically quantifies subjective, qualitative human preference into an exact machine-readable scalar value. With our preference mathematically defined, we move to Phase 2, reinforcement learning via proximal policy optimization, or PPO. The language model acts as an agent, taking actions by predicting tokens, and receiving a signal from the frozen reward model about how well it did. The active policy optimizes for advantage, an estimation of how much better a generated output is compared to an expected baseline, calculated using a jointly trained value function. But PPO introduces a severe systemic threat. If you give an AI a mathematical score and an unconstrained mandate to maximize it, the system will exploit the metric. Imagine a lecturer whose only objective function is the volume of applause at the end of class. They realize quickly that telling jokes generates louder cheers than teaching complex math. The score is maximized, but the core objective, education, is entirely lost. In machine learning, this is called reward hacking. An unconstrained model generates bizarre, repetitive text, triggering the reward classification head, while losing specific knowledge acquired during pre-training. This chart maps the engineering solution within PPO. The solid curve is the active, updating policy. We apply a KL divergence penalty, represented by the dotted boundary lines, which forces the new policy to stay mathematically proximal to the original frozen SFT reference model. PPO's strict proximity constraint is the mechanism preventing the active policy from cannibalizing its own intelligence to chase high reward scores. PPO is mathematically elegant, but in practice, it is computationally brutal. Look at the memory footprint required for PPO training. You must carry 4 distinct neural networks in VRAM simultaneously. Compounding this memory tax is algorithmic drag. The active model must stop training, generate fresh rollouts, score them, and then resume, constantly bottlenecking training speed. For engineering teams without infinite compute budgets, there is an architectural alternative to PPO called Best of N. Best of N skips the reinforcement learning training phase entirely. Instead, at inference time, you take a prompt and generate N parallel completions from your standard SFT model. You run all of them through your frozen reward model, score them, and serve the highest rated completion to the user. This completely removes the instability of RL training, but it pushes the massive computational tax directly onto inference. Generating 5 answers to serve 1 means multiplying your API costs and latency by 5. Teams must choose between unstable, memory-crushing training pipelines with PPO or brute force, expensive inference serving with Best of N. In 2023, researchers published a mathematical bypass to this alignment dilemma called direct preference optimization, or DPO. The DPO paper operates on a single thesis: your language model is secretly a reward model. Researchers solved the PPO objective, proving through algebraic rearrangement that the reward term, the R you see here, can be entirely expressed as log probability ratios of the active policy and frozen reference. Plugging this back into Bradley-Terry completely eliminates the explicit reward model. This algebraic substitution transforms unstable reinforcement learning into a direct supervised classification loss function operating directly on your preference pairs. The hardware implications are immediate. Returning to our GPU footprint, the reward model and value function blocks dissolve. Hardware requirements drop from 4 simultaneous models down to just 2. DPO collapses a brittle 4-model reinforcement pipeline into a stable 2-model supervised problem using pure mathematics. This matrix shows that aligning language models is an optimization problem balancing training compute, inference compute, and performance. RLHF using PPO maintains the highest performance ceiling, but demands massive engineering resources to stabilize its 4-model architecture. Best of N avoids training headaches completely, acting instead as a brute force tax on inference costs and user latency. DPO provides an elegant, stable mathematical shortcut back to supervised learning, though it carries a minor risk of distribution shift if the preference data strays too far from the base model. To see the code implementations and build these architectures from scratch, check out the Learn by Doing with Stephen YouTube channel. For deep dive discussions on machine learning paradigms, search for the Stephen Data Talk podcast on Spotify and major audio platforms. Links in the description. Preference tuning serves as the mathematical bridge. It takes raw autocomplete capabilities built during pre-training and fine-tuning, converting them into a functional, aligned, safe AI assistant. This matrix shows that aligning language models is an ongoing optimization problem, balancing training compute, inference compute, and model performance. RLHF using PPO maintains the highest performance ceiling, but it demands massive engineering resources to stabilize its 4-model architecture. Best of N avoids training headaches completely, acting instead as a brute force tax on inference costs and user latency. DPO provides an elegant, stable mathematical shortcut back to supervised learning, though it carries a minor risk of distribution shift if the preference data strays too far from the base model. To see the code implementations and build these architectures from scratch, check out the Learn by Doing with Stephen YouTube channel. And for deep dive discussions on machine learning paradigms, search for the Stephen Data Talk podcast on YouTube Music, Spotify, and major audio platforms. Links are in the description. Preference tuning serves as the mathematical bridge. It takes the raw autocomplete capabilities built during pre-training and supervised fine-tuning and converts them into a functional, aligned, and safe AI assistant. Traditional large language models are extremely good at guessing the next word in a sequence. But when presented with complex mathematical or coding problems, that linear autocomplete style prediction breaks down. To solve hard problems, models need to generate a chain of thought, explicitly breaking the problem into intermediate steps before finalizing an answer. Initially, AI labs tried to teach this behavior by relying on supervised fine-tuning. Engineers would feed the model thousands of examples of humans writing out step-by-step logic, hoping the model would simply mimic that structured process. Sourcing these high-quality reasoning chains is incredibly expensive. Writing them from scratch takes specialized experts hours per problem, creating a severe bottleneck. You simply cannot generate enough human data to scale this approach indefinitely. Even if you could, there is a core cognitive mismatch. The way a human reasons through a physics problem relies on intuition and experience. That human heuristic does not naturally align with the mathematical way a language model optimizes its token probabilities. Because of this, trying to teach a model to reason solely through supervised fine-tuning means its capabilities are strictly capped by the limits of the human data it was trained on. Rather than forcing a model to copy exactly how a human thinks, the architecture needs to evaluate what the model produces. We have to shift to reinforcement learning to reward the final, correct outcome. Typically, aligning a model involves reinforcement learning from human feedback, where human raters score the model's answers. But for advanced mathematics or thousands of lines of code, human evaluation is far too slow and subjective to provide a clean, high-volume training signal. This necessitates a shift toward objective measurement through verifiable rewards. This approach moves the burden of evaluation from human judges to deterministic code. If a model writes a program, a compiler can automatically check if the code runs and passes test cases. If it solves a math equation, a deterministic parser can verify if the final string matches the known ground truth answer. The environment itself provides an absolute binary signal of success or failure. The training reward is then split into two clear checks. First, a formatting reward ensures the model successfully wrapped its logic inside designated think tags. Second, an accuracy reward triggers only if the final extracted solution is completely correct. By combining these two checks, verifiable rewards create a self-contained optimization cycle. Models can continuously generate logic and verify their own results against objective systems, which allows for pure logic optimization at a scale that human data cannot reach.
Once a model begins thinking, evaluating its true capability becomes complex. For highly difficult tasks, forcing the model to rely on a single attempt is incredibly noisy. One small arithmetic error ruins the entire output. Instead, the industry evaluates reasoning using a metric called pass at k. This calculates the statistical probability that if the model generates a batch of k unique attempts, at least one of those attempts will successfully solve the problem. Looking at this diagram of the derivation formula, you can see how it works. Rather than calculating the odds of success across varying attempts directly, it defines the metric as 1 minus the probability that every single sampled attempt is incorrect. This models the evaluation as sampling without replacement. We take the number of total possible failures chosen k times, divided by the total number of generations chosen k times. This chart graphs the pass at k score against generation temperature. A low temperature produces safe, repetitive answers. As you increase the temperature, the model generates highly diverse reasoning paths. This increases the likelihood of finding one correct answer in the batch up until the point where diversity peaks and the logic completely collapses into hallucination. The pass at k framework proves a crucial structural mechanic. We can directly trade inference compute for reasoning accuracy. Granting a model the extended time and massive compute to generate more answers yields mathematically higher success rates. To optimize these models during the reinforcement learning stage, the industry historically relied on an algorithm called proximal policy optimization, or PPO. Looking at the PPO workflow on the left, there is a critical architectural flaw. It requires the primary policy model to run alongside a massive parallel value model, which attempts to predict the expected future reward for every single token being generated. Running this secondary value model token by token introduces a crippling compute overhead and doubles the memory demands on already massive network architectures. To fix this, researchers introduced Group Relative Policy Optimization, or GRPO. As you can see on the right, this architecture removes the value model entirely. Instead, it takes a single prompt and generates a group of G distinct completions directly from the policy model. The advantage, how good a specific completion actually is calculated relative to its peers. The system scores all the completions in the group and compares each individual reward against the mean and standard deviation of that exact batch. Because the scoring is relative to the group, it inherently self-adjusts for the baseline difficulty of the prompt. A hard math question where most outputs fail will still accurately isolate and highly reward the single successful logic path. By eliminating the massive memory requirements of a parallel value function, GRPO allows engineering teams to focus all their hardware and compute cycles squarely on policy optimization. However, this specific equation represents the original GRPO objective function, and it contains a mathematical flaw. Notice the normalizing term at the end, 1 over the absolute value of O, which represents the output sequence length. This division creates a bad incentive. Dividing the advantage by the output length means that the mathematical penalty for a short, incorrect answer is significantly harsher than the penalty for a long, incorrect answer. During training, the model quickly figures this out. It begins artificially inflating its reasoning length, endlessly babbling before committing to an answer, simply to minimize the mathematical penalty applied to its tokens. Modern iterations of GRPO fix this exploit by either equalizing token-level contributions across the board or deleting that denominator entirely. Once the math is corrected, the runaway output length stabilizes. An objective function must flawlessly map to the desired behavior. A language model will ruthlessly exploit any mathematical loophole to maximize its reward. This dynamic is perfectly illustrated by DeepSeek R10. This model was a proof of concept, trained from a base language model using pure, verifiable reinforcement learning without any prior formatting supervision. While R10 achieved elite scores,
Its outputs were functionally broken. It suffered extreme readability issues, mixed multiple languages mid-thought, and lacked a structural anchor. To fix this, DeepSeek engineered a hybrid production pipeline for their official R1 model. It begins with a cold start phase, utilizing several thousand highly curated supervised fine-tuning examples, specifically to enforce rigid formatting and language consistency. Once the output structure is anchored, Phase 2 applies the GRPO algorithm, using verifiable rewards on math and coding problems to massively scale the model's logical capabilities. Phase 3 is rejection sampling. Using the newly capable model, engineers generate thousands of potential outputs for difficult prompts. An automated judge filters out the noise, keeping only the highest quality logic paths to use as a massive synthetic dataset for another round of fine-tuning. Finally, Phase 4 applies a standard reinforcement learning pass targeting general helpfulness and harmlessness, ensuring the reasoning model functions safely as an everyday assistant. Producing a highly capable reasoning model requires an interweaved approach. Supervised fine-tuning provides the formatting anchor, and reinforcement learning scales the raw logic. Deploying a massive 600 billion parameter model like GateGeek R1 locally or for everyday applications is financially and technically prohibitive. The solution relies on distillation. This is the process of transferring the dense cognitive capabilities of a massive teacher network directly into a much smaller, highly efficient student network. Instead of running the entire expensive reinforcement learning pipeline again, distillation uses the massive teacher model to generate millions of verified, correct logic chains. These outputs are used as direct, ready-made, supervised fine-tuning data to train the smaller student model. This methodology has enabled models as small as 8 or 14 billion parameters to achieve reasoning scores that match closed-source behemoths. The immense compute investment required for deep reinforcement learning serves as a one-time cost. It yields high-quality synthetic data that immediately elevates the reasoning capabilities of the entire open-source ecosystem. The architecture of AI development is rebalancing. The industry is actively shifting vast amounts of compute away from initial pre-training and reallocating it directly into inference time reasoning and search operations. By leveraging verifiable rewards and highly efficient algorithms like GRPO, models can now optimize their own logic at scale, breaking past the strict limits of human-labeled data. To build these systems yourself, visit the Learn by Doing with Steven YouTube channel for step-by-step technical tutorials on modern machine learning architectures. And for long-form discussions on the mechanics driving the AI industry, search for the Steven Data Talk podcast, available right now on Spotify and YouTube Music. A standard large language model is sealed off from the outside world. Its knowledge freezes at the exact moment its training data is cut off. It has no live connection to current events, no memory of new facts, and no ability to observe a changing environment. To bypass this limitation, the industry default has been to aggressively expand the model's context window. The logic assumes that if the model doesn't know something, developers can just dump hundreds of thousands of tokens, entire books' worth of raw, unfiltered text directly into the prompt. But here we see a heat map illustrating the needle in a haystack phenomenon. As the prompt length grows, the model's ability to retrieve a specific relevant fact degrades sharply. The flashing red areas represent lost information. When you feed an LLM too much irrelevant data, it gets confused and fails to locate the correct answers hidden in the noise. Beyond losing accuracy, this brute force approach comes with a massive computational price tag. API calls charge per token. Shoving hundreds of pages of text into every single prompt forces the system to process massive amounts of redundant data, driving inference costs exponentially higher. Overcoming these performance and cost plateaus requires a transition toward an active architectural engineering approach. These failures in recall, cost, and static knowledge define the requirements for a truly independent system. To function outside the context window, the model needs a pipeline for selective memory, a method for executing software, and a loop for multi-step goals. The first layer is dynamic memory, achieved through retrieval augmented generation, or RAG. Rather than dumping an entire database into the context window, a RAG pipeline acts as a precise, narrow stream. It searches an external knowledge base, extracts only the highly relevant information, and injects that specific data into the prompt. To make this searchable, the raw documents in your knowledge base must be systematically indexed. The text is sliced into pieces called chunks, typically around 500 tokens in length, with a slight overlap between them, so that sentences at the borders aren't abruptly cut off. Slicing a large document into hundreds of isolated paragraphs strips away the broader context. A 500-token chunk about a specific financial metric might not explicitly mention the company name or the year it belongs to, rendering it practically invisible to the retrieval system. To solve this, developers use contextual retrieval. Before the chunks are stored, an LLM processes the original full document and generates a short overarching summary. This summary is then prepended to every single isolated chunk, permanently tethering the specific data back to its original context. Calling an LLM to read a massive document for every single chunk summary is highly resource-intensive. Engineers use prompt caching to mitigate this. Because the document prefix is identical for every chunk, the system calculates the neural network activations once, saves them, and simply looks them up for subsequent requests, dropping the cost heavily. Proper indexing and caching create a highly efficient, context-aware foundation. When the system reaches for memory, it pulls fully formed semantic meaning rather than disjointed text. Here we see the two-stage retrieval pipeline. The first stage is candidate retrieval. Its goal is pure recall. It filters millions of stored chunks down to a pool of a few hundred potentially relevant candidates, executing this as fast as possible. This stage relies on two parallel searches. First, semantic search uses bi-encoder models, like SentenceBERT, to measure the cosine similarity between the query's mathematical embedding and the chunk's embeddings, finding concepts that share meaning. Second, heuristic keyword matching, known as BM25, looks for exact vocabulary overlap, ensuring you don't miss a document just because it uses highly specific terminology. Sometimes a short user question and a dense reference document are structurally too different to match cleanly. A technique called hypothetical document embeddings, or HYDE, prompts the model to generate a fake, ideal answer to the query first. The system then searches the database using that fake document's embedding, which structurally mirrors the target chunks much closer than a brief question. Once you have your rough candidate pool of a few hundred chunks, the pipeline moves to stage 2, re-ranking. The goal shifts entirely from fast recall to strict precision. While bi-encoders process queries and chunks independently, this stage uses a cross-encoder. By simultaneously processing both the original query and the retrieved chunk together in the same neural network, the model captures deep cross-attention. This outputs a highly accurate relevance score, sorting the chunks into a strict top K list. This is the formula for normalized discounted cumulative gain, or NDCG, which evaluates if the ranking actually works. Pay attention to the denominator, which applies a logarithmic discount based on the item's rank. NDCG evaluates the entire ranked list. If your system successfully retrieves a highly relevant document, but places it at rank 10 instead of rank 1, the denominator aggressively discounts its value. The formula mathematically penalizes the system for burying the best answers. A simpler evaluation metric is mean reciprocal rank, or MMR. Instead of measuring the entire list, MRR strictly looks at the position of the very first relevant document. If the first correct answer is at position 2, the score is 1/2. If it's at position 3, it's 1/3. High recall grabs the haystack, and high precision isolates the exact needles. This mathematical optimization solves the context window illusion entirely. RAG gives the model an excellent memory, but it remains a passive observer. It can fetch a document about the weather, but it cannot actually adjust your smart thermostat. To interact with the physical and digital world, we implement tool calling. Developers inject specific software function APIs along with detailed documentation of their inputs and outputs directly into the model's preamble. The critical distinction here is that the LLM does not execute the code itself. It takes a natural language request, recognizes which tool is needed, and maps that request into exact, structured JSON parameters. The external system runs the Python API, gets a result, and feeds it back to the model. Models learn to format these tool calls through supervised fine-tuning. Engineers train the model on thousands of pairs, mapping user queries to perfect API outputs, or use highly capable reasoning models to generate explicit instructional prompts that guide the tool's usage step by step. This creates a massive scaling bottleneck. A true enterprise agent might need access to hundreds of APIs. Loading all of their documentation into the context window for every single query degrades performance and drives up latency. The engineering solution is tool routing. The user query hits a lightweight intermediate LLM layer first. This router scans a massive grid of 50 tool icons, extracts exactly which APIs are relevant to the specific prompt, and passes only those few functions into the active context window. Anthropic's Model Context Protocol, or MCP, provides a standardized architecture for this. By separating the LLM client from external MCP servers that host the actual tools and data, you create a modular, highly scalable ecosystem. By combining tool routing with protocols like MCP, the LLM bridges the gap between probabilistic text generation and deterministic software actuation at an enterprise scale. Agency emerges when the model stops treating every prompt as a single-turn prediction and starts pursuing a target through iterative loops. We architect this autonomy using the REACT framework, Reason plus Act. This framework structures the LLM's thought process into a continuous loop of 3 nodes: observe, plan, and act. If a user states that their teddy bear is cold, the model enters the observe node. It analyzes the vague natural language query and translates it into an actionable system state, realizing it currently lacks data on the room's temperature. The cycle moves to the plan step, deciding to retrieve that missing data. The act node executes the specific Get Current Room Temperature API. The external software returns a value of 65 degrees, feeding it straight back into the top of the loop. The system observes the 65-degree reading, determines it is too low, plans a heat increase, and triggers an Adjust Temperature tool. This recursive logic continues firing on its own until the model confirms the final goal is met and exits the loop. You can scale this by linking entirely separate agents together. Frameworks like Google's Agent-to-Agent protocol standardize the communication, allowing an energy management agent to negotiate directly with the temperature agent. Autonomy introduces severe security risks. An agent equipped with recursive reasoning and API access can easily cause systemic damage. If a malicious prompt tricks an autonomous email agent into accessing restricted files, it can seamlessly execute a data exfiltration attack. Mitigating this requires a comprehensive defense stack. Protection begins during training, embedding harmlessness constraints directly into the model's weights using reinforcement learning. At inference time, independent safety classifiers act as a firewall, intercepting the conversation and halting the agent's actions if the behavior violates security policies. Because failure modes in dynamic loops are highly unpredictable, these defense mechanisms are continuously evaluated against rigorous testing frameworks, like Agent Safety Bench, to systematically quantify vulnerabilities. The REACT loop provides the engine for autonomous problem-solving, but without strict architectural safety constraints, that same engine can cause cascading system failures. This is the complete architecture of a modern agentic LLM. A user prompt enters the central model. The RAG pipeline uses biencoders and crossencoders to pull precision memory from external databases. The MCP tool router selects the specific software APIs required, and the REACT loop drives the reasoning, cycling through observations and actions until the task is complete.
The static next token predictor is now surrounded by a live infrastructure that fetches memory, triggers software, and manages its own recursive planning. As these agentic capabilities take over raw code generation and execution, an engineer's taste, the ability to verify correctness, enforce strict safety, and validate architectural logic becomes the most valuable asset in the industry. To put these exact frameworks into practice, head over to the Learn by Doing with Steven YouTube channel and platform. And for deeper conversations on data engineering and architectural design, listen to the Steven Data Talk podcast, available on YouTube Music, Spotify, and all major platforms.
In standard software development, evaluating performance is straightforward. A classification model takes an input and outputs a deterministic binary result, a clean 1 or a 0. But large language models generate free-form text, complex blocks of Python code, and multi-step mathematical proofs.
Because this output is non-deterministic, we cannot rely on simple rule-based scoring systems to check if the model is correct. Two completely different sentences can contain the exact same factual truth. This introduces a strict engineering problem. If you cannot reliably measure a system's output, you cannot systematically optimize it. Without measurement, you cannot improve the model, grinding your development to a halt. To measure this scalar complexity, engineers rely on a specific three-tier architecture, the LLM evaluation stack. At the micro level, we evaluate individual outputs. We discard rigid word matching algorithms in favor of building an automated LLM as a judge to evaluate semantic meaning. At the meso level, we evaluate multi-step reasoning. We dissect autonomous agent loops to isolate exact execution failures when models attempt to use external tools. Finally, at the macro level, we measure raw base model capability against global benchmarks. Mastering this complete three-tier stack allows us to accurately map the Pareto frontier of artificial intelligence. The instinct is to evaluate LLM outputs by having human raters grade them, but human raters operate slowly, cost a premium, and frequently disagree on subjective tasks. This matrix shows Cohen's kappa, a statistical metric used to measure inter-rater reliability. We use it to determine if human agreement is driven by clear guidelines or random chance. Even aligned humans introduce too much variance for high-volume testing. In the past, engineers relied on hard-coded rule-based metrics like BLUE, METEOR, and ROUGE. These formulas compare a model's output to a single static reference text. But these formulas look strictly for n-gram overlap. If your model generates a perfectly accurate response that uses a different stylistic phrasing than the reference text, metrics like BLUE actively penalize it. To solve this, the industry standard shifted to using a separate, high-capacity model as a grader, a proxy for human preference, known as an LLM as a judge. This architecture requires three specific inputs: the original prompt, the model's generated response, and a crisp binary grading criteria. These feed directly into the judge, which evaluates the text semantically. For this to work inside an automated testing pipeline, the judge's output cannot be freeform. We must use constrained decoding, often called structured outputs, to force the judge to return a programmatically parsable format, like JSON. To maximize accuracy, we structure the prompt to demand a rationale before the numerical score. This sequence forces a chain of thought process, giving it compute space to articulate reasoning before committing a final grade. This setup requires active mitigation of specific model tendencies. Judges exhibit position bias, favoring the first answer they see. They show verbosity bias, equating longer answers with better answers. And they suffer from self-enhancement bias, artificially inflating the scores of responses generated by their own base architecture. By controlling for these biases and constraining the output format, we transform the LLM judge into a reliable foundational unit capable of evaluating free-form truth at massive scale. Now, factuality introduces an entirely different challenge. A single text generation is rarely completely true or completely false. It is almost always a blend of accurate claims and subtle hallucinations. Consider this text. Teddy bears first created in the 1920s were named after President Theodore Roosevelt after he proudly wanted to shoot a captured bear. Evaluating this paragraph requires breaking it apart to ground the specific claims against concrete historical data. First, we extract atomic claims into index cards. Next, a RAG pipeline verifies each card against a knowledge base, confirming Roosevelt but rejecting the 1920s date. Finally, a weighted formula calculates a score, penalizing major historical errors more heavily than minor ones.
We cannot treat factuality as a monolithic binary check. It must be engineered as an active pipeline of decomposition, verification, and weighted aggregation. Evaluating a single output is only the micro level. When we deploy models to perform actions over time, we enter the meso level, evaluating multi-turn agentic workflows. This models the react loop: observe, plan, act. We must debug agents at the node level. First, tool prediction fails if the model hallucinates a non-existent function. Second, argument errors happen when missing data forces the LLM to pass invalid defaults, like 0, 0 coordinates. The third failure is an execution backend error. If your database crashes, returning a raw Python stack trace directly to the agent will confuse the model and break the loop entirely. Even if a search query yields no results, returning an empty JSON object is vastly superior to returning a none value. An empty JSON correctly signals to the model that the database was successfully queried and nothing was found, allowing it to plan its next move. And finally, we evaluate for synthesis errors. This occurs when a successful tool call returns a massive JSON payload, flooding the context window with raw, unstructured data. This sudden context truncation blinds the LLM. The answer might be buried deep in the payload, but the model cannot parse it, forcing it to falsely tell the user the task failed. Because the agent operates in an autonomous loop, a single node failure causes a cascading collapse of the entire system. Monolithic scoring obscures the root cause. Evaluating agent behavior demands isolating the variables and identifying exactly which node failed and why. When we step back from agents and individual outputs, we reach the macro level. Here, we evaluate raw base model capabilities using strict, hard-coded global standards. This matrix shows the core industry benchmarks: MMLU, AIME, SWE-bench, and TAU-bench. These tests eliminate the subjective noise of an LLM judge by demanding precise, verifiable answers. MMLU tests broad knowledge retention from the model's pre-training phase. It operates across dozens of academic fields using a strictly constrained multiple-choice format. AIME evaluates rigorous mathematical logic. It removes multiple choice entirely, forcing the model to generate its own reasoning path and land on an exact 3-digit numerical output. SWE-bench provides applied coding evaluation. The model is fed a real historical GitHub issue and codebase. We measure performance by injecting the model's proposed patch and running the repository's native unit tests to verify if they pass. TAU-bench shifts to multi-turn agents, simulating retail and airline environments to test policy navigation. Success is measured using pass-hat-k, calculating the strict probability that all k sequential attempts succeed, demanding absolute consistency. These global benchmarks strip away the ambiguity of natural language, providing the objective baselines we need to map the absolute frontier of model capability. But these benchmarks carry a systemic danger. When developers prioritize high scores over general capability, the tests degrade. This is known as Goodhart's law. When a measure becomes a target, it ceases to be a good measure. Due to data contamination, models often memorize the specific questions in these benchmarks during their training phase. They overfit to the test, creating an illusion of capability rather than true analytical intelligence. This is why the complete evaluation stack is your primary defense. You cannot rely solely on a single metric to understand how a model will perform in production. Evaluating free-form truth requires abandoning static text matching. It demands passing automated semantic judges, executing inside simulated agent environments, and verifying against global benchmarks. By integrating all 3 tiers, we build the rigorous engineering framework required to accurately map, measure, and push the Pareto frontier of AI performance. To build these systems yourself, head over to the Learn by Doing with Steven YouTube channel for applied tutorials. For deeper architectural discussions, search for the Steven Data Talk podcast on Spotify and YouTube Music.
In 2017, the original transformer architecture solved a specific, isolated problem, translating text from one language to another, sequence to sequence. Over the past 8 years, those simple text predictors have evolved. Today's frontier models operate as multi-stage, multimodal reasoning engines capable of executing complex autonomous workflows. Reaching this level of performance requires moving far beyond the basic self-attention mechanism. We optimize the internal matrices, build software tailored to hardware memory, deploy new alignment algorithms, and ultimately break the bottleneck of generating text one word at a time. Frontier performance in 2025 depends on the synergy of this entire stack, shifting the engineering focus from raw parameter volume to the precision of the pipeline.
The core engine of the architecture remains the self-attention mechanism. It processes an input sequence by allowing every single token to establish a direct mathematical link to every other token, regardless of how far apart they are placed in the sequence. To process longer sequences, engineers had to rethink how tokens track their location. Instead of assigning a static, absolute position to each word, modern models use rotary position embeddings. This mathematical operation rotates these vectors based on the relative distance between a query and a key, giving the model a dynamic understanding of context. Evaluating all those relationships requires massive memory overhead. Grouped query attention mitigates this by grouping multiple query heads and mapping them to a single key value cache. The network retains high performance while reducing the memory required to store intermediate calculations. This efficiency carries over into the feed-forward network layer through mixture of experts. Instead of passing every piece of data through the entire model, a gating mechanism routes each specific token sparsely to only the relevant subnetworks or experts. By combining rotary position embeddings, grouped query attention, and mixture of experts, engineers decouple the total parameter count of a model from the active compute cost required to run an inference pass. Training a large language model requires striking an exact mathematical balance between model size and data volume. The chinchilla scaling laws establish a rule of thumb. An optimal training run requires at least 20 tokens of data for every single parameter in the model. Processing trillions of tokens exposes a severe physical constraint. The compute bottleneck is not the mathematical operations themselves, but the memory input and output moving the data back and forth to be calculated. Looking at this schematic of a GPU chip, we see the divide. The hardware possesses a large, slow outer ring called high bandwidth memory and a tiny, ultra-fast internal core known as the SRAM. The flash attention algorithm solves the memory bottleneck by dividing the query, key, and value matrices into smaller chunks. These chunks are loaded into the SRAM, computed entirely from end to end, and then written directly back to the large outer memory, skipping the intermediate read and write steps. At the 2025 frontier, software algorithms are tailored specifically to the physical memory hierarchy of the hardware they run on. The pre-training phase teaches a model the structure of language through basic autocomplete. To make the model useful, engineers apply supervised fine-tuning, demonstrating the exact input and output behavior required for specific tasks. The system is further aligned through preference tuning. By using human pairwise data pointing out which response is better, engineers train a separate reward model, utilizing the Bradley-Terry formulation to score the probability of one output outperforming another. Historically, this alignment relied on proximal policy optimization. This logic tree exposes a drawback. Calculating the advantage required maintaining an active value model in memory to establish a baseline for how good a prediction was, effectively doubling the structural overhead. Group Relative Policy Optimization, or GRPO, eliminates that overhead. The algorithm drops the value model entirely. Instead, it samples multiple different completions for the same prompt and evaluates their relative rewards directly against each other. In domains with verifiable ground truth, like math or code, GRPO eliminates the dependency on learned reward models. By comparing multiple samples against a fixed correct answer, the model reinforces the specific reasoning paths that consistently yield the right result. Even highly trained models suffer from a static knowledge cutoff. Retrieval-augmented generation solves this by fetching external, up-to-date documents and injecting them directly into the prompt context. The system retrieves documents in a two-step pipeline. First, candidate retrieval uses a bi-encoder setup, taking the vectorized query and computing the cosine similarity against a database of document embeddings to extract a broad list of matches. That list is then refined through a cross-encoder. The initial query and the retrieved documents are run through a joint neural network to output a highly precise, re-ranked order of the most relevant information. Models interact with external systems through tool calling. The sequence pauses. The model outputs an exact API schema with arguments. An external script executes the action, and the resulting data is fed back into the context window so generation can resume. By coupling precise re-ranking pipelines with deterministic tool execution, engineers convert a static text predictor into an autonomous agent capable of resolving complex logic loops. The underlying transformer architecture is highly adaptable. Vision transformers operate by slicing an image into flat vector patches, treating them exactly the same way an LLM treats discrete text subwords. But whether processing text or images, standard language models face a strict limitation. They are autoregressive. They must predict left to right, requiring 10 separate forward passes to generate 10 tokens of text. Masked diffusion models adapt the parallel generation techniques used in image creation directly into discrete text. As shown in the bottom of this diagram, instead of generating one word at a time, the model starts with a full sequence of blank mask tokens, treating them as the text equivalent of Gaussian noise. The network learns an unmasking function. It refines the entire block of text through coarse-to-fine refinement iterations, stepping from a rough conceptual draft down to the final specific tokens across just a few discrete passes. Abandoning the left-to-right autoregressive bottleneck allows the model to process context in both directions simultaneously. This reduces inference latency, driving speedups crucial for complex coding tasks and agentic workflows. The research pushing these architectures forward is absolutely relentless. New techniques like muon optimizers are actively challenging legacy update rules, while hardware engineers are prototyping analog chips that embed matrix computations directly into physical signals. But an immediate data wall is approaching. As synthetic AI-generated text floods the internet, recursively training models on that low-diversity output leads to model collapse, degrading the underlying data distribution. To solve this and push the limits of cost efficiency, the industry is deploying small language models, meticulously trained on highly curated datasets rather than scraped web data. To start building your own applications using these techniques, check out the Learn by Doing with Stephen YouTube channel. It walks through practical engineering implementations of the systems we cover today. For audio deep dives into the latest research papers, tune in to the Stephen Data Talk podcast. Links to both are in the description below. Advancing the frontier now involves a transition from theoretical discovery to a high-stakes engineering discipline, one that requires the simultaneous integration of optimized hardware, efficient memory management, and verifiable alignment. The core challenge of modern vision models is learning how to map an easily sampleable, chaotic noise distribution into a highly complex data distribution. Think of this generation process like sculpting. You start with an unformed block of variation. By deterministically removing that noise piece by piece, you reveal the target sample hidden inside. The denoising diffusion probabilistic model, or DDPM, is the mathematical framework that systematizes this sculpting process. To understand how this operates, we have to construct the underlying math from first principles. That requires bypassing the intractable probability equations standing between pure static and a clean image. Then we have to address the real-world compute bottleneck. We will break the Markov chain to strip out the latency and achieve massive inference speedups. Mastering these specific mathematical nuances is what turns diffusion from a theoretical academic curiosity into a functional, state-of-the-art engineering system. This timeline establishes our training environment. Far left, x0, a clean image. Far right, xt, pure noise. The forward process incrementally corrupts the image over t steps, using a variance-preserving schedule governed by beta weights. The noise dose steadily increases as we approach total noise, but computing thousands of sequential step-by-step additions during the training phase would force our compute costs to scale out of control. Because the injected noise is drawn from a standard Gaussian, their variances can be summed linearly. We consolidate these into a direct jump variable, alpha bar. This allows us to calculate any specific noise step, xt, using a single operation. This direct jump property gives us a mathematically perfect, computationally cheap way to generate training pairs of any noise level on demand. Now we pivot to the reverse trajectory. We want to find the neural network parameters that maximize the probability of recovering the original training data. This note graph illustrates the mathematical requirement for computing that true reverse probability. It requires marginalizing across every single possible noise trajectory branching backward from step t. In the high-dimensional vector space of an image, the number of potential paths is staggering. Solving this specific integral is completely intractable. We bypass this impossibility using the evidence lower bound, or ELBO. By applying Jensen's inequality to the concave log likelihood function, we extract an expression that acts as a mathematical floor. This entirely bounds the problem. We no longer need to calculate the exact maximum probability, just confidently push this lower bound upward. The practical result? We can sample trajectories directly from our predefined forward process, Q. The ELBO trick saves diffusion models from mathematical dead ends by replacing an impossible infinite sum with a tractable, sampleable expectation. Comparing these curves, we reframe ELBO as a KL divergence problem, an operator measuring how far apart two probability distributions are. The first is the forward-posterior, Q. The second is the neural network, P theta, attempting to predict the exact same step backward. The critical advantage here is that both distributions are structurally Gaussians. Because of this, we possess the analytical solution required to compare them. When we feed two known Gaussians into the KL divergence formula, the complex probability variables structurally cancel each other out. The dense mathematics dissolve entirely, leaving us with a straightforward L2 regression. This reveals a counterintuitive reality about our loss function. The neural network is not predicting pixels or images at all. The network is exclusively predicting the exact noise vector, epsilon, that we injected at time step t. These highly complex, multidimensional probability distributions have now been successfully collapsed into a single, highly efficient geometric distance calculation. The training loss is elegant, but deploying this model for inference exposes a brutal latency problem. To generate a single image, data must be passed sequentially through the neural network up to 1,000 times. This sequence illustrates the mathematical culprit, the Markov assumption. A Markov chain dictates that every step strictly depends on the immediate prior step. Because of this rigidity, the model must inject a mandatory stochastic noise variable between every single node. We solve this inference bottleneck by deliberately breaking the Markov chain using the denoising diffusion implicit model, or DDIM. DDIM operates under one strict constraint. It formulates a new forward process that maintains the exact same marginal probabilities as DDPM. This ensures our pre-trained model weights remain valid. The mathematical leap is achieved by manipulating the hyperparameter that controls step-to-step variance. DDIM manually forces that variance down to 0. Setting variance to 0 strips all stochasticity, transforming generation into a deterministic mapping from noise to image. The model can now approximate the clean data early, executing sweeping mathematical arcs that skip dozens of steps. This compresses a 1,000-step bottleneck into just 20 evaluations. Treating image generation as a rigorous sequence of continuous probability transitions is exactly how we tame isotropic noise into coherent structure. We bypass intractable mathematics in training by optimizing the ELBO, simplifying competing probability distributions down into a basic noise regression. We resolve the massive compute requirements of inference by stripping out the Markovian step-to-step stochasticity, allowing DDIM to leap over the generation bottlenecks. If you want to deepen your practical application and build these systems from scratch, search for Learn by Doing with Stephen. And for high-level discussions on machine learning data architecture, listen to the Stephen Data Talk podcast. Mastering these underlying mathematical mechanics is the crucial difference between engineers who blindly deploy black box models and architects who actively build the future of machine learning.
When we want a neural network to generate new, realistic images, we are essentially asking it to sample from a vast, completely unknown data distribution. Historically, models tried to learn this landscape by calculating the exact probability of every single point. But probability distributions must sum to 1 across the entire space. Computing that normalizing constant, a value known as z, requires summing across millions of dimensions. The math simply breaks down. It is computationally impossible. There is a mathematical workaround. Instead of forcing the model to calculate the absolute volume of the probability, we can teach it to find the gradient. We just need it to point in the direction where the probability gets higher. By discarding the need for an exact probability calculation, we remove the normalizing constant entirely. This specific adjustment takes high-dimensional data generation from mathematically impossible to computationally tractable. This equation defines a quantity called the score. It is the gradient of the logarithm of the probability density function. Because of the properties of logarithms, taking the gradient of the log probability splits the numerator and the denominator. The normalizing constant, z, is a constant with respect to position. Its gradient is 0. The intractable part of the equation cleanly cancels out. What remains is a vector field. At any coordinate in space, calculating the score gives you an exact directional arrow pointing toward the nearest concentration of real data. The lower the probability, the larger the magnitude of the arrow. This score function acts as a mathematical compass. We can start anywhere in the coordinate space and simply follow the gradients step by step to arrive at a realistic image, all without mapping the total volume of the space. To use that compass, we need to train a neural network to predict the score. But doing that directly requires knowing the true probability distribution of the data, which is exactly the unknown variable we started with. Researchers developed a proxy method called denoising score matching. By taking known training images and perturbing them with a small, specific amount of Gaussian noise, we create a mathematical target. The network learns to predict the score of this slightly noise distribution because the score of a Gaussian is analytically tractable. This topographical map reveals a structural flaw in that approach. When we only add a small amount of noise, the training data remains tightly clustered. The model learns the vectors near these dense peaks perfectly. But out here in the vast flat plains between the data points, the network receives almost no training signal. Its score predictions here are entirely inaccurate. To generate a new image, we start by sampling pure random noise. This pure noise places our coordinate in unmapped, low-density plains. When the model checks its compass, the vectors are meaningless. The math behind pure score matching holds up, but the execution fails. The model possesses a precise map of the destination, but has absolutely no navigational data for the origin. Solving this blind spot requires a technique known as a noise-conditional score network. Instead of relying on a single, small noise level, we apply a massive spectrum of Gaussian noise to the training data. This extreme noise aggressively blurs the distinct data clusters, forcing their density to spread out and physically fill the empty voids. The entire space is now covered by a measurable gradient. Generation now begins using annealed Langevin dynamics. The model checks the score at the highest noise scale first. The vector here is blurry and imprecise, but it provides a reliable, broad direction pointing inward from the remote edges of the space. As the particle travels, the solver steps down to progressively lower noise scales. With each step, the topographical map sharpens. The broad slopes recede, the tight data peaks return, and the vector gradients become highly specific, guiding the coordinate to an exact high-resolution destination. By stacking these varying distributions, the network constructs a continuous gradient bridge. It connects the extreme outliers of pure noise directly to the sharp manifolds of realistic data. Look at these two equations side by side. On the left is the denoising diffusion probabilistic model, which preserves variance. On the right is the noise-conditional score network, which explodes variance. While they operate differently, both rely on breaking the noise process into rigid, discrete increments. We can push these sequences to their mathematical limit. If we shrink the time step between noise increments down to 0, the discrete steps vanish. Both models collapse into a single continuous equation, a stochastic differential equation. This forward SDE breaks the continuous noise process into two distinct parts. First is the deterministic drift term, dictating how the data moves linearly over time. Second is the stochastic diffusion term, driven by a continuous random walk known as the Wiener process. Because the forward process is a verified SDE, we can apply an established theorem from 1982. This theorem proves that any forward SDE has a direct mathematical inverse. To reverse the flow of time and extract clean data from pure noise, the equation only requires one missing variable, the score. By moving away from discrete steps into the continuous domain, diffusion and score matching unite.
They are simply two ways of configuring the same underlying differential equation. Watch this trajectory. When we generate an image by solving the reverse SDE, the stochastic noise injects constant randomness. The particle vibrates erratically as it moves. To keep this jagged path aligned with the target data, the solver must constantly self-correct, requiring hundreds or thousands of individual calculation steps. We can remove this computational bottleneck by converting the SDE into a probability flow ordinary differential equation. Using the Fokker-Planck continuity equation, the stochastic diffusion term is mathematically stripped away. The randomness is gone. What remains is a perfectly smooth, deterministic trajectory that maintains the exact same marginal probability densities as the noisy original. Without the need to calculate constant stochastic variations, the solver can traverse the exact same mathematical space using a fraction of the computational steps. The primary engineering goal in deploying these generative models is to reduce the number of function evaluations. Every time the neural network evaluates the score, generation slows down. This diagram shows the probability flow ODE formula. If we analyze the structure, we can separate it into two distinct parts. There is a purely linear equation block and a highly nonlinear block containing the neural network score prediction. Modern numerical algorithms, such as the DPM solver, exploit this separation. By applying the mathematical variation of constants, the solver calculates the linear portion of the trajectory exactly. The computationally expensive neural network is then only queried to discretize the nonlinear portion. By isolating these variables, the model takes massive, mathematically precise leaps forward. The process that once took 1,000 steps to trace is collapsed down to 10 to 20 evaluations, achieving the exact same visual output. To see the code behind these solvers and build your own implementation, search for the Learn by Doing with Stephen YouTube channel. For deeper discussions on the mathematics of generative modeling, find the Stephen Data Talk podcast on your favorite platform.
The most powerful image architectures today operate not by painting pixels from scratch, but by reversing the diffusion of structured data into pure noise. Specifically, we are going to deconstruct denoising diffusion probabilistic models, or DDPMs. To understand how they work, we will construct the forward process, the deliberate corruption of an image, and then navigate the intractable probabilities of reversing that corruption using a mathematical tool called the evidence lower bound, or ELDO. From there, we can derive the remarkably simple L2 loss function that trains the network, and finally utilize DDIM to drastically accelerate the generation speed. Trying to force a neural network to guess the exact configuration of millions of pixels in a single pass is overwhelmingly complex. Modeling the step-by-step decay of information gives the model a much simpler task, predicting tiny, localized increments of noise. This diagram outlines the forward process, Q. We start with a clean image vector, x0, and progressively corrupt it over t steps. At each step, a noise schedule dictates the ratio of original signal to new Gaussian noise, governed by parameters beta t and alpha t. Calculating thousands of steps individually is computationally inefficient. Because we're adding independent Gaussians, their sum yields another Gaussian. This reparameterization trick lets us calculate any noisy state, xt, directly from the clean image, x0, using the cumulative product of signal ratios, alpha bar t. Bypassing sequential forward steps is the critical mechanic here. It allows the system to instantly generate millions of highly randomized training samples on the fly, making the entire training pipeline computationally viable. Our ultimate generative objective is finding the neural network parameters, theta, that maximize the probability of generating actual training data. Mathematically, this target is log p theta of x0. Here is the fundamental roadblock in this diagram. Computing that target probability requires marginalizing, or summing, over every single possible trajectory from pure noise at step t all the way down to the clean image at step 0. Attempting marginalization across thousands of steps creates a combinatorial explosion. The math is strictly intractable. To bypass this, we rely on the evidence lower bound, or ELBO, providing a safe, computable proxy for our target probability.
To derive the elbow, we start with our target probability and multiply it by a fraction of the known forward trajectory, Q over Q. Multiplying by 1 changes nothing algebraically, but it injects the forward process into our equation. Next, we apply Jensen's inequality. Because the logarithm is a concave function, this rule allows moving the logarithm inside the expectation over those trajectories. Moving that logarithm formally guarantees that the resulting expression is a lower bound. Optimizing this new equation will continually push our true target probability upward. The elbow framework successfully transforms an impossible global probability calculation into a highly tractable, localized sampling problem that a neural network can actually solve. Expanding the elbow reveals the Kullback-Leibler, or KL, divergence, which compares two specific probability distributions. The first, Q, represents the probability of stepping back to a less noisy image, assuming we know both the highly noisy image and the ground truth clean image. Computing this backward step directly is difficult. Our forward process Q is defined as moving from clean to noisy, meaning we need a mathematical inversion. Because the forward process is Markovian, depending only on the prior step, we apply Bayes' rule to invert the probability. The complex Q terms physically rearrange. Forward probabilities act as numerators and denominators, striking each other out, collapsing into a single, smooth Gaussian bell curve. The result is that this conditional probability is no longer intractable. It becomes a fully analytical, computable Gaussian distribution. This calculation is only possible during training. We can compute this specific Gaussian solely because the system has access to the ground truth data, x0. Anchoring the abstract, uncertain reverse step to the definitive x0 training data provides the fixed target the neural network needs to learn effectively. To finalize our training objective, we require one last assumption. The neural network, p theta, must also be designed to output a Gaussian distribution. Computing the KL divergence between two known analytical Gaussians causes almost all complex algebra to collapse, leaving behind only this simplified L2 distance equation. In this regression, the network takes two inputs, a noisy image, xt, and the time step, t. It is strictly tasked with predicting epsilon theta. That output is directly compared against epsilon, the exact pure noise originally added to the clean image. The immense, intractable complexity of generating photorealistic reality reduces mathematically down to a remarkably basic, elegant noise subtraction problem. This architecture creates a fatal bottleneck at inference time. To create a new image, you must execute the neural network sequentially for thousands of individual stochastic steps. The architectural solution to this speed limit is the denoising diffusion implicit model, or DDIM. The primary mathematical pivot in DDIM defines a new family of forward processes, Q sigma. These are non-Markovian, but perfectly match the marginal distributions of the original DDPM. The specific mechanical change is setting the stochasticity parameter, sigma, to absolute 0. Setting sigma to 0 makes the transition from xt to xt-1 strictly deterministic. We completely eliminate random noise injection. Without stochastic noise accumulating, the system can mathematically skip intermediate steps without destroying final image fidelity. Breaking the Markov chain requirement turns an academically elegant but sluggish model into a commercially viable high-speed architecture. State-of-the-art generation is achieved not by trying to predict the geometry of pixels, but by learning the precise geometry of noise. We leveraged the elbow and KL divergence to turn an impossible, multi-dimensional probability problem into a highly tractable L2 regression. By manipulating the underlying stochasticity through DDIM, we successfully enable rapid, highly scalable deployment in the real world. To explore deeper coding implementations of these models, head over to the Learn by Doing with Stephen YouTube channel. And for continuing high-level academic and industry machine learning analysis, stream the Stephen Data Talk podcast on YouTube Music and Spotify. Running unconditional generation directly on pixels yields chaotic, unpredictable exploration. But modern models instantly resolve into highly specific, complex structures based on precise user prompts. Generating an image relies on stochastic differential equations, or score matching, to reverse a noise-adding process. You start with standard normal noise, and a neural network predicts a vector field to denoise it back into an image. The mathematical bottleneck here is dimensionality. To output a standard 1024 by 1024 image, the algorithm must operate across more than 3 million distinct RGB color dimensions simultaneously. Calculating the trajectory of every pixel through that high-dimensional space takes massive compute. This topological map reveals the pixel space problem. Valid images are compressed, isolated spikes separated by vast planes of meaningless noise. Adding slight noise to an image pushes it off the spike into the flatlands, instantly destroying the structural signal entirely. To make generation tractable and prompt-driven, we must solve 3 distinct architectural problems: compress the data, condition it with text, and steer the mathematical noise. The mathematical elegance of flow matching is entirely constrained by its operational space. To truly scale these algorithms, we must engineer an escape from pixel space. The standard approach to data compression is an autoencoder. You pass an image through a neural network encoder, forcing it through a bottleneck to extract a static, lower-dimensional representation, and then a decoder rebuilds the pixels. Standard autoencoders fail for generative tasks because they do not impose any geometric structure on the bottleneck. The resulting latent points are scattered randomly. A diffusion model starting from standard normal noise will easily get lost trying to find them. We solve this with a variational autoencoder, or VAE. Instead of mapping an image to a single fixed point, the VAE encoder outputs a probability distribution, predicting a mean and a fixed variance. Every input maps to a region of probable points. Training this network requires maximizing the likelihood of the data. Because calculating every possible latent state is impossible, we derive an evidence lower bound, or ELBO, using Jensen's inequality. This provides a tractable loss function composed of 2 highly specific penalties. The first component of this loss is straightforward reconstruction loss. We decode a sample from the latent distribution and compare it directly to the original image using a pixel-wise L2 penalty. The second component is the KL divergence. This penalizes the model if the distributions generated by the encoder stray too far from a standard normal prior. It forces the overlapping bell curves to group together into a smooth, searchable normal distribution. But an L2 pixel-wise penalty causes a severe artifact: blurriness. If a generated texture is off by just a few pixels, the strict L2 distance treats it as a massive error. The network responds by averaging the values, outputting a blurry, safe guess. We strip out this blurriness by adding 2 additional losses. Perceptual loss, or LPEPS, runs both images through an external feature extractor and compares their deep structural maps, ignoring minor spatial shifts. Adversarial loss pits the decoder against a GAN discriminator, forcing it to generate high-frequency, realistic textures to fool the network. The resulting VAE successfully divides the labor. The encoder acts as a low-pass filter, ignoring exact pixels to build a smooth, semantically ordered latent space. The heavier decoder takes those compressed coordinates and hallucinates the high-frequency perceptual details. With a continuous latent space established, we need a mechanism to guide the generation using user input. This requires translating discrete text strings and raw visual data into a shared mathematical language. On the text side, we break sentences into tokens and feed them into an attention-based transformer encoder. Each token generates an embedding by looking at every other token in the sequence, contextualizing its meaning. For the visual data, we use a vision transformer. Instead of scanning pixels individually, the network divides the image into discrete patches, treating each patch the exact same way a language model treats a word. This image of a teddy bear is flattened into these discrete patches. The transformer learns an initial linear projection for each patch and routes them through self-attention layers to map the geometric relationships. Compare that to these water polo players. In a training patch, we feed the network massive amounts of image caption pairs scraped from the internet. The teddy bear caption is the positive match, making the water polo caption a deliberate in-batch negative. To summarize these sequences, we extract a single dense vector from the end of both networks, the CLS token. These tokens carry the aggregated global semantic identity of the entire sentence and the entire image. Next, we multiply both tokens by a final learnable projection matrix. This aligns the output of the vision transformer and the text transformer into a single unified dimensional space where they can be directly compared using a dot product. We train this using contrastive learning. We calculate the exponential similarity between an image and every text token. The loss function pulls the matching pairs closely together while pushing the negative pairs, like the teddy bear and the water polo match, as far apart as possible. This creates CLIP. It provides a highly accurate multimodal coordinate map. We can now convert any human text prompt into a specific mathematical coordinate, giving our diffusion model an exact destination within the VAE probability field. We have a smooth latent space, and we have our specific CLIP coordinates. The final problem is forcing the diffusion vector field to actively steer toward those coordinates at every inference step. The first attempt was classifier guidance. By applying Bayes' rule, researchers shifted the trajectory by calculating the gradient of a separate classifier. But training this Gestalt classifier is highly unstable. Running a full backward pass at every step is computationally expensive and scales poorly. We eliminate the external network using classifier-free guidance, or CFG. Using Bayes' rule again, we can mathematically derive an implicit classifier by isolating the difference between the diffusion model's unconditional generation and its conditional generation. To build this, we alter the training loop. 10 to 20% of the time, we deliberately drop the text condition entirely. This forces the single diffusion network to learn both the unconditional base distribution and the conditional semantic distribution simultaneously. At inference, the model predicts two noise values, one with the text condition, one without. We subtract the unconditional noise from the conditional noise to isolate the pure direction of the prompt. We then scale that difference by hyperparameter W, forcefully extrapolating the vector further. CFG extracts the raw mathematical signal of the text condition. By relying exclusively on forward passes within a single network, it violently steers the generation process without the massive compute overhead of a secondary classifier. When you type a prompt, you are triggering this exact pipeline. The text is tokenized and passed through the CLIP encoder, mapping your words to a highly specific multidimensional coordinate. That coordinate locks into the smooth, continuous topology prepared by the VAE, identifying exactly which region of the latent space holds the semantic concept you requested. The diffusion model samples random noise and evaluates it. The CFG algorithm kicks in, calculating the unconditional and conditional vectors, scaling the difference and aggressively pushing the noise closer to the CLIP target at every discrete time step. Once the noise is resolved into a clean, latent representation, the VAE decoder takes over. It inflates those compressed coordinates, referencing its GAN-trained adversarial weights to output a photorealistic, high-frequency image into pixel space. The VAE creates a continuous playground. CLIP provides an exact coordinate map. CFG provides the steering wheel. Together, they make diffusion tractable. To build out the ML infrastructure supporting pipelines like this, check out Learn by Doing with Steven on YouTube. For a deeper breakdown of data architecture and scale, listen to the Steven Data Talk podcast, available on Spotify and all major audio platforms. For a physical AI agent to operate in the real world, it needs a functioning internal simulator. It must accurately predict the future state of its environment based entirely on what it sees right now, combined with the specific action it is about to take. The prevailing approach to this problem relies on generative world models. These models attempt to simulate the future by rendering highly detailed pixel-level environments, predicting exactly what the next frame of a video should look like. This split-screen diagram highlights the inefficiency of the generative approach. The left model wastes computational power, calculating irrelevant background noise, instead of focusing on core physics. JEPAs discard pixel generation entirely. Instead, they predict outcomes as vectors in an abstract mathematical space. While large language models can predict text autoregressively, physical AI operates under different constraints. It requires action-conditioned prediction. The model must calculate how its own interventions alter the environment while managing the inherent physical uncertainty of the real world. This suggests that robotic agility doesn't depend on memorizing specific tasks. If the agent understands the underlying mathematical dynamics of the environment, it can calculate successful actions for entirely new goals on the first attempt. JEPAs operate as energy-based models. They are designed to output a low energy score for compatible, mathematically plausible future states, and a high energy score for impossible physical sequences. In this predictor architecture, states X and Y pass through an encoder to minimize distance to the future state. But without a visual anchor, the encoder can just dial its weights to 0, outputting a constant vector. Loss hits 0 instantly, learning no physics. This failure mode is known as representation collapse. The network takes the mathematically laziest route to minimize its loss function, flattening all data into a meaningless constant. Traditional machine learning fixes for this, like contrastive learning parameters or tracking exponential moving averages, are often computationally heavy, difficult to tune, and frequently unstable. To safely operate in latent space, researchers deploy either strict structural biases to force the network's hand or statistical regularization to keep representations informative. Researchers at Brown University approached the collapse problem by building strict structural inductive biases directly into the network architecture. Instead of processing an image as a flat grid of patches, they utilize slot attention. As shown here, raw visual features are sorted into discrete, dedicated object baskets. Each physical object gets its own isolated node in the latent space. Causal JEPA leverages this slot architecture to prevent collapse through aggressive object masking. As the node is blacked out, the model completely hides an entire object node and forces the bidirectional transformer to reconstruct that missing state from the remaining visible nodes. If you cover a banana with an invisible cloth, but you can still see a monkey moving its mouth, you can deduce that the banana is getting smaller. The model must perform this exact same deduction, inferring the state of a masked object entirely from the behavior of the visible ones. By requiring this cross-object deduction, the network is forced to abandon constant vector shortcuts. It has to accurately calculate the influence neighborhood, the predictive dependencies between distinct objects. Structurally hiding entire objects, rather than random pixel patches, forces the architecture to learn strict, temporally directed physical relationships. Earlier iterations of action-conditioned models handled robotic inputs by taking the action data and concatenating it onto the end of the visual patch embeddings. This concatenation method dilutes the causal impact of the action. It blurs a specific robotic movement into the general, undifferentiated visual noise of the environment. Causal JEPA treats the robotic action as an entirely separate, distinct node. As the action node connects, it explicitly connects to and alters specific target object nodes, rather than merging into a massive block of state data. This explicit action node architecture mirrors human physical reasoning. It tracks specific interventions applied to specific targets. Treating actions as independent causal triggers allows the model to reliably predict the cascading physical effects of a specific robotic intervention. An alternative solution, developed by researchers at the University of Montreal, prevents collapse without requiring the architectural complexity of slot attention. Previous end-to-end models required multiple interacting loss functions, including spatial and temporal variance-covariance matrix minimization, just to prevent the embeddings from degrading. Simple JEPA is a minimalist model. It eliminates the auxiliary components, like exponential moving averages, stop gradients, or pre-trained encoders, relying instead on a single hyperparameter for its internal regulation. The core mechanism allowing this efficiency is CREG, an isotropic Gaussian regularizer. It forces the batch of latent embeddings to maintain a highly informative Gaussian distribution. This scatterplot represents the high-dimensional latent space. Running statistical tests to ensure a Gaussian distribution in a space this dense is computationally demanding, a limitation known as the curse of dimensionality. CREG bypasses this with a mathematical workaround. As the projection occurs, it samples random one-dimensional lines and projects the high-dimensional embedding data onto them. According to Wald's theorem, if the model optimizes these one-dimensional marginal distributions to be Gaussian, the entire high-dimensional joint distribution also becomes Gaussian. The data stays rich and representation collapse is prevented. CREG provides a statistical safety net. A lightweight 15 million parameter architecture can learn robust physical dynamics entirely end-to-end, directly from raw pixels. When applied to 3D robotic manipulation tasks, like the OG bench environment, this pure latent approach yields significant performance gains. This chart compares planning latency for model predictive control. A highly optimized patch-based generative world model requires 47 seconds to plan a sequence. The simple JEPA model, operating entirely in latent space, executes the full planning sequence in under 1 second. This 50x speed increase comes directly from eliminating the pixel-level decoder. It avoids the computational cost of running patch-wise attention to predict thousands of individual future pixels. By operating strictly on a single condensed latent vector, optimization algorithms can backpropagate through thousands of potential future scenarios almost instantly. Real-time robotic agility requires an agent that simulates future states in abstract latent mathematics rather than generating heavy visual images. To verify the model has actually mapped the rules of intuitive physics and isn't just memorizing frame-by-frame correlations, researchers hit the simulator with impossible events. This graph tracks the model's prediction error. If a simulated cube changes color, the error line remains flat. Color doesn't impact physical dynamics. But the moment a cube teleports across the screen, the prediction error spikes drastically. A core physical rule was violated. The framework does face current limitations. In highly simplistic environments with low intrinsic dimensionality, the C-reg regularizer struggles. The model is forced to invent fake variants just to satisfy the isotropic Gaussian requirement. Extending these latent models to long-horizon hierarchical reasoning, understanding the difference between planning a cross-country flight and planning a single footstep remains an active engineering challenge. Solving representation collapse in JEPAs pushes agents past simply mimicking visual reality. It forces the architecture to mathematically comprehend the constraints of the physical world. To continue exploring the bleeding edge of AI, machine learning frameworks, and data science, check out the Learn by Doing with Steven channel on YouTube and other video platforms. And for deep dive audio discussions, subscribe to the Steven Data Talk podcast, available on YouTube Music, Spotify, and everywhere else you get your podcasts.
You type a complex question into a chat window. Within milliseconds, a perfectly formatted, highly intelligent response streams across your screen. Most leading models run on the same transformer architecture, using the same fundamental code regardless of which tech giant built them. The real differentiator is a massive industrial pipeline divided into 4 sequential stations: data engineering, system scaling, pre-training, and post-training. To understand how these models actually work, we need to trace a single piece of text through one of these pipelines, a production run that can cost upward of $75 million and take months to complete. Constructing these models demands a level of logistical precision and hardware coordination that rivals the most complex global manufacturing projects. Curious, the process begins by scraping the web, downloading roughly 250 billion internet pages to build a petabyte-sized dataset. But a random sample of the internet is a chaotic mess of broken code and endless boilerplate menus. Engineers use automated heuristics and smaller machine learning classifiers to aggressively filter out the garbage, keeping only the highest quality text. Even clean text presents a problem. Neural networks struggle to process raw words directly because of varying lengths, typos, and the different spacing rules used across global languages. The solution is tokenization. A specialized algorithm scans the text and chops it into common sequences of about 3 to 4 letters. Each of these sequences, or tokens, is assigned a unique integer ID that the model can mathematically process. Once the text is tokenized, the core pre-training phase begins. The model looks at a sequence of tokens and predicts the most likely next block. If it reads, "The mouse ate the probability distribution graph heavily favors the token for cheese. It learns this by calculating cross-entropy loss over trillions of similar examples. By absorbing a significant fraction of human knowledge, the raw model masters the mathematical probability of human syntax. It maps statistical relationships across a massive vocabulary to understand how tokens typically follow one another. This chart shows what we call scaling laws. When plotted on a log scale, increasing computation, data, and parameters yields a predictable drop in test loss. Adding more compute makes the model consistently better. Because of this predictable math,
Companies spend tens of millions of dollars to string together tens of thousands of specialized graphics processing units, or GPUs. Physical scale creates a unique bottleneck. Data movement between memory and compute cores often takes longer than the actual processing, leaving expensive hardware waiting for information to arrive. To keep these supercomputers from sitting idle, systems engineers use extreme tactics. They compress mathematical calculations down to 16-bit precision to shrink file sizes and use operator fusion to do all the math in one trip, rather than constantly shuttling data back and forth. At the highest levels of development, success depends on whoever can successfully move data through silicon the fastest. A purely pre-trained model is practically useless for a normal user. Because it was trained on the entire internet, asking it a question often results in it generating a list of related questions, mimicking the format of an online forum. To fix this, engineers run a phase called supervised fine-tuning. They feed the model thousands of high-quality human-written examples to force the underlying statistical engine into a strict question-and-answer format. Supervised fine-tuning focuses on structural formatting. When a model attempts to match a human's desired output using information it never learned during pre-training, it produces the plausible inventions we call hallucinations. The final correction is reinforcement learning from human feedback. Human graders are shown two different AI-generated responses and choose the better one. This preference data steers the model's behavior, penalizing bad outputs and rewarding helpful ones. Without this post-training alignment, a large language model is a chaotic probability engine. Human intervention is the tool that physically sculpts it into a polite assistant. This brings the industry to a massive hurdle: evaluation. Once an AI is aligned to answer open-ended questions like a human assistant, traditional mathematical tests for accuracy become unreliable. There is no single correct answer to a creative writing prompt. Metrics used during pre-training, like perplexity, which measures a model's statistical uncertainty, lose their utility here. The alignment process trained the model to act as a definitive policy, stripping away its natural distribution of probability. The modern solution is the chatbot arena. Developers rely on blind, crowdsourced human voting. Random users chat side by side with two unnamed models and cast a vote for the one that provides the better response. Despite the petabytes of raw text ingested and the millions of dollars spent cooling supercomputers, the final judge of an artificial intelligence's worth remains subjective human preference. To start experimenting with these models yourself, subscribe to the Learn by Doing with Steven YouTube channel. And for deeper dives into the data science driving this technology, check out the Steven Data Talk podcast, available now on Spotify and YouTube Music. This chart shows how AI systems historically responded to receiving more data. On the bottom axis, we have the sheer amount of data fed to a system, and on the vertical axis, its accuracy. If you test older, traditional machine learning models, like decision trees or logistic regression, they hit a hard ceiling. Even after absorbing thousands of hours of data, their accuracy flattens out into a plateau. They simply didn't know what to do with all that extra information. But an entirely different architecture called a deep learning network acts differently. If you map a neural network on this same graph, that plateau disappears. Instead of flattening out, a deep learning model continuously digests that massive ocean of data, and its accuracy climbs steadily upward. The hardware capable of processing that kind of scale didn't originate in massive corporate data centers. About 15 years ago, an undergrad named Ian Goodfellow built a controversial computer server directly inside his Stanford dorm room. By using consumer-grade GPUs, hardware originally meant for video games, to train neural networks, he proved these massive computations could be executed efficiently. Combining immense data with heavy GPU computing unlocked a predictable mathematical reality known as scaling laws. Researchers realized that if they purchased a specific number of GPUs and added a specific volume of data, they could precisely forecast how well the resulting AI would perform. That predictability allowed companies to invest billions with total confidence. Artificial intelligence shifted from a volatile academic experiment into a highly reliable industrial-scale engine. To navigate this ecosystem, you have to look at the modern AI stack. The base layer begins beneath AI entirely. It starts with core computer science fundamentals: understanding how memory, software architecture, and code physically interact with the machine. Stacked directly on top of that is traditional machine learning. These are the classic algorithms built to extract basic patterns from data without relying on massive layered networks. The critical middle layer is the deep learning layer. This is the highly scalable neural network engine that digests the world's raw data and drives the heavy computations. Sitting at the very top is generative AI. This is the consumer-facing application layer that writes code and creates images, but it relies entirely on the heavy lifting performed by the deep learning engine underneath it. The general public interacts almost exclusively with that shiny generative AI surface. However, for builders and engineers, the actual control and economic value requires mastering the deep learning core. Operating inside that deep learning layer is rarely about searching for perfect mathematical truth. Instead, it is a gritty, highly empirical process of testing software to see what actually functions in the real world. The first step to gaining that control is stepping away from the automated frameworks that do the work for you. You have to build basic neural networks entirely from scratch using raw Python code, ensuring you understand the physical mechanics of the algorithms. Next comes hyperparameter tuning. This requires manually adjusting the settings that govern the network, like its learning rate or total size. In practice, this involves staring at a screen at 2 in the morning, tweaking variables through endless trial and error, until the model finally trains correctly. That trial and error requires a highly disciplined development process. Without one, teams routinely misdiagnose their systems, blindly purchasing expensive GPUs they don't need, or wasting 6 months collecting extra data that does nothing for their specific application. Ultimately, success relies on rapid, quick and dirty prototyping. You have to build fast to discover the bizarre quirks hidden inside your dataset, and to confirm whether users actually want the tool you are trying to build. Once you establish that disciplined workflow, you can deploy specialized architectures. If building a computer vision application, you use a convolutional neural network. This acts as filters, slicing images to identify precise patterns. But to process an ongoing stream of information, like audio or sentences, you use sequence models, structured to read data in a linear order. The famous transformer architectures that power modern language models are simply a highly scaled, specialized evolution of these sequence models. Mastering these core architectures allows a developer to bridge radically different industries. The same logic used to identify financial fraud in real time is what enables researchers to model complex shifts in the global climate. This chart illustrates a trap for growing applications. Prototyping with a large language model is cheap, but as your user base grows on the bottom axis, API bills skyrocket exponentially. To survive, pull your deep learning skills back out. By fine-tuning a smaller, open-source model in-house, you bend that massive cost curve down to a manageable baseline. Operating efficiently at this level requires a specialized vocabulary. You have to navigate vector databases and implement concepts like retrieval-augmented generation, a technique that connects your language model directly to your own secure external knowledge sources. This shift has sparked intense anxiety over whether AI will eliminate coding jobs. The reality on the ground is that companies are desperate to hire, but they're rejecting developers who refuse to adapt. An engineer with 10 years of experience using old workflows is routinely passed over for a recent graduate who uses AI to write code faster. The most lucrative and unfilled roles in tech demand a specific hybrid profile. You need a rigorous grasp of computer science fundamentals so you know exactly what to tell the machine, paired with extreme fluency in AI coding assistants to execute the work. Because these coding assistants lower the technical friction, the barrier to creating software has dropped dramatically. It is no longer restricted to computer science majors. Today, climate scientists, educators, and mechanical engineers now have the explicit power to build and deploy complex applications themselves. If you want to master these layers and build out your own AI skill stack, you can start practicing today by heading over to the Learn by Doing with Steven YouTube channel and checking out the available platforms. And for deep dives into the trends and engineering actively shaping this technology, listen to the Steven Data Talk podcast on YouTube Music, Spotify, or wherever you get your podcasts. The tools required to build the future are sitting directly in front of you, completely accessible. The only requirement now is the discipline to actually start building. When we think of artificial intelligence, we often imagine an autonomous brain learning in a digital void. But here, in the labs where these models are actually built, machine intelligence is built on the back of massive human labor. This is the standard loop of supervised learning. You feed the system an input, like a photo. A human provides the ground truth, a label that says, "This is a cat." A loss function then measures the gap between the machine's guess and that label and recalibrates the model until they match. It works for simple tasks, like identifying whether a photo was taken during the day or at night. But to make this reliable, you need tens of thousands of images covering every possible lighting condition. The problem is that reality is messy. Take this image. The sun is technically visible, but it's low on the horizon. A human might label this as dusk, but in the Arctic, this could be noon. When environmental edge cases collide, manual labeling becomes a subjective, unscalable chore. Moving from images into audio introduces a temporal dimension. For a device to wake up to a trigger word like activate, it has to listen to a continuous stream of sound. A binary yes or no isn't enough here. To train the model, a human must scrub through the waveform and identify the exact millisecond the word begins and ends. This is the bottleneck. Supervised learning relies on humans cataloging the world by hand, a process that fails as soon as we move into the infinite complexity of real-world environments. To bypass the need for manual scrubbing, engineers developed a shortcut: synthetic training data. We can take a recording of a crowded subway car, which is essentially free background noise, and computationally overlay a clean recording of the word activate. Because a computer did the mixing, the system automatically knows the perfect timestamp of the trigger word. A single script can then pitch shift the voice, speed it up, or add echoes to simulate thousands of different rooms. In a few hours, this process generates millions of data points without a human ever touching a waveform. While synthetic generation solves the immediate labeling problem, it doesn't give the machine true understanding. To achieve that, the model has to learn to see the world without our help. To move beyond human labels, machines need a way to translate raw information into a geometry they can navigate. They need a mathematical language for concepts. Facial verification is a perfect example of why this is necessary. A computer can't rely on pixel-to-pixel comparisons. A change in lighting or a new pair of glasses would make the same person look like a stranger to a rigid algorithm. Instead, we use a triplet loss mechanism. The system takes an anchor photo and a positive match of the same person. It translates both into a long string of numbers, an embedding, and pulls them together in a shared mathematical space. When we introduce a negative image of a different person, the math pushes it to the far edge of the grid. By iterating on these triplets, the AI builds a map where distance represents difference and proximity represents similarity. These embedding vectors allow the model to organize reality based on underlying features, like the structure of a nose or the shape of an eye, rather than superficial surface details. Engineers are now using this logic to train models on massive, unlabeled datasets through a process called contrastive learning. We can take an image of a dog, crop it, and rotate it. To a machine, these look like different sets of pixels, but we tell the model they must have the same embedding vector. This forces the AI to learn that an object remains the same regardless of its orientation. This same label-free philosophy is the engine behind modern text models. We call it next token prediction. By scraping billions of articles and masking random words, we force the model to develop logic and factual recall just to guess the missing word. Through this simple task of filling in the blanks, the model develops emergent behaviors. It begins to understand the relationships between concepts, like why a cup is likely to be paired with a liquid, simply by processing the patterns of human knowledge. For a long time, AI models were specialists, confined to a single sense like vision or text, but human experience is multimodal. We hear a bark and expect to see a dog. Weakly supervised learning allows engineers to bridge these gaps. Instead of creating new labels, they harvest the loose pairings that already exist on the internet, like text captions on photos or the audio tracks synced to video frames. Breakthroughs like ImageBind use text as a universal shared space. Because text can be linked to both an image and a sound, it acts as a central hub that allows entirely different types of sensory data to communicate with each other. This creates a system that can hear a sound and instantly generate a corresponding visual or even a thermal image. It is connecting modalities it was never explicitly taught to pair. By moving past the human-labeled bottleneck, AI has shifted into a role where it maps the interconnected world without constant supervision. It has evolved from a student memorizing flashcards into an observer of the world's patterns. To start building these systems yourself, visit the Learn by Doing with Stephen YouTube channel for practical tutorials. For a deeper look at the data driving these shifts, listen to the Stephen Data Talk podcast on YouTube Music and Spotify.
In traditional software engineering, you are the absolute dictator. You write a piece of code, compile it, and the machine executes your commands exactly. The logic is strictly deterministic. Artificial intelligence flips that relationship. You can write the code, but the behavior is dictated by data. No human can look at every single image in a massive data set. You never know exactly what strange edge cases your system has learned. Imagine you're the CTO of a 3-person startup. Your goal is to build an AI smart lock that scans faces to unlock corporate doors. You can train a model perfectly in a controlled lab, but eventually someone approaches the camera stepping out of harsh shadows while pulling a thick winter scarf over their mouth to block the wind, or they show up wearing heavy, reflective sunglasses. You cannot anticipate every lighting condition, fashion choice, or strange facial expression in advance. Because of that, getting the model right on your first attempt is practically impossible. Building a functional AI system is an ongoing exercise in empirical trial and error. You build, you deploy, and you discover what unexpected things are actually hiding in your data. The first mandatory step in this pipeline is data collection. A common trap is spending months trying to curate a flawless dataset before writing a single line of code. That wait is a fatal execution error. A more effective strategy is a 48-hour data sprint. You grab a camera, head to a busy campus cafeteria, and ask people to opt in for a quick photo. You prioritize momentum over quality, gathering raw, messy examples as quickly as possible. Training a basic face recognition model takes hours. Letting data collection become a months-long bottleneck grinds your pipeline to a halt. Once trained, you run error analysis, watching the model break to pinpoint where it fails, like misidentifying blurry faces. You then actively engineer your data, feeding new targeted examples back into the pipeline to fix the exact vulnerability. This isn't limited to computer vision. When prompting a large language model, you're interacting with a system trained on more data than anyone could read. Since you don't know the specifics of those trillions of tokens, you can't predict how the model will react. You have to build a prototype, test its responses for errors or safety issues, and refine it based on what you find. It's the exact same empirical loop. Failing fast reveals your true data gaps. Discovering those gaps and engineering specific solutions is the only viable methodology for building robust systems efficiently. Eventually, your face recognition model works well in testing. Now you have to attach it to a physical door out in the real world. This introduces a harsh compute constraint. Streaming a live 24/7 video feed from that door to a large cloud-based neural network is computationally massive and completely unaffordable for a startup. The solution is visual activity detection, a cheap preliminary gatekeeper at the edge. The fastest way to build this is a script that calculates if pixels change to detect movement. But out in reality, a swaying tree or passing car spikes that count, flooding your server with useless video. To fix this, you execute a pivot, replacing the script with a lightweight neural network to detect human presence. It isolates the subject and selects only the single perfect frame to send. Successful real-world deployment is rarely about having the smartest overarching AI. It is about building clever, constrained architectural funnels to protect it from unnecessary noise. There is a dangerous assumption among junior developers that scoring perfectly on a controlled lab test means the project is finished. This is the test set fallacy. This clean curve represents the baseline of your original training data. But the moment a model goes live, it faces data drift. The real world actively changes over time, constantly degrading the performance of static models. Winter arrives and users put on thick scarves. Seasons change, bringing out dark sunglasses. Or you take a self-driving car model trained in California and move it to Texas, where the traffic lights are strung horizontally.
The physical reality of the environment literally shifts away from your training data. Because of this constant drift, a machine learning engineer's job heavily revolves around long-term post-deployment maintenance. Engineers build predictive dashboards to monitor subtle behavioral metrics. They track details like latency, or specifically how many times a user is forced to re-authenticate their face before the door finally clicks open. These metrics act as early warning alarms. A spike in the re-authentication rate exposes hidden user frustration, pointing out exactly when it is time to capture fresh data and update the model. Building an AI project is an ongoing process. You don't write the code and walk away. You manage a living, breathing system that must constantly adapt to survive its environment. If you want to move past the theory and get hands-on, head over to the Learn by Doing with Steven YouTube channel for practical tutorials. And for deeper strategic discussions, check out the Steven Data Talk podcast on YouTube Music and Spotify. Links are in the description.
We interact with AI through a simple text box, but that interface is a leaky abstraction. When you rely solely on prompting, you restrict yourself to a predefined sliver of the actual design space, completely walled off from the mechanics driving the output. To understand how these systems actually operate, you have to bypass the API entirely. You must tear up the entire software and hardware stack and examine the physical limits of the infrastructure. One way to frame the challenge of training is as a product of efficiency and resources. If accuracy is the objective, researchers must treat algorithmic efficiency as the primary lever for maximizing the output of a fixed compute budget. At the frontier scale, where training runs cost hundreds of millions of dollars, you cannot achieve higher accuracy by simply throwing more hardware at the problem. You have to ruthlessly optimize the algorithmic design to squeeze every possible operation out of your memory bandwidth. Constructing a language model from the ground up requires mastering 5 specific engineering disciplines. But before any parameters are updated or matrices are multiplied, the entire process relies on a bedrock layer of data compression. Understanding these layers step by step is the necessary path to transition from querying a pre-existing system to architecting a new one. The foundation is training basics. This is where we define the mathematical shape of the system, selecting the transformer architecture, allocating parameters into a mixture of experts, and tuning hyperparameters to maintain strict stability. The second layer is systems. Processing chips are extremely fast, but they sit physically separated from where the data is actually stored. Moving information from memory into the processor creates an intense structural bottleneck. To close that gap, engineers write custom CUDA kernels. These are specialized software instructions designed to minimize data travel, locking the compute sequences to match the exact high-bandwidth memory transfer speeds. Above that sits the third pillar, scaling laws. When a single training run carries an enormous financial cost, trial and error is no longer an option. You extrapolate performance using strict mathematical curves established on smaller models, predicting the exact loss you will achieve before the full-scale run even begins. The final 2 tiers dictate the model's actual utility: data curation and alignment. Here, vast reserves of raw web crawls are aggressively filtered and deduplicated before applying weak supervision techniques like direct preference optimization to shape the model's ultimate output behavior. To make this entire stack operate, we have to look back at the precise moment raw text first enters the machine. While alignment and scaling generate the majority of public interest, the throughput of the entire stack is capped by how effectively we compress raw text into the machine. A neural network has no concept of a human alphabet. The transformer architecture operates strictly on numerical indices. The most obvious way to translate text is to assign a unique integer to every single character. But treating every letter as its own data point stretches sentences into highly elongated, inefficient sequences. This directly triggers the core constraint of the transformer architecture. The computational cost of the attention mechanism scales quadratically relative to the sequence length. If you feed a character-by-character sequence into the model, that squared cost curve spikes. It instantly exhausts the GPU's memory bandwidth,
grinding the entire training process to a halt. You could try the exact opposite approach. You could map entire, complete words as individual indices, keeping the sequence lengths as short as possible. But natural language contains millions of rare words, misspellings, and names. Attempting to map them all creates an unbounded, massively expanding vocabulary. This introduces severe matrix sparsity, transferring the overload directly to the embedding layer and blowing up the memory footprint in a different way. Rigid rules create a trap. Small units exceed compute limits, large units exceed memory limits. To thread the needle, the system requires an adaptive, dynamic compression algorithm. The industry standard solution is an algorithm called byte pair encoding. The process begins by stripping all text down to raw UTF-8 bytes. Because a byte can only hold 256 possible values, the system starts with an absolute baseline vocabulary size of exactly 256. The algorithm then sweeps across the entire training corpus, searching for the single most frequently occurring adjacent pair of bytes. When it finds a dominant pair, it merges them into a brand new token index and appends that new integer to the master vocabulary list. By replacing every instance of that pair across the entire dataset with the new single integer, the algorithm mechanically reduces the data volume, explicitly shrinking the total sequence length. This is a strictly iterative loop. The software scans the data again to find the next most frequent pair, and it is now fully capable of targeting the newly minted tokens. If our new token represents the letters T and H, it might quickly identify that this index sits right next to the byte for the letter E. It merges them, creating token number 257 to mathematically represent the complete word the. Through thousands of repetitions, the algorithm reaches an equilibrium. Highly common linguistic concepts organically fuse into single, hyper-efficient tokens. Conversely, rare words and strange misspellings aren't discarded or flagged as errors. They simply remain subdivided into their smaller, constituent byte chunks, completely preventing the system from ever encountering an unknown sequence. This mechanism directly satisfies the requirement of our starting efficiency equation. It maximizes the data compression ratio for every document passing through the system. BPE functions as a computational safeguard. It manages the quadratic expansion of attention costs by ensuring the transformer operates on the most information-dense sequence possible. Tokenization proves that securing algorithmic efficiency must start before the first piece of data is even processed. By adaptively compressing bytes into optimal sequences, the algorithm perfects the geometric shape of the inputs long before the first neural matrix multiplication takes place. This philosophy of optimization persists as you move up the stack. From writing custom logic for memory transfer, projecting performance through predictive mathematical curves, to aggressively sanitizing raw internet scrapes, every layer of the architecture is an exercise in resource extraction. The seamless interface of a chat window hides a physical reality defined by the orchestration of thousands of interconnected GPUs and petascale data streams. To push the boundaries of what these systems can achieve, you have to break past that clean API abstraction and confront the physical and algorithmic limits governing the hardware. Pushing the frontier of intelligence requires more than prompting. It requires an engineering mindset that confronts the physical and algorithmic limits of the hardware itself. To continue exploring applied model engineering and hands-on systems architecture, subscribe to the Learn by Doing with Steven YouTube channel. And for deeper dives into AI architectural strategy, listen to the Steven Data